Okay, good morning, everyone. It's a pleasure to start this session. I'm Antoine Kouchner, Vice Chair of APEC. If you don't know me, I should remove this, sorry. Yes, and so it's my pleasure to introduce this morning the reports of the 6 topics that were selected 2 years ago after the first Jenas meeting in Orsay for expression of interest. This is an open procedure with new ideas. And so we are going to listen to the reports of these initiatives this morning. And the first speaker that we have is Federica Petrica. And she's going to introduce the expression of interest about dark matter in the coming 30 minutes. So Federica, please.
So thank you very much for the introduction and good morning, everybody. It's a pleasure for me to open this session on the expression of interests that were initiated after the last Jenas Symposium. So on behalf of the organizers, which are currently Marco Cirelli, Caterina Doioni, Gabriela Zacharias, and myself, I will report on IDMU, that as the name says, it's an initiative for dark matter, which started in Europe, but we aim to go beyond frontiers. Yes, why dark matter? In the course of the session, I believe you will probably hear this hot topic more than once, given the appearance in many of the abstracts of the different expression of interest. So dark matter is really everywhere, and this statement has many different meanings, as dark matter is everywhere in a different sense. So let me briefly introduce the hot topic. There is an overwhelming observational evidence for the existence of dark matter on all astrophysical scales, from the small scales that are probed by rotation curves of galaxies up to the cosmic microwave background. There is a model which fits all our observations, telling us that in our universe, in fact, there is 5 times more dark matter than the ordinary matter we are made of. This opens up some very philosophical questions, but anyhow, the problem of this model is that it does not tell us what dark matter is and how it interacts. Therefore, we need experiments that test different mass ranges, couplings, and interaction channels. Theories provide valuable candidates for dark matter in a very broad range of masses and cross-section, as you see in this graph, which is adapted from a publication from some years ago. The scope here is not to provide you a complete overview of the different candidates, possible candidates, but just to convey the message that the parameter space of dark matter candidates spans many order of magnitudes, both in mass and interaction cross-section, which require a wide range of experimental approaches for their detection. So there is no single experiment which is able to explore such vast space. And with these extremely approximative contours that are overlaid to the plot, which are just there for illustration, I want to show you the experimental overlaps. We have dark matter searches and probes, which are fairly mature, for example, direct and indirect detection, collider searches, and other probes, which are instead more recent, as, for example, gravitational waves. But they overlap, and the message here is that overlapping doesn't mean competition, but means complementarity. Though this might really require a change of mindset, we have to realize that overlapping is positive. The message was already given yesterday. The most interesting regions of the parameter space is possibly where more approaches and more techniques overlap, because there is really the maximum potential for a thorough understanding of dark matter and of its properties. What does this mean in practice, change of mindset? For searches that are already mature, they need to develop a mutual understanding towards common discoveries and constraints on dark matter. And more recent searches need to develop connections with others for a fully complementary picture. And the main scientific drive for us should always be how to share the data when we can make common interpretations and give common constraints. These are the premises from which IDM-EU started. So in October 2019, the proponents participated in the first Jenas meeting. As you see from the list of proponents, we had a common shared interest in dark matter, but coming from different communities. In talking to each other, we realized that we all have some similar questions and some very basic, like what are your assumptions? How will your results influence my research? So we realized that our different scientific worlds do not really understand each other thoroughly. We might not meet the right people because conferences are too focused. Simply, we don't really know. But Jena got many of us together, and we realized that it wasn't just our secret desire to understand more of the neighboring communities, but the desire was shared by everybody. So since we all had this problem, something must be missing. And therefore, we decided to submit this expression of interest. So an expression of interest for dark matter, an initiative for dark matter. So we were ourselves strongly convinced that discovering or constraining dark matter requires broad discussions, and realizing at that point that there was no common platform where to do so, we aimed to be this platform for discussion where the different communities can find opportunities for cross-fertilization, and this is for mutual benefit. This is what we have to all understand, that communication and interaction is of mutual benefit. And our vision seemed to be very well fit with the European strategy, and here just some excerpts from the strategy update document, and just allow me to read one. I'll read the central one, which says that focusing on the quest for dark matter in the coming decades, there was consensus in further developing synergies between the efforts of the high-energy physics and astrophysics community. The discussion highlighted the need for enhanced communication between accelerator, collider-based direct detection and indirect detection dark sector searches. So this was exactly our feeling, and it was nice to find it written in an official document. So what is the objective? The overarching aim is to enable and facilitate the exploitation of synergies and highlight the complementarity of different communities, but how this translates in practice. So we want to develop a common platform where we can collect dark matter resources in an online meta repository that could facilitate new cross-community scientific communication, and that could help develop a common dark matter story for different audiences. We, of course, are well aware that some efforts already exist. We do not intend to duplicate anything, but more to bring together existing and future community efforts. So like pointing to data, to results and analysis tools, linking to existing resources, advertising main scientific events, collecting and connecting technical know-how whenever there is need for that. So we want, of course, to participate and not only facilitate where possible to discussions on results and underlying models, assumption techniques, with the aim of achieving some joint analysis at the end and some joint interpretation. And we want to have a forum where we can really informally and openly ask questions across communities, and without forgetting the aspects of public outreach, where the aim here is to collect data and share appropriate material for a broad public. So these are the three main objectives, very much overlapping, and how we intend to, and still intend to reach them. First of all, we had a year ago a kickoff meeting to feel the pulse of the community, from which we had a very positive feedback. So surely this meeting will be followed by more in future. We started developing an online platform and infrastructure. There was our main focus in the past year. And we initiated and supported some cross-collaboration activities. Currently, we organizers are mostly directly involved, but we aim to soon include general ideas from the community where we do not have to be directly involved. Just once it's triggered, it might go by itself, at least. This is our goal. And allow me to briefly go through these objectives. So first of all, the kickoff meeting. The meeting was intended to really get to know each other. We had more than 350 registered participants, and the attendance to the sessions were always very good. It was, of course, an online meeting at the time, since it was a year ago. During the meeting, we tried using live captioning to improve the accessibility of our meeting. We were convinced that this is a way to go. We found the result sub-ideal, but at the time, the company we hired for the purpose was really considered the best for this kind of actions. So surely more could and definitely should be done in that direction to be as inclusive as possible. Anyhow, live notes from each section and the list of items to follow up are available on the Indic of the event, together with, as usual, slides and registrations of each sections. The first day of the kickoff meeting featured, first of all, an introduction from us, from the organizers, and from the ECFA, APEC, and NUPEC chairs. And this was followed by 12 talks from different dark matter communities, where we asked the speakers, before preparing the talk, really to address a set of review questions, to have talks as similar as possible, and to address, for example, briefly a report on status and challenges in comparison of results and data sharing. These were the key points. The talks and discussions also included the expectations of how the initiative IDMU could be useful to their community, and proposals of common work that were then developed in the breakout sessions, which were held on the second day, and I will highlight the outcome of a couple of them. On day 3, we had a very inspiring outreach session where we should have learned how to produce a good scientific TikTok video. I'm not sure I would be able to do it, but still it was very interesting to learn how this has to be done. We had a roundtable discussion about efforts on dark matter, and we had a very interesting question and answer session that was, in a way, the prototype of the forum vision we had. So before and during the meeting, we collected via the mailing list a number of questions that people from different communities wanted to always ask about dark matter and never dare to. And we selected some of them to be answered by experts in some short talks. Of course, the idea of the forum will be to have all the relevant questions being answered by experts, since we will not be time limited in that framework. So I told you I would highlight the outcome of some of the breakout sessions. I picked 2 here in the interest of time, but the complete material for all of them is available online. The first session was about the forum. So we discussed with the community, and the need for a virtual forum to share expertise, ask questions, and search for collaboration was clearly shared by everybody. So we decided to add this functionality to the website. We, of course, carefully considered the issues that were raised during the breakout session, in particular with respect to moderation and maintenance. We have a working plan at present, so probably at the beginning, you might expect to be addressed by one of us, being asked to answer some questions, with the aim of, in the future, to have this running without our moderation, if we see that this works without frictions. Of course, we do not want to have one person dominating all conversations, and at the same time, the forum has to be a safe place for everybody, so there has to be a code of conduct to stick to, but the idea would be to then reduce with time the moderation to the absolute minimum, and we will have to see how good this runs. The second breakout session was centered about need raised by the community to have a cross-connection on hardware topics. The main questions that were addressed here were very basic. So how can I get information about similar R&Ds which are going on in different communities? Or how can I inform other communities about the R&Ds that I'm performing, that I'm doing, and that could be of interest for others? Many possible approaches were proposed, dedicated conference and whatever, and a point of future discussion for us is about the possible communication tools to be implemented in that respect. But there are many dedicated initiatives, and there are some talks where the issue will be addressed as well. So let me summarize for you the conclusion of the kickoff meeting. Our vision was and is to create the conditions for crosstalk and further collaboration. So we agreed that the first step would be to create the infrastructure where a common story could be developed. Therefore, we focused very much in the course of the last year on the preparation of the website. That should be the ground on which we all could propose ideas to work together. Again, the goal is not to necessarily create new groups, but mainly to develop projects within existing groups and communities. And of course, we intend to follow up on what is seeded by the initiative on coming meetings that as well do not have to be yet another dark matter conference. There is really no intention to do so, but maybe we could simply have satellite meetings to existing conferences. Now, let's move to the website that is functional to the success of the initiative, and therefore were the first topic where we really concentrated on after the kickoff meeting. With the support of Jenas and some funding from the European Union Horizon 2020 Research and Innovation Program, we commissioned the realization of a professional website for the initiative. In the original plan, it should have been ready already since a while. Unfortunately, apparently each single member of the developing team got infected by COVID during the last 12 months, and not all at the same time, so not aligned, which delayed things significantly. So right now we have a demo ready, which it's linked on the title slide, and will go online within the next weeks under the official IDMU address, where at the moment you can still find the self-made, rather primitive website we prepared ourselves to start up the project and start collecting the material. As I already stressed, the idea is not to duplicate what is already existing, but rather to link existing resources whenever available. The main content that we wanted to have is a list of experiments, telescopes, and searches with few key features like name, where to find the home page, what is the contact person, a brief description of the technique used. We wanted to have a link to repositories of data, tools, and results. A list of scientific events of interest for the communities, a collection of outreach material, and of course, the virtual forum that I already described. The content that is on the current web page and that is being transferred to the new one was collected by some curators that were students doing an internship or a thesis collecting information. You see the picture of some of them on the slide, and they had the opportunity to learn about dark matter and to work hands-on on projects with one of us or many of us at the same time from time to time. And you can see examples of this work in two of the posters that are presented in the poster session outside. Of course, having a collection of information is not a one-time job. This requires constant update and maintenance. So should you have interested students, tell them not to hesitate to contact us because there is a lot to do. And here you can see just some impressions from the demo website. More is on Gabriella's poster. You see that we have searchable tables from different experimental approaches. Direct and indirect detection are ready, just need a verification from the community, but still quite a bit needs to be added, and this will progress with time. And here, this is still the preliminary version of the list of outreach material, which is split by audience in terms of age group, language, background, and will soon become a searchable table as well. And since a number of data and software repositories for and beyond dark matter already exist, we will only link to these repositories and show highlights of software packages that change over time for adding visibility and for giving recognition to software work, which is an important aspect of our science. And last, I would like to give you a sense of some of the connected activities that are already ongoing. The first one is the Dark Matter Data Center, which is a project which is supported by the Cluster of Excellence Origins, whose purpose is to foster data and information sharing for the dark matter direct detection community. So it addresses issues both for the experimental collaborations, like how to make data open, which is a necessity, providing a data repository, preserving data for long-term availability, and providing person power as well for the data preparation, which is a non-negligible amount of workload, and provides support for phenomenologists as well, with detailed instructions on data and examples of analysis. So the aim of this Dark Matter Data Center is to bring together experimental data, workflows, theories for dark matter, all together on one platform. The project is ramping up, and you see many functionalities from the graph are already implemented, and some are being prepared. But if you want to know more, there is a dedicated poster outside in the poster session. And in the past year, we also brought forward some IDMU-related activities, even without the IDMU brand, really in the spirit of the initiative of being a meta-repository and not having its own brand on everything. So there is a number of activities which are of interest for the initiative or that were brought forward with the participation of a proponent that will result in a number of upcoming white papers, and more can be found in Josh's poster outside. So in conclusion, we are convinced that the initiative IDMU will allow to do more than the sum of its parts. The initiative is intended to be a service to the community and to provide exactly what we as proponents felt was missing at the time. The initiative is still in its developing stage with the precious support of the task force, which was put in place by Jenas to support us through the development of the initiative. And since the success of the initiative depends on the success of the activities that it will facilitate, really don't be shy and come to us with ideas, questions, and proposals. So thank you very much for your attention, and I'm happy to take your questions.
Thank you very much, Federica. Looks very promising, and we look forward for the opening of the website soon. So, is there any questions or comments, maybe? You have one question? Yes.
Good morning, and thank you very much for your presentation. I had a question for the website that you created. You said that you have received funds from the European Union, and I would like to know for the funding process if it was complicated and...
Sorry, this was maybe not clear. We did not receive dedicated funding for the specific project, but we used funding for outreach in an existing project. So it was in-kind contribution of one of the proponents to use part of the existing public outreach funds for this activity.
Thank you very much for the nice presentation. I have a question. What do you need to develop this activity more? What are the most urgent needs? You mentioned, of course, the students. I hope that they will come. This exciting topic, but what do you need really from the committees, but maybe also from the funding agencies or any other resources?
I think the first thing we need is participation, and participation of the community and an open mindset. So a community that is wishing to share. This is the real important thing to have. Because fundings are important to develop more strategies, to have more meetings, to have more tools. But the real key point for a success of such an initiative is the participation and an open mindset from the community.
But this you seem to have, right? Because you mentioned 350 participants to the kickoff meeting.
Yes, but this has to proceed with time. So sure. It's clear that a kickoff meeting is something interesting. You want to get to know each other. You want to learn the ideas behind, but then you have to commit in doing something. So it's always easy to say, yes, data sharing is important, but then at some point you really have to do it. You have to answer questions in the forum. You have to be willing to share know-how with others, share data. It's a step further. There is need for some commitment and some wish of the community to work in that direction.
Yeah, I think we have to accompany this as much as we can. It looks like a very good initiative. Thank you very much again, Federica. We now move to a second initiative, an expression of interest about gravitational waves for fundamental physics, and the speaker is Paolo Pani. Morning.
Okay, thank you very much. Thanks for this opportunity to present this initiative in this beautiful hall in such a nice conference. So this initiative is called Gravitational Wave Probes of Fundamental Physics, and I will present it on behalf of the steering committee for this initiative, which is these people here. So the outline of my presentation is the following. This is a science-driven initiative, so I will overview very briefly the science that we are investigating. And then I will move to discuss current and future activities connected to this science goal. And since this is the only presentation about gravitational wave science directly in this conference, I will also overview the science of the Einstein telescope, and I will show you how our initiative is pretty much connected to this third-generation detector. Okay, so our overarching starting point is that gravitational wave science is much more than astrophysics and astronomy. Of course, gravitational waves have opened a revolution that is impacting very strongly astronomy and astrophysics, but there is also the opportunity to learn more about fundamental physics, which I think is important for this audience. And I will follow the organization of this recent paper that the steering committee has published recently in April in the NUPEC magazine Nuclear Physics News, in where we identified 4 big themes in which gravitational waves will be very important for fundamental physics. In particular, we will discuss matter under extreme conditions, multi-messenger astronomy, and the important role of nuclear and atomic physics, gravitational waves and cosmology, and fundamental problems in high-energy physics and gravity. And as it will become clear, these are all multidisciplinary topics which will require a cross-cutting effort in merging different communities. And in fact, part of the effort of this initiative is to boosting the synergies and complementarities and working towards community building. Okay, so let me start with matter under extreme conditions. So we all know that gravitational waves from binary neutron star mergers provide a unique way to test matter in extreme conditions, so unique conditions in terms of temperature, densities, and isospin. And the questions that gravitational wave physics can address are what is the equational states in the neutron star core, whether there are different phases of matter, maybe other particles like hyperons, quark, etc. And it is interesting that the temperature and densities, the extreme values that are reached during a neutron star merger, are comparable to what can be probed with heavy ion collisions. And it's actually striking interesting that these snapshot simulations taken from a neutron star merger obtained with supercomputers solving Einstein equations in their full glory of a neutron star merger are similar to what you will get by simulating heavy ion collisions. And of course, the analogy is not only, say, visual, but if you look at the temperature density diagram of nuclear matter, what you will get is that nuclear neutron star mergers cover a region which is nicely complementary to what heavy ion collisions can do. And these, of course, call for synergies to explore quark-hadron phase transitions. I will later mention that a single detection with the Einstein telescope or 3G detector will constrain the equational states in the neutron star core at unprecedented levels, so this is very important for our initiative. Nuclear and atomic physics are also important for multi-messenger astronomy, and in this context, the electromagnetic counterpart of GW170817, so the very first binary neutron star merger detected by Lhc and Virgo, have provided the strongest evidence to date for the formation of heavy elements through the process called rapid nuclear capture, or R process. And here, as we learned yesterday, there are very few experimental data that describe neutron-rich unstable nuclei. So nuclear theory is really important there and is advancing quite fast. And this is instrumental to set up large-scale nuclear network calculations that will require thousands of nuclei, 50K more reactions to be included in the simulations in order to simulate, for example, the kilonova emission during and after a neutron star merger. And this eventually is used to inform nuclear theory. So as you can see, there is a circularity and a deep connection between these different areas. The very appearance and detectability of a kilonova requires knowledge of the high-energy spectrum in atomic physics, and this will become available even with higher resolution than the current one with future X-ray missions such as X-RISM, Athena, NICER, and Gravity. So going to the connection to cosmology, gravitational waves provide what are called standard sirens. These are very important sources because they allow us to measure redshift and the Hubble constant quite precisely in the future. As you might know, the Hubble constant is currently at the center of attention or a disagreement, as we heard yesterday, because different observations give different values, and in the future, gravitational wave observations can disentangle this tension in one way or in the other. But they can also be used to test dark energy, so finding a fundamental origin for the acceleration of the universe, or understanding modified gravity at cosmological scales. Another important point is that gravitational waves in the 3G era will have access to the early universe, so they can probe inflation and phase transitions in the early universe through the detection of a stochastic gravitational background. There are already hints of these stochastic backgrounds in pulsar timing array, but in the future we will have more confirmation about this. So the reach of future detectors is very well explained in this plot here. So current detectors can only explore the local universe up to redshift at most of a few, not much more, while in the 3G era we will reach redshift of order 100 or more, so deep in the so-called dark ages of the universe where not even the first stars were already formed. This is very important because if we detect black holes at such a high redshift, they cannot be of astrophysical origin, they can be of primordial origin, so formed right after the inflation. And it's interesting because these objects might form actually the totality of the dark matter. This is also shown in this plot here, showing the redshift versus the mass of the black hole. The horizon of LIGO in Virgo is very small, it's just a redshift of a few. ET and LISA will reach redshift much higher in a complementary mass range, so they will cover altogether a big range of masses for potential primordial black holes. Let me see if I want to say something there. Okay. Yeah, so moving to fundamental physics, there is also something else that gravitational wave can do about dark matter, and we also heard something about this in the previous presentation. In particular, there is an interesting connection to ultralight dark matter or wave-like dark matter, in the sense that ultralight bosonic fields around black holes emit gravitational waves in a very peculiar way. And what is shown here is the signal, which is almost a monochromatic waves, for ultralight fields, such as axion-light particles, dark photons, in the range of 10 to minus 11 electron volt or lower. So this is a very low mass range in which dark matter behaves as a wave. And as you see here, is complementary to current searches in the laboratory with other observations. So this is very nice because it shows complementarity between different topics. And it's also important that this signal will be detectable even in the nightmare scenario that was mentioned yesterday. So even if dark matter does not have a coupling to standard model, this effect is gravitational, so it will still have a signature in gravitational waves. Concerning fundamental physics, there are also connections and ways to test general relativity, both at the classical and quantum level. And an important, very recent, say, ongoing activity is to port high-energy techniques to compute, for example, scattering amplitude to the realm of gravitational waves. For example, to compute high accuracy waveform, gravitational waveforms that should be used in the searches. And in fact, the EFT, so the effective field theory community and the scattering amplitude community are working in close contact to gravitational wave astronomers. Gravitational waves are also probes of dark matter in several different ways, and I think this is very well explained in this sort of diagram here. This is taken from this review by, coordinated by UCAP director Gianfranco Bertone. And you see that there are different aspects of the dark matter that can be probed with gravitational waves. This also gives me the opportunity to show you what are the activities that have been done and will be done in the future. So last year, February 2021, we organized an online meeting. It was supposed to be in presence, of course, then it became an online meeting on this particular aspect of this initiative, so primordial black holes confronting gravitational wave data. And here we brought together experts both from the gravitational wave community and data analysis, and experts from primordial black holes, cosmology, high energy physics. I think this was one of the first time they talked to each other. And it was a very successful event with more than 200 online participants. This is, of course, very important, as I was saying, because we are working toward community building. And in the same spirit, we are organizing another workshop, this time about the second aspect of the initiative, so environmental effects and gravitational waves. This will be instead an in-person meeting organized in Rome in 1 month from now. And we have, at the moment, more than 100 participants. And, well, if you are interested, this is the webpage, and you will find more information there. And I should mention that this is organized in collaboration with UCAP, so the European Consortium for Astroparticle Theory, that is funded also by APEC. So one of the main activities we have been working on in the last 2 years was the write-up of a proposal submitted to the COST action. So COST is the European Cooperation in Science and Technology. This proposal is called GWSci, so Gravitational Wave Science, and is the follow-up of a previous COST action that was founded a few years ago. Our contribution coming from this initiative was to enlarge the scope of this proposal by including topics that were not included before and that are of interest for our audience. In particular, as you will see these, so these are the 4 working packages of the proposal, and you will see that there are teams such as multi-messenger astrophysics, equational states, QCD phase transition, etc., which were not there before, so we are contributing with our expertise on these topics. The budget of this proposal is €500,000, and it goes essentially for workshops, community building, and dissemination outreach activities, but most importantly on scientific visits, especially for early career researchers, which I think is very important for our goals. It was submitted in October 2021, and the results are expected anytime soon within this month. Okay, so let me move to an overview on the Einstein telescope. I already mentioned ET several times, so I think it's about time to give a proper overview. So ET pioneered the idea of a third-generation gravitational wave observatory. This will be an underground facilities using cryogenic technologies with a triangular shape and arms which are at least 10 kilometers long. And the idea is really here to have a new infrastructure which is capable to host even upgrades in a long time scale of about 50 years. And the sensitivity should be at least 10 times better than the nominal sensitivity of advanced detector. This will give ET a much bigger horizon so we can explore the universe farther in time. And it should happen in a wide frequency range, in particular improving the sensitivity in the low frequency range, which is crucial to detect intermediate mass black holes. LIGO and Virgo have just started detecting these objects, but there might be a new family beyond 100 solar masses that we should detect with ET. The instrument should have high reliability, so high duty cycle, and thanks to the triangular shape, it should have standalone localization and polarization disentanglement, which will be very crucial for multi-messenger astronomy, as I will mention in a moment. The crucial point is that ET will be both a precision physics machine, so it will improve more than an order of magnitude compared to what LIGO and Virgo can do right now, but also a discovery machine, so it can discover sources and phenomena that are out of reach current generation detectors. So as you know, ET entered recently the roadmap of the European Strategy Forum on Research Infrastructure. So this was a proposal submitted by Italy, Belgium, Netherlands, Poland, and Spain, and many other countries and funding agencies joined later on. The consortium is currently coordinated by NICEF and INFN, and there has been large preparatory fund available in several countries. Very recently, a project for infrastructure development has been approved, and there are others that are just being submitted. A few weeks ago, we heard the news that the Netherlands intend to invest more than 40 million euro for geology, R&D, and organization, and they reserved almost 900 million euro in case ET is built at the border between the Netherlands, Belgium, and Germany. And similar investments are under discussion in Italy, and we should have the outcome very soon by June 2022. So the organization of ET is in constant development, but I think right now the situation is the following. So there is the ET Observatory, which is coordinated by NICEF Director Stan Bent-Velsen and INFN Director Antonio Zoccoli, who coordinates and interacts with the board of scientific representatives and the boards of governmental representatives, and with the project directorate, chaired by John van der Brandt and Fernando Ferroni. The project directorate coordinates the infrastructure development, the project office, which oversees the ET project, and also monitors the ET collaborations. So the ET collaboration is managed by the ET steering board, chaired by Michele Punturo and Harald Luke. And this steering board manages some specific boards. There are 4 of them, which are in this slide here. So Site Characterization Board, Observational Science Board, Instrument Science Board, E-Infrastructure Board. I'm part of the Observational Science Board, coordinating the fundamental physics divisions, because each of these boards is divided in divisions. And well, without entering any details, you might see just by looking at the title of the scientific topics that most of them actually have a strong overlap with the interest of Jenas, but also with the interest of our initiative. And there are also other divisions not related directly with observation and science, which are of interest for example, particle physics and accelerators. Let me just advertise that in 1 month from now, there will be the 12th ET Symposium in Budapest. This will be the formal birth of the ET collaboration. So if you are interested to attend, this is the webpage. So a few more details on ET key elements, and then I will overview the science, which is of interest for us. So ET requires a wide frequency range, as I was mentioning. This is very important, because wide frequency range and good sensitivity means that we can reach wide mass range at high redshift, which is very important. And it's particularly important that the sensitivity at low frequency should be very good. And in fact, ET sensitivity is actually better than the one from its US counterpart, Cosmic Explorer. This will allow us to detect massive black holes above 100 solar masses, even above 1,000 solar masses at high redshift, which will be very important. In order to do so, we need, as I said, underground cryogenic facilities with long arms, at least 10 kilometers long. And particularly important design specification of the instrument is the fact that it is a triangle that can operate also as a multi-detector design, which means that it can allow for localization and polarization disentanglement. And this will be very important for multi-messenger astronomy, as I will mention in a moment. Okay, so the science of ET is very rich, and I cannot really give an overview on this. Let me just mention that these are the topics that are under discussion within the Observational Science Board. I find this classification a bit maybe misleading, because, for example, within astrophysics, I would claim that neutron star properties such as QCD at high densities or exotic state of matters is fundamental physics, but nevertheless, many of these topics, including neutron stars, multi-messenger astronomy, and all topics listed here are of interest, I believe, for this audience and for our initiative, in particular the natural compact object, test of generativity, dark matter, dark energy modified gravity, and stochastic background. So let me really give you two highlights about ET science. So the first one is that with ET, we will be able to do really black hole and neutron star demography. So we are going to detect 10 to 5 events per year. This means about 1 event every 5 minutes, meaning that during the time of my presentation, we will detect about 6 mergers, either black hole neutron stars, so mixed event, or neutron stars. And in fact, as shown in these distributions here, ET will detect essentially any binary black hole at a given redshift occurring in the universe, and it will detect most of the binary neutron star mergers at a given redshift. But not only it will be important for detection, but also for sky localization. In fact, the fact that the sensitivity at a low frequency is very good means that we can localize the sources quite accurately and send early alerts to electromagnetic facilities in order to look for an electromagnetic counterpart of all these mergers. ET alone can detect order 100 events per year with a sky localization better than 100 square degrees, which is pretty good. And in combination with its US counterpart Cosmic Explorer, it can detect order 1,000 events per year with sky localization better than 10 square degrees. So this will be really a game changer for multi-messenger astronomy. Finally, I think my last slide before the conclusion, I mentioned before that ET will be unique in order to constrain the equational states, which I think is particularly interesting for this audience. Let me give you some more details about this. So let us look at the situation now, actually not even now, but the situation with advanced LIGO design sensitivity. So the best we can do with 2G detectors. So what I'm showing here is the Byte Factor, so essentially a measure of the evidence that we have in order to distinguish two equational states. I'm taking these equational states as a reference, and anytime you see this bar going beyond -2, it means that there is a very strong evidence that you can distinguish each of these equational states from this reference one. As you can see, for some of them you already can with a GW1708-17-like detection, which was actually very loud, but for many of them you cannot. For example, in this case here, APR4 and these equational states are essentially indistinguishable within a 2G measurement. So let us now look at what will happen in the 3G era. So I will take this particular case, which is very conservative, it's the one that we cannot really disentangle right now, and ask ourselves what will happen if ET was detecting that same binary here. So remind that ET will detect one event every 5 minutes, so it will be very easy to have 20 events. It will take less than 2 hours. So in less than 2 hours, we will have 20 events like GW1708-17. For most of them, these equational states, which are the most challenging to disentangle, can be completely distinguished from one another. There will be cases, for example, this one, where, for example, the inclination will be not optimal or the distance of the source is too large that they cannot be disentangled. But after 5 minutes, there will be another one in which the two same equational states will be completely disentangled. So this will really be a game changer for constraints on the equational states and will allow to put constraints and pinpoint the phases within the neutron star core much better than now. Okay, so concluding outlook of the initiative. So the work in progress is we as initiative members are contributing to the ET science, both by coordinating some divisions of the observational science board, and most importantly, contributing to the write-up of a blue book. So this blue book will be one of the main outcomes of the ET Observational Science Board. It will collect all the science that can be done with ET. We are also contributing to LISA science, both in the fundamental physics and cosmology working groups. Just today on the archive, there was the white paper on the fundamental physics LISA working group that was recently accepted for publication. We are organizing workshops, and we will continue in the future. But most important, in the future, we are working toward fundraisings because, well, virtual meetings and events are important, but in-person ones are more, and they require money and efforts. And in particular, we want to organize short-term scientific missions. This will be very important to exchange expertise in a multidisciplinary initiative and to train a young generation of scientists. We are working toward creating software repositories, and also there is some discussion about organizing our activities, which is pretty diverse and rich, in working groups and have recurrent meetings among different working groups in order to speed up the activities. So with this, I thank you for the attention, and I leave this advertisement for the next CT Symposium meeting. Thank you.
Thank you very much for the nice talk and the good publicity for future Einstein telescope. Do we have questions or comments? Yes, first.
Thank you very much. It was very nice, and it's clear that the science case is very good. My question has to do more with the future and the organization of these working groups you were mentioning. Have you already thought about the structure? Just how are you going to maximize the, let's say, the synergies between the three fields? And okay.
Sorry, the synergies between?
The working groups you are going to organize, and how are you going to maximize the synergy between APEC and NUPEC, basically? I mean, that is the topic here.
Yeah, I think that the two main actions will be the organizing workshops. Those will be have been already very successful. It will be in the future because, I mean, in each workshop we are organizing, we are bringing together different communities, so there is already some exchange of idea there. I think that short-term scientific missions are particularly important. So the way we see this is that we should have a scheme for, I don't know, people, especially young researchers coming from a community, to visit another group, another laboratory in another field, and therefore really for a few weeks exchange ideas and work toward common projects. So those are the two main actions that I would say would be important.
Yeah. Thank you also from my side for your nice overview. How are your connections to the high-frequency gravitational wave initiatives, which I think the 10 kilohertz to megahertz region might be even more interesting for fundamental particle physics than the low frequency part. Mm-hmm. Do you have connections there?
Yeah, I think it's a very good point for, I would say, historical reason, because the steering committee that was created 2 years ago didn't have that expertise. This was not included in the action, but I think it will be particularly important, for, especially, for example, for neutron star, yeah, for the post-merger phase of neutron stars, detecting the high-frequency case will be very important. So yeah, maybe this is something, we never discussed this in fact, but this is something we should probably discuss and try to include in the initiative. Thank you.
Hi, thanks for the nice talk. I just had a detail, since we are in this combined symposium. So you talked about the equation of state. So I was wondering, what is the nuclear physics contribution into this equation of state? Do you already have some strong connection?
I would say yes. For example, the equation of states I was mentioning before in the study, I mean, essentially they all have different particle contexts. Some of them include hyperons, quarks, etc. And so there is already strong interaction with nuclear physics in order to constrain them more. There are also ongoing studies of, for example, constraining three-body interactions, and those are already done within collaborations between gravitational wave astronomers and really nuclear physicists working on the equation of state. So there is already work in progress in that direction.
Yeah, thank you very much for this talk. And there are a lot of activities going around regarding all these workshops and activities and synergy effects regarding Einstein telescope and gravitational wave detection. So my question is, what is the particularly role of this expression of interest, and how one can support this from our communities, from ECFA, NUPEC, and APEC, and what are your concrete plans for the next steps within this expression of interest? I mean, it is difficult, I understand, because there are so many things which are organized anyhow. So how do you see the particularly role of this EOI?
Yeah, so this is an important point. I totally agree, of course, that there are things organized anyhow, but I think that within those things that are already organized, it's important to bring a particular expertise or a particular focus for a given topic. I can give you 2 examples. There is a lot of activity going on within the ET Observational Science Board, and there is important to have people from this initiative that can sort of give more emphasis to a given topic compared to others. And same thing happened for the cost action proposal that we wrote, because probably that proposal would have been written anyway, but maybe without including neutron star physics, for example, or equation of state and things like that. So it's very important to enter this initiative, even if they are happening anyway, in order to sort of, divert a bit the direction of those initiatives. Considering what we'll need in the future, I would say that fundings and money is the most important things, because as I was mentioning, virtual events are almost for free. They only require time and effort and, of course, enthusiasm from the community, but have a limited scope. In-person events are much more important also from a scientific point of view, but they would require money. So this is why we spent a lot of time trying to find some money. If we get funded, we will have money to, for example, scientific missions, workshops, and things like that. That will be very important to build the community and push forward it.
Okay, thank you very much. So we have time, so no problem about this. It was a bit I had the same questions. I think I'm wondering how you should get organized not to create things that already exist and at the same time have enough influence. You mentioned UCAPT, and are you, the people you showed the list of people, you're all members of ET consortium, or you?
No, not all of them. Some of them have also coordinating role within the Observational Science Board. Some of them are part of UCAPT, so there is really a synergy between different organizations, and putting these things together is important.
Okay, I think it's very good, but indeed I think we have also to have a close look to how we can help and streamline, not to dissipate too much the effort. Anyway, thank you very much again for the talk. If there's no more questions. Thank you. We move to the last speaker for this morning session, and this is going to be Pietro Viscia about machine learning optimized design of experiments. Thank you.
So, hello. This is not working. Fantastic. Should I? Is there anything I can do to make it work? It's working. Okay. Not entirely. Should I? No, it's really not. I point here? No. The light is not working either. Huh? I don't know what's... So, while... it's off? It was... Okay, fine. Sorry. Thanks to the previous speaker. Thank you very much. So, okay. Very well. I've been already kindly introduced. Thank you very much for the opportunity of being here. I want to start by reading the headline of this morning from a Belgian local newspaper saying that the European Union is losing the AI race, says a report adopted by members of the European Parliament who voted on Tuesday on a report that could also set the global standard for the technology. So I hope to show you today which are some possible paths for being leaders of artificial intelligence applied to physics in the fields of interest of this consortium. So in particle physics, we have a hugely complex experiments, and to design them, optimize them, we need to have a costly full simulation that takes a long time to run and is very complicated. It's characterized by the interrelation of many parameters. We have a huge number of subdetectors that cannot be optimized, and this is a superhuman, optimizing them in a global way is typically a superhuman task that so far, that ideally could be, should have as a target the final physics goals of the experiment, but this is not always possible because of the sheer complexity of the task. So currently, the paradigm that you know very well for this kind of things is to track first, destroy later. So you track particles to measure their momentum, and then you they extinguish themselves in the calorimeters where you measure their energy. So these are systems that are characterized by a large redundancy in the detection systems. Robustness is embedded in this kind of designs. However, these designs are typically symmetrical, even if this is not automatically guaranteed for optimality. And typically, they have been optimized by looking at subdetector-specific figures of merit, like the resolution on the energy measurement in the calorimeter, and so on. Now, this paradigm served us very well and will continue serving us, but we want to show that this can be now assisted by artificial intelligence, in particular by machine learning. So why do we need to have a joint optimization of all the detectors at the same time instead of only optimizing with respect to different parts of the detector? Well, in a general way, if you look at a reasonably simple function, the global maximum of this function is here, what we call the joint maximum. But if you instead try to find the maximums of this function independently for the two parameters, you may obtain something that for one parameter maybe is close to the joint maximum, but for the other parameter could be in a dramatically different region. So you are not identifying the actual maximum of your target function. And if you do things sequentially, so you first optimize with respect to one parameter, and then across that solution you find the maximum for the other parameter, you could even worsen the situation and be completely fooled in your search for optimality. So This highlights that mathematically does make sense to try to optimize jointly a full system with respect to all its parameters. And the 2020 update of the European Strategy for Particle Physics and the talks yesterday highlighted that we actually need to do this kind of large optimizations on new large long-term projects that will push our technological skills to the limit. However, we live in a world that is plagued by climate change, by famine, by pollution, and these are unprecedented challenges that are also shifting the public opinion, bringing it to be somehow less receptive to fundamental research. So it's a moral imperative, according to us, to try to work within the budget that we have and maximize the extraction of the scientific value from that limited budget. And in a framework like optimization of an experiment, we can try to do that by writing our budget inside the optimization algorithm. How? Well, you may be familiar with the typical gradient descent. It means that we have a target function, which we call the loss function, that represents how well we are reaching our physics output. And then we climb downwards the gradient of this function to find the optimal place. So we can insert cost, and by cost I don't mean only monetary cost, I mean also the physical constraints, like I cannot put my detector through a wall or things like that. We can model all of this inside this kind of loss function. But instead of modeling it through a wall that impedes the loss to drift toward high cost, the most effective way we have found is to add a penalization term to the cost, which basically means that when your cost goes over budget, you have a huge loss component. And this leads to optimization systems that actually learn in a kind of unbiased way the best solution given a reasonable budget. So, of course, we would be naive in saying that such an optimization of a very complex experiment can just be solved by AI and that AI can give you the optimal solution full stop. So what we aim at is accounting for the fact that, for example, we cannot parameterize all the effects that may affect optimization. So what we plan to do is to look at regions of this loss landscape which are near to the optimality, so near the minimum, this red region maybe, before things get too wiggly or too not optimal, and to provide this landscape of possible solutions to the physicist, who will have the last word in deciding which is the one that is most feasible with respect to budget or other constraints that maybe couldn't be parameterized meaningfully in our algorithms. So we want to assist the physicist with this kind of solutions that can empower them to find maybe solutions that are better than the ones that we would find by manual search. So the optimization via gradient descent of this is very difficult and involves computing computer derivatives. So technically what we do is we have some function that is coded by a computer and we want to differentiate it. So previous paradigms in differentiation include either manual differentiation, but for very complex systems that's very error-prone and unfeasible. You could use software like Mathematica to do symbolic differentiation, but you need an expression in closed form, so you cannot kind of use loops and things like that. And still, when you do that many times in a chain, as you do typically when for a machine learning algorithm, you obtain large expressions that are very then hard to compute and taxing. So it's not really a good way. I think we all know what's the problem with numerical differentiations. Basically, in a finite precision machine, don't divide small numbers. And so the actual solution to the problem of minimizing these huge systems is using what we call automatic differentiation, which is a way of obtaining exact computer derivatives without too much overhead. So the way it works by the concept that every mathematical function can be divided into atomic operations. Atomic operations for which you know how to compute the derivative very easily, like a ratio, a logarithm, the sine, cosine, and so on. So first we build what we call the primal trace, so the exact sequence of operations that encodes the function in a computer code. And once we have done that, we need just to track the numbers that correspond to each of the operations. Then if we want to compute derivatives, we have two choices. Either you derive with respect to each input, or we derive with respect to each output. Now, of course, the more inputs or the more outputs drive which of the two is the best. And since the typical systems problems that we have involve functions that have many inputs and one or a small set of outputs, which are our goals, then our method of choice is what we call the reverse mode. And the key of this method is that while you are computing and tracking these numbers, you are always tracking what we call the adjoint, which is the numerical computer derivative of each atomic operation. And this results in exact differentiation at a very low computer cost. And this is what powers inside this kind of algorithms. Okay, so now that I laid more or less the ground on what we are doing, let's look at how we started looking into these things and what we are doing now. So a first seminal effort was the attempt, the successful attempt at encoding the unsystematic uncertainty into the learning process. So if you have trained a machine learning algorithm in particle physics, what you probably and typically have done is you train your algorithm on your nominal simulation, you freeze it, and then when you have simulation with the systematic uncertainties applied, you just feed that new simulation to the frozen algorithm. What you can do instead is to encode your Fisher information matrix, so the uncertainties of your problem inside the loss function. And in a feedback loop, this can inform the inference that you can do on the parameter of interest that you're trying to determine. And these have been shown. Did I close it? No. And this has been shown to actually work pretty nicely. So here you have a likelihood function. In blue, you have the results of the typical procedure in energy physics. And in orange, you have what happens when you use this inference-aware neural optimization. And you see that the likelihood function is smaller. So the uncertainties on the final results are smaller. So to understand what is due to, so what actually the algorithm is doing, we can look at the correlation between the parameter of interest and the systematic uncertainties. And the effect of this neural technique is that basically the correlation between the systematic uncertainty and the parameter of interest. And this explains how the method works. In order to do that, however, this matrix of uncertainties must be differentiable because we want in this pipeline to differentiate everything. And this will be a leitmotif in the next slides. We need to find a differentiable form for things that would maybe not differentiable by themselves. A more practical endeavor is the optimization of the Lhcb electromagnetic calorimeter. So this is something that is constituted by many cells with different sizes and densities, and the problem is that with a high luminosity LHC, we need to cope with the harder operation conditions. So this requires a reoptimization of the structure of this calorimeter within a budget cost. So, and what you can do is, well, the first naive things you can do is just you increase the number, the granularity of the cells by having cells of smaller size, and this is a first level optimization that you can do. And then you can do a full study. This is an example where the signal significance is B sub s to j psi with a pion decaying to 2 photons, and the photons are detected in the calorimeter. And you can try to do an optimization and see how your signal significance increases where, for example, the number of channels of the calorimeter increases. So this is a rather trivial result, which is reassuring in the sense that it makes sense. But an interesting thing about this that will be shown in a poster in the poster session is that the number of channels actually drives the cost-performance trade-off, and in this specific case, the geometry, the placement of these cells is not so crucial to the optimization. And in order to perform this global optimization, again, since generators like GN4 are not yet differentiable, they have to use a differentiable surrogate, in this case, generative adversarial networks. So the problem of differentiability is really crucial to this. So to come to our expression of interest, in 2019, we were 10 people in 4 institutions, and we submitted to you this expression of interest. We created a collaboration that we call the mode collaboration. We had a website, Twitter account, and so on. And now, in 2022, we are 28 people across 15 institutions. We are particle physicists, nuclear physicists, astrophysicists, and, crucially, computer scientists. So we have gathered a community with also some rather high-profile names in computer science, which have started to bring these ideas to light. Thanks to you, we published our first paper as a collaboration in the official NUPEC journal, and well, you can find it here. This is March 2021. And then we started actual work. So one of the key efforts of the collaboration is to optimize a muon tomography apparatus. The idea is that you have a passive material, maybe it's a container at the customs border, and you want to know what's inside. You want to know maybe if someone is smuggling uranium in this container. And you can do the cosmic, you can use muons from the cosmos to infer the material that is contained inside this passive material. So essentially, you have detectors that detect the muons. You infer the scattering angle for these muons, and from there, you can get an information about the radiation length and therefore the material. And if you encode this in a fully differentiable loop, then you can include cost constraints and systematic uncertainties into this optimization of the detector parameters that tells you where to put your detectors and which material can you afford to have a target performance. Oops, sorry. So we have some very, very preliminary results. We have systems that actually seem to learn something. We can track which part of the loss function comes from the physics goal and which one comes from the cost of the apparatus. We can do some simple imaging of this kind of layered passive material. And by devising some clever summary statistic, it seems that we have quite a good performance, can have quite a good performance in discriminating scenarios where there is uranium in the container and there is not uranium in the container. So this sounds promising at the moment. And this is done by having loss function which has a combination of performance and cost. I have said many times that we need surrogates to make things differentiable, because we need things to be differentiable in order to be able to have a differentiable pipeline. So if things are not differentiable, you can do 2 things, essentially. One is find a surrogate. So maybe you train a generative network to approximate your non-differentiable thing with a differentiable function. And this is what we've done so far. Or you can redesign your non-differentiable component to be differentiable. And this is something that has been done by some authors of mode recently when they made differentiable the matrix element computations from MADGRAPH. So here you can generate some physics process with MADGRAPH, and then you can compute a fully differentiable matrix element, obtaining some PDFs which have embedded the gradient in them. And this kind of object is something that, which have these small arrows. This kind of object, something that is automatically embeddable in any full optimization pipeline. So down the line, we hope that in the future we will see a differentiable version of Gen 4, or it's probably a stretch because of we don't know how to differentiate showers and so on, but stuff like PT as well. So there are many other efforts in mode. So we will have 3 posters today. The one is about muon tomography by Maxime. He is Maxime. You can ask him anything about this muon tomography effort. And we have other 2 posters by Lucas and Alexi, who for different reasons couldn't be here. But all of these posters show that this kind of optimization assisted by AI can give actual improvement over human found solutions. In simple cases, we have improvements of factor 2 even, and we have found also some serendipitous things, like you will find it in the poster by Lucas, that actually we can learn the muon, we can regress the muon energy, even if we weren't originally planning to. More about that on the poster. There will be either Tommaso or me around the posters to illustrate these points. The last thing I would like to talk to you about is what we are doing to build a community around these concepts, to bring this, to make a critical mass and bring these concepts forward. So, the first effort is a workshop that we organized in my institution in UC Louvain last September. This workshop saw 100 participants, and about 1/3 of them were in person, even if there was COVID. And the 30 talks spanned across 6 communities: muon tomography, collider physics, meaning detectors, but also accelerator design and control, nuclear physics, astrophysics, neutrino, and computer science. And we were funded, crucially, by you. And without your support, we couldn't have done it, honestly. So thank you very much for the support. You made possible the seminal creation of this kind of community. And this workshop actually raised interest not only in the people who attended, but also in people who didn't attend. So, and this led to the creation of a white paper about the end-to-end optimization of particle physics instruments with differentiable programming. This is a collective effort where we were joined by several computer scientists from a collaboration called CIVER that does proton CT. And in these documents, we not only explain the mathematics behind this, but we also have about 50 pages of, 50 pages of use cases that span from medical physics to many other fields. Fields of interest to you are probably muon tomography, calorimeter optimization, accelerator design and control. So we are trying to lay the path forward for our and others' efforts. We are not stopping with one workshop. We will do yearly workshops. You are all invited to join our second workshop that will be in this September in Crete. We have already a first confirmed keynote, Adam Paske from Google Brain. If you don't know him, he is one of the main authors of JAX and the main author of DEX, which is another differentiable framework for scientific experiments. So he's a really very nice guy. We had him already in a previous workshop, and we had hugely good interactions. So, without taking much of your time, I would like to leave you with the idea that MODE is a collaboration that tries to maximize the extraction of scientific value in a constrained environment, constrained by budget and so on. We want to assist the physicist with the landscape of solutions that the physicist will be able to use to choose the final optimal solution according to the criteria that are necessary. And we are trying to create and guide a multidisciplinary community to bring these concepts forward and to realize these things. We are searching for funding right now, and yeah, that's all for me. Thank you.
Thank you very much, Pietro. Do we have questions? Yes, many questions. Okay, let's start here.
Yeah, thank you. Very interesting. The real intelligence will remain all the time skeptical about artificial intelligence. You know that.
Yes, absolutely.
Human would like to see proofs every time.
Yes.
So this takes me to benchmarking. How benchmark of such approach can be done? Or let me put the question differently. Could you take an existing project that has been built with human thinking and optimization and try to apply whether the choice that had been done this way 10 years ago was the right choice or not? Can you do that? I can give you an example. Yesterday we heard about Agata. It's a simple multi detectors. You may apply this and tell us whether we were wrong or not making the choice we made.
Yeah, it's certainly possible. We were exploring, it's always difficult to just re-optimize something that someone else optimized and show them, it wasn't really optimal. There was a paper, I think, by Tommaso, who showed that for the Muone experiment, the optimization, the solution that was found by the collaboration wasn't really entirely optimal according to if analyzed through a machine learning algorithm. Maybe you can say more about that. And we are certainly exploring the idea of trying other real cases that have been already done in the past to show our performance. But yeah, it's and interpretability is always a concern. So maybe Tommaso can briefly describe that or not.
Yeah, I'm also answering this question. So the thing Pietro was pointing out is, in fact, the paper where I showed the factor of 2 improvement in the relevant figure of merit of Muone, the differential Q squared by a simple optimization. So these things being huge increases, okay? So, but I wanted to make a comment. As stressed by Pietro, mode is a spontaneous initiative, and it is maddeningly complex to do these things. So we shouldn't hide it to ourselves. And we are not the right persons to do this because we are not computer scientists, and the field is moving away. If we don't catch it, we will not be able to keep in track. And artificial intelligence requires to develop interfaces. It's not, if we are not profit-driven, we will be dead, okay? So we need to keep the path to this. So we have started to do this, but as this audience includes many of the decision makers in our community, I want to take this opportunity to point out that Jenas and Lhcb, which is a US endeavor, are only sources of funding at the moment. And we wish the community would support this direction of research more consistently because, as Pietro pointed out, there are huge potential gains and innovations that may be possible that can only be discovered by machines because they look at the whole problem, not parts of the problem. I cannot optimize for the best precision on lambda of the X. I can only optimize with respect to the resolution of photons in my calorimeter because I cannot do the full thing. These things can do the full thing, okay? There are huge potential gains and innovations that may be discovered. This is the point I wanted to make. We need to to sensitize the community. We don't want to substitute you guys, you detector builders. We want to assist you, put you in the center of the decision process and give you the tools to take better informed decisions. But this is a huge long-term plan that takes 10 years, probably 15 years to be completed and bring dividends, so we cannot pull it off alone. Okay, thank you very much.
So my question actually links a little bit also with this, and thank you very much for the very nice presentation. It's also nice to see that your community is building up and you are organizing a lot of workshops. My question has to do with the fact, are you also thinking in let's say, joining other forums, like there are these workshops towards the future Higgs electroweak top factory, and there is a lot of work thinking on the detectors for the future. Are you planning to get also involved in this and let's say, cross-share more with detector experts that are working towards these future machines and so on?
Yes, absolutely. So we have started, well, apart from this presentation today, we have started to show our ideas in different venues, which are even more detector specific or future collider specific. Some of the talks from yesterday that mentioned the design on new colliders, new accelerators, and so on, can actually profit from our work, and we definitely plan to tackle these issues. Of course, right now we are starting with the simplest ones because we want to show robust use cases where also things are more explainable. So where we can convince the community that these things learn something that makes sense. But then, yes, of course, we need to use these kind of tools precisely for the future colliders that we are going to develop. Otherwise, it's going to be bad.
Okay, thank you very much for that. I'm sure there are lots of technical questions I could ask, but I wondered about the multidisciplinary group that you've got together. You've included a lot of, or you said you've included computing scientists, which is, I suspect, absolutely essential to get the best cutting edge stuff. How have you, are these people computing scientist researchers in the sense of academics, or are they from like Google or whatever? Because one of the problems I've always had is how do you interest somebody in another field in a problem that's good enough for them rather than just churning through stuff that they know as a service? So have you been able to tackle that issue?
So the computer scientists that we are working with and we are talking to are actually from rather diverse from this point of view. So we have people like Adam Paske, who is from Google Brain and develops software, open source software that targets also scientific experiments. So these are industries that are sensitive to the fact that academic institutions need access to these tools and need also to help develop these tools. Of course, they do it because, like that, everyone will use the industry's tools, but okay, that's their turn, the game. But we also have academics, in particular the ones from this collaboration called CVERT that we mentioned, are computer scientists that are trying to use analogous methods for improving proton computer tomography. And these are all academics. They are developing specific computer tools like software that solves the problem of optimization for general pipelines. And that's why we're finding this very useful. We are also submitting research grants with them because these are really the people that can help us writing down in the most effective way cutting-edge software that does this optimization. Our idea is not to have a series of software that solves each specific problem. So the ultimate goal would be to have a general modular pipeline where you encode the specificity of your problem, but the machinery is generic and common. This would be the ultimate goal of this. And they can help.
That was a really interesting talk. I wanted to pick up on one specific technical point, though.
Yes.
You mentioned Xeon 4 a couple of times, that it's not yet differentiable, which we know. And I wanted to ask you about that. I mean, we, of course, are already putting in a lot of effort in developing machine learning models to somehow substitute for the stochastic particle tracking. In your opinion, is that the way forward, to just continue to develop these surrogates? Or is there a different way that we could think about the problem? You know, we're just doing a Monte Carlo and deciding which interaction the particle is going to undergo. Is there a different approach that we could take here? Because I personally, I don't have a very good feeling for that. I don't see a particularly obvious way forward aside from machine learning, which we have good reasons for doing otherwise anyway, because it's much faster than the particle tracking. But, you know, what's your feeling on that?
My feeling is that there is no clear-cut answer, in the sense that So the very practical thing that you can do nowadays to get something differentiable is building a surrogate, which is intrinsically an approximation, and is somehow a way of condensing, well, basically of building a PDF in an approximated way. So I personally don't know what would be the technical, practical way of making, building a differentiable distribution without using a surrogate. But we are starting discussing with people who are actually developing these generators and so on to find out what is the best way, maybe at the first stage, to reduce the scope of these surrogates, so to use them only really in the parts of the software where you cannot get away with the surrogate because of the stochasticity of the problem. And then, who knows, maybe we will have some breakthrough that can help us leave the surrogates, but yeah. Thanks.
Yes, thank you very much for your initiative and for this. I would like to know if you already considered to include the computing expert with the detector expert in order to constrain also the cost that will come with the computing use of your detectors, because we know that it's already a big cost.
Yes. At
the same amount of the detector cost.
Yes, and we are also looking at this. For example, in one of the nodes of mode, the NF1, there is one of the responsible of the cloud computing software of the regions part, the Veneto part of NFN is within mode, and we are certainly starting to look into these problems. And one other thing that I would like to mention is that, of course, these kind of models need to be trained, and there is a growing literature about the carbon footprint in training these models. But what we would like to stress is that in our case, the memory footprint of training a few times this kind of model, even if it's very complex, is far smaller than the carbon footprint that you would get from not optimizing an experiment in this way. So we are looking at the computing part both from this point of view.
Yes, I was not talking only about the footprint for you computing, but also for the computing that we use to exploit our detectors. Mm-hmm. So, yes.
Yes, but we are in collaboration with computing experts that are also within the collaboration to tackle this kind of those things. So we are not forgetting this part, I say.
Very good, thank you. So we have to stop here. I would like to thank the three speakers of this first session morning, and thank you all for the lively session. So it's now time for coffee break, and we reconvene at 11. Thank you.
That's all. So, welcome to the second session of this morning on expression of interests. My name is Herbert Wittmann. I'm Deputy Chair of NUPEC. And I first want to say the expression of interest that you hear today are the result of a call after the first Jenas meeting. And we called for expression of interests to spawn some activities across at least 2 of the 3 communities, so in order to bring the communities more together. And most important, this call is still open. That means we will probably also make another announcement whenever there is an idea about joint activities between the communities. You're welcome to submit an expression of interest. The committees will look at it and they will endorse it if it is sound. And what we actually hear now, there are 3 more expression of interests that have been endorsed by the communities, and there is 1 more submitted that has not yet received endorsement. And let's start with the first one by Laura Fabietti from Technische Universität München about nuclear physics at the LHC.
So thanks a lot, Everett. So it's a pleasure to be here in this fantastic hall. I feel very honored to explain to you what we thought we could do at the Lhc in terms of nuclear physics, but more specifically, trying to use the nuclear physics measurement to say something to help astrophysics. And this expression of interest has been prepared by Alexander Kalweit from CERN, Philipp von Döttingen from University of Hawaii, Manoa, and Akira Onishi from the Yukawa Institute of Theoretical Physics in Tokyo, and myself, in Kyoto, sorry. So, nuclear physics at LHC. So my talk tried to illustrate to you what we can do. And obviously I bring only some example of the state of the art. We hope that this will develop in the future. And today I will focus on 2 experiments, the SMOG experiment at the Lhcb and the Lhc experiment. And I will show you an example of 2 topics. One is the production and annihilation study for antinuclei, and how these studies impact on the indirect search of dark matter in our universe, or study of cosmic rays, so propagation in our interstellar medium. And then I will show you how we can study strong interaction among hadrons at the LHC, and how this impacts the equation of state of neutron stars with the ambition of solving the so-called hyperon puzzle. So what is the aim we have? It's really to realize these beautiful triangles that connect at the Lhc the physics of QGP, which is investigated in many experiments, together with astroparticle physics and hadronic physics. And we have determined that nuclei could be a good platform or a starting point to promote connections. So beyond what we normally do and publish in the different Lhc experiments. And we hope that Jenas will help us to develop the network which we need to use the nuclear physics measurement for astrophysics application, for example. So I want to show you now these 2 examples, these 2 physics examples. Let's start with antinuclei propagation in our interstellar medium. As you probably know, antinuclei are interesting because dark matter candidates such as WIMP might decay into antinuclei like antideutron, anti-helium-3. And after the decay, this particle can be propagated and reach, hopefully, the experiments, satellite experiments such as MS, or balloon experiments such as GAPS. The same can happen actually when high-energy cosmic rays impact on interstellar mediums, nuclei, and can also produce also antinuclei. And obviously, what is particularly beneficial for antinuclei is that the signal to background, where the signal is the dark matter and the background are the cosmic rays, it's actually very large for low energy. So that's why antinuclei are golden probes. But it's clear that in order, even if astrophysicists will observe antinuclei, right? In order to really understand what is going on there, you need experiments at accelerators. Because Normally, astrophysicists look at an equation, a differential equation of these kinds, which tells you how the flux of antinuclei vary as a function of time. And this equation has three different components. The first component is the source part, which tells you basically how many antinuclei are produced. Then there is the propagation part, which we experimentally at accelerator have no impact on. But then there is the last part, which describe the absorption of these antinuclei through their passage. And this is basically also a topic where we can contribute. So now I'm going to show you the example of the contribution of the Lhc experiment for the first parts of the equation and the third part of the equation. So the two experiments that I bring you as an example today are the Lhc experiment and the SMOG experiment at Lhcb, which is a particular declination of the measurements that have been carried out at the Lhcb. So why are these two experiments very good to do at look at antinuclei? Because they have a very nice particle identification. So it is possible to measure production cross-section for antiprotons for both experiments. And in case of Alice, this has, at the moment, the best data for anti-deuteron and anti-helium-3 productions, right, at the Lhc. Together, actually, with the experiment at Brookhaven, right, to also mention them. And the two experiments are slightly different because on the left, we have really a collider experiment at energy up to 13 TeV. While in case of SMOG, we have basically a bag of helium in the target region where basically a fixed target experiment at a square root of S of 100 GeV has been carried out. Now, you might ask which are the energy which are important for astrophysics. And that's why I'm showing you now these two plots. We showed you on the x-axis the kinetic energy of the primary cosmic rays, right, that can produce antinuclei. And on the y-axis, you have the kinetic energy of the antiproton or the antideutron. What can you see from these two plots? That the maximum is actually located at square root of S around 10 GeV. So, the Lhc is not the best place to look at these nuclei, right? Because actually the physics of cosmic rays happens at SPS energy, so at much lower energy. But then why do we look at Alice or Lhcb? Because there you have a copious production of antinuclei. While at experiments like the NS61 SHINE, cross-section for antiproton have been published, but antideutron are still not measured there, hopefully in the future. And there is the AMBER program at COMPASS, which would like to measure antiprotons, cross-section. But at SPS, probably we need new detectors with high-grade measurements to really be able to see antinuclei because we are close to the threshold. So our strategies is we make the best use of what we have. So we use the Lhc as antinuclear machine to try to learn something, okay? And this is the first piece of information. So I want to convey to you the very precise measurement of antiproton cross-section measured by the SMOG experiment within Lhcb. So basically, the measurement of the cross-section is very important because in this plot you see the flux of antiproton divided by the flux of proton measured by satellites. And the data, as you can see, they have a little tension with the background generated by cosmic rays in the high momentum, high kinetic energy part. So it's very important to have a perfect control of the cosmic rays background, let's say, in this region. And that's why this experiment, this SMOG experiment is so important. And there were data published in 2018, and recently Moriond, an update was presented where not only the cross-section of antiproton are discussed, but even the source, let's say the fraction of primary protons in comparison to weak decay can be pinned down. So what I wanted to say, people are really going into the microscopic description of this production cross-section. But if we want to look at antinuclei, at the moment the best place to do so is the Alice experiment. There are several publications. Here I just show you 3 examples. And basically what this histogram should, let's say, convince you about is that we can measure with high statistic and high precision antiprotons, antideutrons, and anti-Lhc over a very wide PT range, okay? So we measure the cross-section, but now, what is important for us? In order to study dark matter, you need to understand the production mechanism of antinuclei. And the cross-section is not sufficient. Then you have to go further, and what we normally do, we define the probability of forming antinuclei compared to the probability of having single nucleons, right? So that's why experimentally we see this BA parameter, which tells you the ratio of the cross-sections of, for example, antideutron with respect to the cross-section of protons. And this is something which has been investigated with, you see, many data points, so many colliding systems, PP at different energy and P-LED collision have been investigated as a function of the system size, also as a function of PT. And within our initiative, many theoretical work have been stimulated, because basically theoreticians, people expert in nuclear physics, people expert in astroparticle physics, try to model this production. And in these modelings, the microscopic properties of interaction among nucleons are considered. So here you see some example of the work produced even most recently in 2021, where we really try to enhance the collaboration between experimentalists at the accelerators and theoreticians. For example, this work where Bellini, Bloom, Calveit, and Puccio are, let's say, are the authors, put together the works of 3 people from Alice with 1 theoretician from the Weizmann Institute. Okay, so why do we matter? So, basically, our measurements of these B2 parameters, here you see another published results now as a function of the transverse momentum of the nucleus. It's very important because this is the essential ingredient which then determines the cross-sections of the produced antideutrons when you simulate cosmic rays in your interstellar medium, basically, and their reaction. And this has been recently published in a paper in the journal PRD, where you can see here you have 2 different curves, and the 2 different curves assume different modelings for the antinuclei production. So you can see the curves differ by a factor 100 up to 1,000 at low energies. So meaning that if we don't understand how nuclei are produced at accelerator experiment, it will be very, very difficult to pin down the cosmic contribution with high precision. Actually, even more exotic things are going on at the Lhc. Recently, theoreticians put forward the hypothesis that the dark matter signal, exactly in a region where IMS claims to have seen but not yet published the anti-helium-3, might come from an enhanced production of anti-helium-3 coming from decays of lambda sub b particles. Okay? So now, the experimentalist is now called upon to demonstrate whether this decay of lambda sub b in anti-helium-3 really exists. And the Alice experiment took up the challenge, and these 2 plots shows you, unfortunately for the moment, only simulation of what we expect will be the signature of anti-helium-3 in our detector during round 4, and maybe in round 5, when the next generation detector, the so-called Alice-3, will be built. Clearly also the Lhcb colleagues are looking at that already now. Indeed, thanks to the Velo detector, that can be employed to look at antinuclei, and thanks to the fact that they have a trigger that selects lambda b decays, yes, they probably be able to really measure this channel directly. This would be obviously a super important contribution to the modeling of possible decay channel of dark matter. The last thing that I want to show you in this nuclei stuff is how we are even able at the Lhc to measure how antinuclei are absorbed in the interstellar medium. What we do? We use the detector, in this case Alice detectors, as a target. So we know we produce plenty of nuclei, so helium-3 and anti-helium-3, and we look at their disappearance. And we can determine the annihilation cross-section. And we did so, actually, for antideutrons and for anti-helium free. So here you can see basically the inelastic cross-section for these two antinuclei as a function of the momentum. And then once we have this inelastic cross-section, we can go back to the propagation of antinuclei in our interstellar medium and use this cross-section to evaluate the transparency of our universe to the passage of anti-helium free. And this is exactly what we did. Here you see basically the final result. What do you see here? The flux of anti-helium free expected from typical dark matter signal with a mass of 100 GeV, and the expected contribution from the background, from cosmic rays. And what we as an experimentalist and at the accelerator contributes to is to evaluate the difference between the dashed line and the solid line, respectively. The dashed line shows you the case in which you have no absorption, right? The anti-helium free goes through without getting disturbed, while the continuous line shows you what happens if you have this absorption. And so you can determine the transparency. Summa summarum, we have determined for the first time experimentally that the transparency is high, because it's something between 25% to 75%, bit different between cosmic rays and dark matter, but actually is a huge number, okay? So the last few minutes, I want to show you another example of how the LHC experiment can be very useful to study, for example, the equation of state of neutron star, which was also mentioned in another expression of interest, 2 talks before mine. Indeed, we don't know what is inside neutron stars, and if all the measurements of neutron star mergers via gravitational wave are very important, the job of a nuclear physicist is to make hypotheses about the microscopic behavior of what is happening. And now, so we can think that only neutrons are included in neutron stars, but actually what can happen is that since the system is greedy, for larger density, the system might transform neutrons into other particles, for example, in hyperons and kaons. And now this scenario, whether you have lambda and psi hyperons popping up in neutron stars, strongly depends on the interactions of this particle with the nucleons. Okay, so whether this plot is right or this plot is right depends on the interaction. So we need a place where we can tag this interaction. And actually we have found a place where basically we can solve the puzzle of studying any combination, right, of interaction between an hyperon and nucleon. And actually not only for pairs, but soon even addressing triplets, we have found a place because we can use the Alice detectors. So, and the idea here is very, so it's sketching a simple diagram. What you do, you produce a lot of particles at the Lhc. You assume you know how the space coordinates of this particle can be modeled. Then, if you have an assumption of an interaction, okay, by knowing the potential, you can solve the Schrödinger equation of the potential to determine a wave function. And then you can combine source and wave function into this integral that already in the 70s was demonstrated to be equivalent to a correlation function that we can measure. So basically, the idea is you measure a correlation function which can be above unity if you have an attractive interaction and below unity if you have a repulsive interaction. And from measuring this correlation function, you can deduce the wave function, right, and hence the interaction. Okay, so what was done now recently? So we measure lambda, psi, omega, sigma zeros. And basically, these are now, let's say, the results published. And what is important here in this context is that this result could only be achieved because we collaborated with theoreticians. With theoreticians expert in chiral effective field theory, or theoreticians who do lattice calculations, right? Without this collaboration, this data would stay in the drawer without their interpretation. And the collaboration of with this theoretician allow us to put basically these lines, right, upon our experimental data. and the lines contain the interaction. So from this comparison, I can really extract the single particle potential of lambda, of sigma, and psi, and those are the ingredients that then go in the equation of state. Just to show you an example of a collaboration, this is exactly what we did. We took this single particle potential, and we calculate an updated equation of state. So here you see basically how hyperon can pop up at different energy density, depending on their interaction, which is now constrained to the ALICE data. And here you can see how one can convert this equation of state into a measurement of the mass versus radius, actually into a behavior of a mass versus radius. And this line, I mean, is only just provides you an example, obviously, right? But shows you how, by measuring interaction at an experiment at the LHC, you can then infer on the neutron star, and only because you collaborate. Okay, so concerning the activities that we have carried out, we have organized a MIAP workshop at the MIAP Center in Munich on the topic of nuclei, antinuclei, cosmic rays, and dark matter this March, February. Despite of Corona, this was a hybrid meeting with about 50 participants coming from particle, nuclear, and astroparticle physics, and I think it was extremely useful to have this meeting. We would like to have a workshop which also includes the topic of neutron stars, maybe after the summer with the support of Jenas. And we would like, actually, we were thinking that it would be good to extend the LHC studies, including all the SPS experiment, right? Because probably there are new opportunities upcoming. Indeed, the new opportunities could be, for example, using the NS60 Plus experiment, which should be an high luminosity experiment to measure antinuclei, or to investigate the possibility of measuring hypernuclei at the anti-proton ring at CERN. But anyway, what I think also is very important, where we are a little bit behind, unfortunately, is to think, to design a database, right, where antinuclei and interaction data from accelerator can be put in a form that can be used, basically, right, by astrophysicists, so that what we do is really useful. Thank you very much for your attention.
Yeah, thank you very much, Laura, for this nice talk, presenting this expression of interest. We have time for some questions.
Yes, thank you very much for your talk. I must say that I was really, impressed by the, in particular, the reaction that you mentioned of the decay of the anti-lambda B into helium-3 plus 2 protons. So actually, is soft QCD in the status of providing a reliable, decay width for that process? Because there are really a lot of quarks.
That's a very good question. Not quite. To my understanding, not quite, not yet. But that's why the two collaborations decided to look for it, to look for the decay experimentally, because we have a means. I think Lhcb, they are really after that. They can tag the lambda sub B decay, and they can look if they see an anti-helium-3. So finally, this is an experimental-driven activity. Once the cross-section has been measured, then I think the theoretician will be motivated to put more effort into this channel. Yeah, so I think that it's driven by the experimentalists at the moment, this activity.
At LSU, you explore equation of state, but at very high energies, which are, as you mentioned, are far away from the energies, I think, necessary for neutron stars.
No, that's,
so what's there of the extrapolation?
So, no, we don't, so I was too fast probably in explaining that, but we measure interaction at small relative momenta, because this correlation technique with which we extract all the interaction is in the region of 100 MeV, 200 MeV over C. So we really measure the two-body, three-body interaction in vacuum, and then those, let's say, ingredients are used to, like scattering experiment at low energy, it's equivalent, are used to then as input for equation of states of dense system. The problem of extrapolation is obviously that you have to extrapolate from vacuum to dense matter. This is a problem that all the equation of state at the moment have. So that's the maximum we can do at the moment.
Okay, other question? Maybe I have one regarding this antihelium-3. I remember 20 years ago it was said one antihelium-3 nucleus in cosmic rays is the proof of antimatter galaxies' existence. That has changed a lot, it seems.
No, well, so the thing is that if an antihelium-3, I mean, if now this measurement by IMS will be confirmed, at the moment they are much higher, right, than the cosmic rays that you expect. So that's why the idea of these Lhcb decays comes up. But anti-galaxy, anti-stars are still an opportunity, an hypothesis that, for example, has been discussed at MEAP, right? But actually, I don't know. We have to see whether these counts are confirmed, and then we have to see about everything else. But it's for sure a very exciting topic. But it's not excluded, no.
Another question, maybe one more regarding, I mean, you said nuclear physics at LHC, you have now ALICE and Lhcb. Is there some interest or some opportunity also in the other LHC experiments? Or are you more going to SPS, which seems to be reasonable?
I mean, in the realm of what we want, we are doing at the moment, these interactions, so neutron stars and dark matter, the next natural extension is the SPS experiment. But this does not exclude that in the future, we also include CMS and ATLAS investigation in the ion sector. I think we are very new in the business. This is just the starting of something which hopefully will be useful. But we can just start with the first steps. So.
Yeah, thank you. I see no more questions, so thank you again, Laura. And we come to the second presentation of the EOI by Jörg Brett. From Jülich, he will talk about storage ring for the search of charged particle electric dipole moments. Please.
Yeah, okay, that works. Yeah, thank you for the opportunity to present our project here. So it's about storage ring experiments to search for electric dipole moments. We heard already about electric dipole moments yesterday, but that was a focus on neutron and neutral particles. So what is new here is to do something for charged particles. And I will give a short motivation. So what is an EDM, relation to CP violation, matter-antimatter asymmetry in the universe. Then I will talk about the experimental method. And the main theme here is to observe a spin or polarization motion in a storage ring. And then I have first experimental results and plans for the future. And the results come from the Cooler Synchrotron COSI in Jülich, and then we have plans for a dedicated storage ring. Okay, the motivation, just one slide essentially. An electric dipole moment is a permanent separation of positive and negative charges in a particle. So if you like a picture, you take this picture here, you have the spin, and the dipole moment has to be aligned along the spin vector, and then you have two separate charges. That even works for the electron. So this picture is as wrong as picturing the spin of the magnetic moment by a current inside an electron, but maybe it helps to describe the effect. So it's a fundamental property of a particle like the magnetic moment, like mass and charge. What is special about it, it's only allowed if you have a violation of T, so time reversal and parity, and of course T violation is equivalent to CP violation. And therefore it has a close connection to matter-antimatter asymmetry in the universe. And axion field or axion-like particles, they also lead to an oscillating EDM, which you could search for even easier than such a permanent electric dipole moment. Okay, so this just shows that it's really a property of the particle. So if you look into the particle data booklet, you have the electric dipole moment here for a proton. And no electric dipole moment was discovered yet. So if you look into the particle data booklet for all particles, you only have upper limits. So for the deuteron, it's the order of 10 to minus 25 e-centimeters. That is the unit usually used in the field. The next slide shows the current status of for various particles. So the orange bars are the experimental limits. Yeah, so for electron, muon, tau, for neutron, proton, lambda. Actually, the electron was not measured on a pure electron, but on a thorium oxide molecule. The proton results comes also from an atomic measurement on mercury. And the blue areas show kind of expectations you would expect, for instance, from supersymmetric models. So if you take this serious, then the electron measurement excludes already a large part of this. Of course, if you put all the phases in supersymmetry to 0, then also the EDM will be 0. So there is not really a clear prediction. It spans several orders of magnitude. That is important. And another important thing is the gray bars, they show the expectation from the standard model. And if you look at the current experimental sensitivity, which is for the neutron and for the proton of the order of 10 to minus 26, you see that the standard model is way below. So if you measure something in the near future, you know it's something new. Yeah. The easiest thing would be that, at least for hadrons, that theta QCD is not equal to 0. That is, of course, you could say that is the standard model, but that would be then the easiest explanation, at least for the hadrons. So we would like to focus on measurement of EDMs of charged particles. So for instance, to do a direct measurement on the proton and also measurements on deuteron or helium-3. And at least the statistical precision we could reach is 10 to minus 29, so which would be somewhere here. The challenge is to get the systematics to the same level. Oh, maybe, thank you. Good. You may ask, if there are so many efforts to measure electric dipole moments, why add another measurement? I try to illustrate this with this slide, so I don't go through all the details, but the important thing is, on the left side, there's the experimentalist point of view, so you have measurements on neutron, proton, on nuclei, on atoms, molecules, or leptons, and the theorist would like to uncover the fundamental theory behind. So if you have one single measurement, you can imagine it's hard to get through this chain. So if you had a set of measurement, of course, one will eventually find out what is the fundamental theory behind. Okay, yeah, now about the experimental method for charged particles. The principle is very easy. So you build a storage ring with a vertical magnetic field or a radial electric field. You can use both to have a beam on a circular orbit, actually this way around. And then if an EDM exists, if the particle has initially a spin aligned with the momentum vector, then you get a torque from the electric dipole moment d, and that will then cause a build-up of a vertical polarization. Now comes the nuclear physics part. If you use, for instance, a proton or deuteron, you get a vertical polarization. You scatter this of a carbon target, and you look at a left-right asymmetry, and you can observe this polarization. Yeah, life is not that easy. So in general, the spin motion is, of course, much more complicated. A particle does not have only an EDM, but has also a magnetic dipole moment, which causes also motions in magnetic fields and electric fields, which are orders of magnitude larger. So what you in general have, you have a composition of a precession around this vertical axis due to the magnetic dipole moment. You know this from NMR experiments. That's just the same thing. And you have a motion around the radial axis due to the electric dipole moment. Okay. And to look at this equation in a bit more detail, you have to look at the so-called Thomas BMT equation, which describes the spin motions. This is even a simplified version. So you have this term here due to the magnetic dipole moment, which is given by the anomaly G here. And here you have the part for the electric dipole moment, now described by a dimensionless factor, eta. And eta, for electric dipole moment of 10 to minus 29, eta is only 10 to minus 15, whereas G is of the order of 1 for hadrons. That tells you somehow how difficult it is. So there are various approaches, so it's a complicated equation, so you can play with the magnetic field, electric field, you can choose different particles. So one option would be to use a so-called frozen spin mode. That means you choose a combination of magnetic and electric fields such that the MDM rotation is frozen, is zero. Yeah. That is what is called frozen spin. If you don't use a magnetic field, so this term goes away, then for particles which have a positive G factor, you can choose the gamma value such that this part vanishes. So for a proton, for instance, where the G factor is positive, you could build a ring with only an electric field to come to this frozen spin. For other particles which have a negative G factor, you have to use a combination of E and B to get this frozen spin condition. Yeah, this shows somehow the playground for protons for this frozen spin condition. So what I mentioned here, if you choose not to use a magnetic field, so magnetic field is zero, if you are able to operate deflectors with magnetic fields of 8 megavolt per meter, that immediately tells you you have to use a proton beam of 700 MeV, which is available, but you have to build a ring with a bending radius of 50 meters. It's quite a huge thing. So we were thinking about a different option, which we call a prototype ring, where you add a moderate magnetic field of 0.03 Tesla, and then you end up also again with this frozen spin condition, but you end up with a momentum of 300 MeV, which is also available, and a ring radius only of 9 meters, so a much smaller project. So I try to summarize these various options. So the first one, which I call number 3 somehow in time sequence, would be this holy grail pure electric ring. So you don't want a magnetic field, I should add. The big advantage is you can run a beam clockwise and counterclockwise simultaneously. That helps, of course, enormously for canceling systematic errors. Yeah? The disadvantage is it only works for particles which have a positive G factor. Then the combined ring, it works for any kind of particles. You only need a smaller ring size. But now you need both an electric and a magnetic field. And now to run clockwise and counterclockwise, you have to have 2 consecutive runs with a reversed B field. Yeah. And the third option, which I didn't discuss yet, is to use a pure magnetic ring. The big advantage is such a ring exists and you can do measurements. That is always a big advantage. You have a lower sensitivity. You have a precision due to the G factor. So you don't have this frozen spin condition, and therefore you get a lower sensitivity. Okay, about the statistical sensitivity, again for the final ring, it's a simple formula. You need the number of particles you can store. You need the measurement time or spin coherence time, we call this, so the time you can keep the spins together so that they don't decohere or depolarize. You need the polarization of the beam. You need the analyzing power of the scattering process to detect the polarization, and the strength of the electric field. And if you plug in these numbers here, you really end up with something of the order of 10 to minus 29 centimeters for 1 year of running. So statistics is really not the problem here. The real challenge is to get the systematics to the same level. And I would like to say a few words about this. Yeah. So the signal you are after is a rotation due to the dipole moment. And if this is really of the order of 10 to minus 29, you expect a rotation of a nanorad. You can easily calculate if you have a radial magnetic field of 10 to minus 17 Tesla, that also causes rotation of a nanorod. So it makes it really difficult. Then there is a fact which is called geometric phases. If you have in the ring longitudinal and vertical magnetic stray fields due to the non-commutation of rotations, you also get effects, if this is of the order of 1 nanotesla, effects of the order of 10 to minus 9. And even general relativity predicts a spin rotation even 10 times larger. Even theorists told us you can use this as a candle, standard candle, to calibrate your device, so that effect should be there. Yeah. And there may be more effects which I didn't discuss yet here. Of course, the recipe, if I add these contributions, some have the opposite sign of the EDM measurement. So if you use clockwise and counterclockwise, if you take the sum, these geometrical phases and general relativity drop out. Unfortunately, the most difficult one is the radial B field. So they have the same, the radial B field has the same sign as the EDM, so you cannot disentangle both. Yeah, we concluded from this that's really difficult, so that we should use a staged approach and not go directly to the final ring with 50 meter of radius. I think I have 2 slides on the systematics about the radial field, how you could get hold of the radial field. If you have 2 beams stored simultaneously, and you store really the beams, you know that the vertical force is 0. And the vertical force comes from vertical electric field. It comes from gravity, which is the same for both. But the radial B field, they are opposite. So if you have a radial B field, you will immediately observe Betatron oscillation of the 2 beams. So that is how you could handle radius. So not by directly measuring a 10 to minus 17 Tesla field, but by measuring the distance or vertical Betatron oscillation of beams. Okay, yeah, this is again the spin rotation, these 3 contributions. Yeah, then, as I mentioned, we have a kind of staged approach, and I would like to say a few words about the first 2 steps. So the first step, I said, is experiment at the existing Hula-Synchrotron COSI at Forschungszentrum Jülich, which is a pure magnetic storage ring. And the next step would be then a ring with initially electrostatic and then adding a magnetic field where you could test a lot of things and also do first measurements, and then finally going to a full electric ring. Yeah, so I will show now some results and plans. The results comes from the first step, and then the plans for the second step. So COSI, as I said, is a magnetic machine. It's a circumference of 180 meters. We did measurements with deuterons, 1 GeV over C momentum. So you have the beta-gamma factor, the G factor, revolution frequency. So we have a lot of devices here. Here we have a so-called Wien filter, which allows to manipulate the spin. Then we have a solenoid, which also helps to manipulate the spin. Then we have a pyrometer, which is not shown in this plot, in this graph here. And what we did, we performed an experiment where we flipped the spin from a vertical direction to a horizontal direction. It starts to precess. And then with the help of a radio frequency Wien filter, which provides orthogonal electric and magnetic fields, you can create a kind of partially frozen spin situation. So you would expect then also in a magnetic ring a build-up of a vertical polarization as a function of time if an EDM exists. So this slide shows that we observe this. So when this Wien filter is off, the vertical polarization stays at its initial value. When we switch it on, we get a build-up, which is in principle proportional to the EDM, but unfortunately at this stage also proportional to many, many other perturbations like misalignments of the ring and things like this. This is still under investigation. If you would like to learn more about this, so there is a poster by Vera Schmakova on the analysis of this data, and by Max Fitz, he's a PhD student working on the understanding of these perturbations using tracking tools, spin tracking tools, to see how misalignments of magnets affect this observable. Okay, yeah, just one slide on other results we achieved with COSI. So first of all, to perform these measurements, many preliminary work was necessary. So first of all, we reached the so-called spin coherence time of over 1,000 seconds. That means if once we flip the spins in the horizontal direction, they stay coherent, they precess coherently for 1,000 seconds. So I don't know, we call it coherence time. I think in NMR it's called depolarization, this T2 factor. So different words, but it's essentially the same thing. And we achieved this for over 1,000 seconds. And the spin precession is 120 kilohertz, so there's a very fast precession, and to keep this for 1,000 seconds is really a big achievement. Then we could resolve this fast spin precession in the horizontal plane. We developed a feedback system where we measure this polarization and can act on devices in the accelerator to define a phase of this rotation. And with all this, so these were 3 PRLs in the past, we could, for instance, do a single bunch spin manipulation. So we injected 2 bunches into the ring. One we left vertically polarized, and one is affected by the Wien filter. So the Wien filter the Wien filter was only switched on when this bunch crossed the Wien filter, and not when this bunch crossed the Wien filter. So you can see that we call a pilot bunch to observe systematics, and the other bunch is then rotated up and down, as indicated by this arrow here, by the Wien filter. And here you see then the decay of this polarization, which is here obviously less than 1,000 seconds, but that was a different running condition. Yeah, then I would like to spend a few words on searches for axions or axion-like particles we did with COSI. The axion field gives rise to an effective time-dependent theta QCD term, and this in turn causes an oscillating electric dipole moment. So the electric dipole moment, up to now, I was only talking about this DC part, constant electric dipole moment, but an axion would lead to an AC part, and AC measurements are always easier. 5 minutes, perfect, yeah? AC measurements are always easier than DC measurements, as we know. And this frequency is directly related to the axion mass, so it's the Compton frequency. And what you do, you have your particles spinning around with this precession frequency, omega MDM, which appeared in the Thomas DMT equation. And if this frequency equals the axion frequency, then you get a resonance effect, and you can also get a buildup. Yeah. So what you can do, you can either, if a theorist tells you the axion has this and this mass, you can spend a year running exactly at this frequency and look for it, or you could scan this omega MDM and just look somewhere. So we did this. We scanned because nobody told us where to look. So we just took our default momentum, 1 GeV, and scaled it a bit. So what we did now is then we scanned this omega MDM by slightly changing the energy of the particles or momentum, and thus we scanned also the search range for the mass, and we looked for a build-up of a vertical polarization. I have to disappoint you, we didn't find anything, of course. So you get many of these kind of plots. You fit this for a step, of course, you always get something. But doing this analysis, we could set an upper limit. So this is, I think, a 90% limit in this mass range, which is a very narrow mass range for the axion mass, which is around half a nanoelectron volt. But you see the sensitivity here statistically, that was only a few days of data taking. We get to 10 to minus 23 with a machine which was never built for this. So what you see here is just the result from many scans, such scans from the previous page. So So just one after the other, a few days of beam time. And as I said, this axion frequency or the axion mass, you can scan this by changing the revolution frequency, which changes then the gamma factor, or in future, if you choose different particles which have different G factors, you can, of course, move to completely different regions. Yeah. Okay, this is one plot taken from the particle data booklet, where we just added our measurements. So that is just this needle here corresponds to this plot here. So it's a much wider range. So this needle could, of course, be longer and thinner if we just set on one frequency instead of covering a wider range. And there's even a debate that we underestimated our sensitivity because there is a great enhancement factor with respect to NMR experiments because our particles have speed of light, essentially. There are some fresh papers on the archive. We are still studying this, so this is really preliminary. So then let me spend my last 2 minutes on the plans for a dedicated ring. So the idea is to build a ring with a smaller size, 30 meters, and to operate first the electrostatic ring, to store the number of particles you would need, to run simultaneously both beams, clockwise, counterclockwise, as indicated here. And then the frozen spin condition can only be achieved by adding magnetic fields. That would be the next step. You could benchmark simulations tools and develop key technologies for a final ring. And of course, the idea is also to perform a first EDM measurement. If you want to learn more about this, there is by Rahul Shankar and by Saad Siddique a poster. Please have a look. Okay, this is how such elements could look like. So you have electric bendings here, and then magnetic coil without iron, because if you want to reverse the field, it's better to have no iron, how it could look like. And we submitted a research infrastructure concept development. I think that's the official name, a long name, Presto, it's called, that's the acronym. And the partners are INFN, GSI, FZJ, CERN, Max Planck Institute in Heidelberg, RWTH, Liverpool, Krakow, and Georgia Tbilisi State University. Okay. Yeah, that brings me to my last slide. So I hope I could convince you that EDMs are a unique probe to search for CP-violating interactions, and that charged particle EDMs can be measured in storage rings. We have first steps were done at the Kohler synchrotron COSI in Jülich, and the next step is that to construct a new type of accelerator, MEV momentum range, to answer fundamental questions of particle physics and cosmology. And I phrased it this way because then all the three communities find their buzzwords in this sentence, hopefully. Okay, thank you.
Yeah, thank you very much. Thank you, Jörg, for this nice explanation about charged particle EDM measurements. Are there questions to this presentation?
Yeah, thank you very much for the nice talk and congratulations to the results. I would like to stress the importance, because what you do with the oscillating EDM is really a firm prediction for the axion, in contrast to many other experiments which look for the axion photon coupling, which might be tuned away by certain models. But if I understand correctly, the oscillating EDM you cannot avoid. It's always there if there's an axion.
Yeah.
Mm-hmm. So it's really the experiment one has to do.
Thank you, yeah.
Very good. More questions?
That was a good final statement, I think.
Yeah.
Don't be shy.
Maybe one question from my side, as was discussed before, this expression of interest, what impact does it have on the experiment itself?
Well, I think at least, we get visibility. I think it was also important to enlarge the community. At the moment, it was really focused at Jülich. Now we have partners like CERN, but that is also due to the particle beyond, BBC, Beyond Collider initiative, but Max Planck Institute Heidelberg is now on board. I think it's important for the community building.
Good. Last question? I don't see, then yeah, thanks again.
Okay.
For the presentation. And we go to the next presentation of an EOI on the electron-ion collider by Daniel Böhr from Groningen.
Thank you. Yeah, so I'm happy to talk about our expression of interest here in this nice room. Also on behalf of Frank Sabatier, who's also here. So this is about the synergies between the electron-ion collider and the Large Hadron Collider experiments. Yeah. So assuming not all of you will be equally familiar with the EIC, I will give an introduction about that and the status, how it was discussed in European strategy, and then I will move on to the expression of interest in our plans, and yeah, in the second part, I will talk about specific synergies, so more the physics, just a number of examples. So the electron-ion collider will be constructed at Brookhaven, and it is well on its path towards realization, but it will still take almost a decade before it starts operating. So it's now in the detector design and collaboration formation phase. And it is a partnership between Brookhaven and Jefferson Lab, and, but it is an international facility with a large EU involvement. Yeah, doesn't go. The center of mass energy is variable, so it will be somewhere between 20 and 140 GeV. So compared to HERA, it is lower energy. But it will have yeah, 3 orders of magnitude higher luminosity. It will collide electrons and protons, but also electrons and nuclei in the whole set up to uranium, and electrons, protons, and also the light nuclei like deuteron and helium-3 and so on will be polarized. Okay. Yeah. So this is a timeline. It is going to be updated, or it has been updated. I haven't seen the recent one, but this sort of, yeah, it will be shifted maybe by a year because of a revised funding plan. But it started with the critical decision level 0, so mission need of Department of Energy. Then it passed the CD1 in 2021, so that was the start of the project execution phase. And now they're working towards CD2, so approval of the preliminary design, and yeah, then there will be approval of the final design, and then construction and transition into operations around 2031. So this means that it will run for about a decade concurrently with the high luminosity LHC that is foreseen to run in up to at least 2040. So that's what we're trying to exploit. So the LHC is basically, well, to a large extent, the gluon collider. And yeah, the EIC has its main objectives to understand gluons better. And it wants to address 3 key questions. So how does the mass of the nucleon arise? How does the spin of the nucleon arise? And what are the emergent properties of a dense system of gluons? And so the physics case was summarized in this white paper. And the detector requirements that follow from this physics case were studied in a year-long process and summarized in this document, the yellow report. It's a 900-page document, and that led then to a call for proposals. And so, of course, yeah, these are they're strong requirements. So you need to know, of course, you have to detect the scattered electron very well to get the X and Q squared identification. Excellent hadron identification, particle tracking, hermeticity, and precise measurement of the luminosity and polarimetry. That is all obvious things. So there were a couple of detector proposals, and these were reviewed recently, and the edge design was recommended as the project detector. So it's a general purpose detector, and at the moment they're now trying to integrate. So there was a similar kind of design, Athena proposal, in trying to optimize and integrate, so to use the nice properties of one in the other. And this process is also at the same time leading to collaboration formation. So that's ongoing at the moment. So in principle, there can be two detectors. So there will be, so here's the project detector will be here, but there's another location that allows for a second interaction region. At the moment, it is foreseen, it's going very slow. Yeah, so it can be, it can be different detector, of course, and then you can exploit complementarity. So of course, if you have two detectors, you can have more statistics, you can have cross-validation, but they can also be, you can also try to accomplish complementarity. So there was a nice discussion by Rick Yoshida in Paris a number of years ago about how that works for the HERA experiment, so H1 and Zeus. So they have similar size uncertainties, but they have differently shaped uncertainties. So if you combine the good parts of one into the other, you get an improved measurement from the other. And so it's very hard in the beginning and before you have the detectors to actually foresee this and try to actually exploit this beforehand. But if the detectors are built one after the other, this may be more feasible. So doesn't seem to be. Yeah, so the DOE will fund one detector, the project detector, but of course the community likes to have two detectors, which is called the off-project detector. And but it is foreseen that there is a large international involvement in both detectors, and hopefully also from Europe. The EIC user group at the moment is more than 1,300 members, and 25% of that comes from Europe. 30% of that is theorists, so we're talking about, say, 250 experimentalists. So that's a big portion. At the moment, EU representative in the steering committee is Daria Sokan. Before her, that was me for 4 years, and that's. So in that role, together with Marco Redici and a number of colleagues, we drafted this input for the European strategy about the synergies between the electron-ion collider and, basically Lhc experiments. And this formed the basis also now of this expression of interest. And so this, from here, this developed. There was other input about the EIC and the European strategy from different countries, and also from NUPEC. There was, so from several sources. And NUPEC also stressed this, the common and mutual interest in the EIC and the particle physics and nuclear physics communities. In the strategy, there was this section about synergies with neighboring fields, and there it was mentioned specifically experiments on the boundary between particle and nuclear physics, and it concluded CERN should continue to coordinate with NUPEC on topics of mutual interest. This then led to installation of the NUPEC ESC task force, which was formed by Dave Ireland, Eugenio Nappi, and Frank Sabatier. And well, together with the chair of NUPEC, we started brainstorming about how we can enhance the activities in Europe about EIC and LHC synergies. And this led to this expression of interest that we proposed in mid-2021. And so even though there are already lots of activities in Europe that cover both EIC physics and LHC physics, so at the moment, for instance, there is the EIS conference here in Spain that covers these topics. There are many workshop series that cover these topics, more specific community, LHC community meetings, heavy ion community meetings. Also Strong 2020 has many work packages that has both EIC and LHC physics in their objectives. So lots of things happening on the overlap. Also recently in the US, there was the SNOWMAS exercise that resulted, among others, in this paper about the electron-ion collider for high-energy physics. So it contains a lot of details of topics of interest for the high-energy physics community that can be done with EIC. So there is some beyond the standard model physics section, tomography of hadron and nuclei, hadrons and nuclei, jets, heavy flavors. So of course these are the standard final state analyzing tools that also are used at the LHC, small x physics, etc. So this was a US exercise that involved a lot of Europeans. So despite all those activities, we thought it is good to have more structured community-wide activities inside Europe. And so that's what the expression of interest tries to achieve. So workshops on the topic of the expression of interest, other community building activities, initiate articles directed to the various communities here to showcase results, etc. And maybe also initiate grant applications and so on. So these are our objectives. So we have a website where you can read the expression of interest. So this is a web address. You're welcome to check it out and hopefully endorse it. If you have more questions, you can ask us. So at the moment, we have 100 plus endorsers. We will have a kickoff meeting at CERN. So we want to have this really as an in-person meeting. So we initially wanted to have it before this meeting so I could report on it, but okay, an in-person meeting, such short notice at CERN was difficult. But now it is possible, so we have room for about 100 people, and we are halfway there at the moment. So this is all in progress. I cannot yet show you the full program, but here you can at least get an idea from some the speakers that we already have confirmed. Okay. No. Yeah. So now about the physics. So this was the expression of interest now about the physics. So there are lots of topics of common interest. I'm not going to go through all of them. I'm going to highlight a bunch. Also partly selected because of my own expertise, because I'm not an expert on all these topics, of course. But just to give you a flavor about the synergies. So the prime example is the part on densities. So if you look, for instance, the gluon density, the uncertainty in the gluon density, essentially. So the green band is the present uncertainty. And with high luminosity LHC in various scenarios, there will be, we will have we will reach a % level accuracy on the gluon density in this range, X range of 10 to the minus 4 to 10 to the minus 1, which is excellent. But the EIC will cover a similar range, maybe a little slightly shifted, but yeah, a lot of overlap. So the high luminosity LHC will reach its precision for protons and for, you will also, of course, know much about the LED PDF. And the EIC will be able to interpolate and do other nuclei, so that you really get, at some point, PDFs as a function of X, Q squared, and A. And now, the regions of interest that we don't know well yet is, of course, small x and large x. So small x, we expect to see onset of saturation, particle saturation effects due to nonlinear QCD. And here, of course, the electron-proton and electron-ion forms a baseline for PP, PA, and AA collisions. So that will come back a few times. So I mentioned already, so the nuclear PDFs are of interest. So if you compare the lead one to the proton one, there's expected to be quite some differences. But as you can see, there's quite some uncertainty there. So this needs to be pinned down better. And the EIC will do EA collisions in a much wider range, kinematic range, than the current existing fixed target data. So so small x nuclei, but also large x nuclei the PDFs are very interesting, and because they form so the initial conditions for the heavy ion collisions at the LHC. So for the core gluon plasma formation. PDFs at large X are also interesting, not just for nuclei, but also just for the proton. For instance, for beyond the standard model physics searches. Yeah, so as I said, LHC, so if you make the Higgs, for instance, you do glue to Higgs. That has an X fraction of about 10 to the minus 2. So that is the well-measured range. Thanks to that, you can really compare it with the Higgs, with the standard model prediction. If you didn't know the gluon distribution well, you couldn't, you can conclude there is a particle. You see a bump, but you don't know if the bump is well described. So if you want to produce heavier scalar particles, for instance, you need to go to, you need to know a higher X gluon distribution where the uncertainties are quite large at the moment. Of course, it's not only for gluons, but also for quarks. You need to know the PDFs, and the EIC will mostly improve actually the PDFs at large X. So this was another NN-PDF study. So large X will also be studied at the LHC in fixed target experiments. So there's another opportunity to compare the results and do a kind of global analysis. With nuclei, there are other objectives. So you so jet propagation through media, and so the evolution really you try to from the EIC you get information from the initial stages, and try to see if you can understand get a better understanding of, say the glasma or the strongly coupled core gluon plasma, the whole process in heavy ion collisions. But there are also interest in using heavy ion collisions at the LHC, but in ultra-peripheral collisions, where you start to really, where you start to probe photons, and collisions with the photons from the nuclei. I come back to that in a couple of slides. No. Yeah, so I talked about the PDFs, which are really sort of one-dimensional distributions. But currently there's a lot of interest in multidimensional parton distributions, like the transverse momentum dependent distributions. So you have really now a three-dimensional momentum distribution of particles. And there are lots of studies foreseen at the EIC about these distributions, especially for spin-dependent ones and for gluons again. Yeah, so it's interesting that, for instance, inside an unpolarized proton, you can have polarized gluons, and that will have then consequences, will lead to sort of azimuthal asymmetries. You want to compare those in PP scattering with EP scattering as well. Well, let me not go through all these objectives for TMDs. But what is really the point is that you want to describe the whole PT spectrum, and especially at low PT, the transverse momentum dependent distributions are relevant. And I just want to give one example. No. It's a bit, yeah. So this is an example, this may be, yeah, it seems very relevant. That is, so if you do semi-inclusive DIS at the EIC, you can probe the flavor structure. 5 minutes, okay. You can probe the flavor dependence in these transverse momentum distributions. And that affects, for instance, the determination of the W mass from the PT spectrum. So this is, of course, now highly relevant because there was this measurement of W boson mass, which was not from the Tevatron. That was 7 sigma away from the other determinations. So they have, of course, estimated some uncertainty because of the parton densities. And there's resummation in there, which also has some non-perturbative input. But they did not include, for instance, that there is flavor dependence in that. And so there was this study, a group from Pavia, that this can really be, several MeVs different. So I'm not claiming here that this will explain the discrepancy. But these things could be investigated very specifically using the EIC. Yeah, they can very nicely probe this flavor dependence of this transverse momentum dependence, which will go into this type of W mass determinations. So there are many other distributions. I will mention a few. So there's a generalized parton densities that gives you not the momentum distribution, but really the spatial distribution. So where are the partons inside the proton and the nuclei? So again, this gives you a baseline for things you see in PP. Let me just skip this in view of time. Yeah. Just, no, I skipped something now. Now I don't know if this was a slide before or after. Sorry, but anyway, so there are, this was, okay, it doesn't want to show the one I want to show. Of course, nowadays, so things get more and more precise. So of course, the PDFs are known very precisely in certain X range. The TMDs, the transverse momentum dependent distributions and the spatial distributions get known better, but you can even have what is called the GTMDs, where you both have, you have the combined distribution, and there can be new correlations between the transverse momentum and the spatial distribution. And before this, people thought this was too difficult to measure, but there are actually nice opportunities at the EIC to measure these GTMDs. For instance, in diffractive dijet production. And at the LHC, you can do, for instance, double parton scattering. You also probe similar GTMDs. In diffraction, go back to this slide, actually it's known for a long time that there is kind of factorization breaking. If you go from HERA to PP, so you have if you describe it with diffractive PDFs, there is factorization breaking, but also inclusive dijet. If you probe the transverse momentum dependence, there is also an expectation that there's factorization breaking. And this is something that needs to be understood. And so these are one of the most simple processes you can think of. So EP to digest or PP to digest, and it would be a pity if we cannot, if we have to dismiss those data because we don't understand the non-factorization there. So that is also a topic of investigation. So as I mentioned, UPCs are very a good topic for synergy because so this heavy nuclei, if you scatter them peripherally, you probe the photon field from the electric charge, and so you can compare that to photon production, for instance, at the EIC. If you do that really peripherally, you have photons from both sides if you do two heavy ions, and the STAR collaboration has looked you get here photon scattering. You produce E plus E minus pair, and that is turns out to be has azimuthal modulations in there due to linear polarization of photons, and so that is from QED. You can calculate that. It actually fits nicely. Data fits nicely the QED expectation, which is here the blue line. And you can do the QCD analog of this, the linear depolarized gluons, and making, azimuthal modulations of muons, for instance, muon pairs, for instance, or dijets for that matter. Okay. Then, so that is all about parton distributions, and so let me also mention there's electroweak physics and beyond the standard model physics. It can be done at the EIC and obviously at the LHC. So one is, for instance, this theta W. Here is from the edge projection. So here will be data. So there's low energy data, JLab, etc. And there's high energy data on the Z mass, Z pole, and the EIC will put data in between. I will try to wrap up. On EP and E deuteron, it will give further constraints on lepton flavor violating processes, or electron to tau, so improve on HERA measurements of that. And it complements the limits on that people got from tau decays, from B factories, and lepton flavor violation studies at the LHC. Also, and there's a poster about this also, so the tensor charge measurements that you can do with the EIC can help to limit bound tensor interactions at the TeV scale. So there, well, if you want to know more about this, I refer you to the SNOWMASS article. There's a whole chapter about this. Yeah, so we also would like to investigate synergies with astroparticle physics. One thing to mention, of course, several cross-sections for this, charm cross-sections, neutrino cross-sections, and explore what the EIC can add to this knowledge. At the moment, of course, if you have neutrino nucleus cross-sections, the nuclear PDFs form the dominant theory error there. So this can be improved by knowing better the nuclear PDFs. Also, cross-sections at energies above the collider, above the LHC energies will be interesting to exploit. For one example for that is, for instance, Odoron physics. So at the EIC, you can do certain Odoron physics with polarized beams and try to relate that to the Odoron physics that is it becomes apparent in the total cross-section, PP cross-section at very high energies. Okay, there's of course synergies with on detector R&D for both the Lhc and the EIC. Yeah, let me, in view of time, skip over that. For details, please ask Frank. We do not intend to duplicate certain activities that are already there, but we will, yeah, it is part of our expression of interest. To end, I want to show the posters. No, doesn't want to do it. Oh. So we have 4 posters. Please check them out. Yeah, so there some titles are different from the program, but okay, that is not so important. My last slide. If it wants to show it. Yeah, is what we want to do next. So we want to advertise more broadly our expression of interest, of course, and ask more colleagues to endorse it and be part of our activities. Primarily, first our kickoff meeting at CERN in June, and so please check it out and join if you are interested. And I thank you for your attention.
Thank you. Time is very short. There is time for one urgent question, if there is. Singular question, if there is.
Can you say something about polarized parton distribution, gluon, quark?
Yeah, I could say a lot, but that is, of course, less of an overlap with the Lhc. So,
okay.
So we yeah, do not focus so much on that. But of course, it is a unique possibility, and that is what exploited in the beyond the standard model part.
Okay.
Most of the time. So you can, with the polarized beams, if you do a standard model effective field theory analysis for the polarized observables, you get different constraints than from the unpolarized ones. So there is, well, yeah, there are many more examples, but for the PDFs, there's not much overlap.
Okay, we have to stop here. Thank you again for your presentation. And the last talk today will be by Vitek Krasny about the Gamma Factory, please.
So first I would like to thank the organizers for giving me the chance of presenting the expression of interest, which we sent 2 years ago. And it is a kind of nice coincidence that you see my talk is coming after the EIC talk, because it reminds me the CSIC meeting which was 25 years ago, in which the EIC was presented for the first time as the project for Europe, as a joint project by GSI and DESE, and it was presented by me. And this project, you see, didn't get much support in Europe. It had to be exported to US, and as you see now, out of all the projects that we discussed at that time, which was the question of constructing Tesla, ENC, Elphi, you see, this is the only project that survived over this 25 years. So it is a nice coincidence that my talk comes after this talk. So in some sense, Gamma Factory is similar in terms of a project which I consider inevitable. So this is why I put, you see, on top of on the side of the logo of the Gamma Factory, the picture from Myanmar. It's just to tell you to which extent I consider this project as something that will have to be done at some period of time. So the proposal of the Gamma Factory was formulated 6 years ago, and by now there is something like 100 physicists from 40 institutions that contributed to the Gamma Factory studies. And so far, the Gamma Factory studies were anchored and supported by the CERN Physics Beyond Collider framework. I give you this, our site, our internet site, if you would be interested, you see, in knowing what kind of activity we have been doing for the last 5 years. From the practical point of view, Gamma Factory is actually the project which proposes another use of existing infrastructure that we have at CERN. On top of the present Lhc beams, which are protons and fully stripped ions, we would like to add atomic beams. Atomic beams are those beams in which you see you do not strip all the electrons from the ion, but you keep typically 1 or 2 electrons on the shell. And you see, if you store those beams in the SPS or the Lhc, then first of all, you can consider those storage rings as atomic traps. And as I will show you, a very special atomic traps, which otherwise you cannot construct because they could be manipulated with ordinary lasers. If you interact atoms, which are in these traps, with laser light, then you can produce very high intensity photon beams. I will explain you how you do it. And having such a beams, you can send them on external targets and produce secondary beams. So the project of Gamma Factory is actually to use the existing infrastructure, but extend its use to storing atomic beams and connecting them with laser pulses. And I'm talking not of the specialized lasers, like, for example, Marek was showing for Eli project, but the commercial lasers that you can just buy and implement. The Gamma Factory project is not about, at this stage of the program, which is predefined, but it is about making totally new tools of very high quality. And I will mention 6 tools and explain 2 of them, because I do not have time to go to the details. So first of all, Gamma Factory would provide atomic traps of highly charged cold atoms. In some sense, we would extend all the domain of the physics that, for example, led to establishing, for example, of Bose-Einstein condensate to the domain of accelerator physics. We would form the high-intensity photon beams. Gamma Factor would provide new laser light-based cooling methods for high-energy hadronic beams. This is very important because this is the only method of cooling beams of hadrons that becomes more and more effective if you go to higher and higher energy. And this is contrary to what we know at the moment for cooling of hadronic beams. Having high-intensity photon beams, we can create high-intensity beams of polarized electrons, polarized positrons, muons, neutrinos, neutrons, and radioactive ions. And for all these sources, we expect the gain in terms of intensity of at least 2 to 4 orders of magnitude. And say, for example, the lepton beams we can produce with very small emittance. For the Lhc program, we can deliver to the Lhc collision points electron beam. And also, our cooling methods could help in making more efficient plasma wave field acceleration, which are driven by the beams, which are modulated by our cooling methods. I will concentrate on 2 of them. I cannot explain. If you would have questions, then I will say more on other things. So the miracle of the high-intensity gamma beams is very simple. If you have inverse Compton scattering methods in your mind, then you basically should see this picture as exchanging, you see, the targets for the collision of laser photons from electrons to atoms, and think for the moment of the lead atom that has large Z and have 1 leftover electron. So if you shine the light, which is precisely to the resonant excitation you see in between the electron, which stays on n equal 1 to n equal 2, it jumps, and it will stay on the excited level for a small fraction of the time, and then it will come back to the ground state. Now, first of all, you notice that contrary to the inverse Compton scattering, you have the process which has gigabarn cross-section and not barn cross-section. So that means that you can produce very large number of photons. So the second point is that basically, if you swallow a photon, first of all, the photon will be seen in the rest frame of the ion as the photon which would have the wavelength shortened by 2 gamma, which is the Doppler effect. And then, if those photons are limited in the direction of the ion, you get another 2 gamma gain in terms of energy. So you can conceive LHC beams as the stable frequency converters of the photons. This is the way how you produce out of EeV photons the tens of hundreds of MeV of photons because of large factor gamma of the beam. Yeah. The gamma factory beams will have extraordinary properties. They are point-like because the excitation time is very short. You see, for the lead-like atoms, it's at the distance of 0.1, 0.2 millimeters. So it's very similar to inverse Compton scattering. But you see, there will be a huge jump in intensity of at least 6 to 8 orders of magnitude with respect to the inverse Compton scattering sources. There will be very wide range of tunable energy photons between 10 keV, which extend by factor 1,000 the energy range of free electron laser photon sources while preserving the same intensity or even increasing the intensity of free electron lasers. The last development that we made was, you see, to control the polarization of these photons. And we found the tricks how you can actually make polarized photons and also twisted photons, you see, if you wish. At the moment, everyone is talking about the energy. So I would like to recall here that the LHC RF power, since those beams are stable, you see, just put the beam, they circulate, and then you pump as much energy in terms of outgoing photons as you put into the RF power of your storage ring. So if you consider the plug power efficiency of the gamma factory, you see, beam of photons, it is 300 times better with respect to, for example, DESI XFEL. And this is assuming the power consumption of 200 megawatt at CERN and 19 megawatt of DESI. So in terms of number of, you see, the energy in the secondary beam, this is a very nice problem. This is the trick how you make, you see, polarized photons. You basically take the polarized laser light, and then you use Pauli principle, which forces the electron to jump exactly to the same spin state in the final state. I will not go into the details, but we can achieve the transmission of the polarization of initial visible photons to gamma rays of 99%. This is the, you see, the simulation of something that is very important for many branches of physics. Very recently, you see, this question of the cooling got quite an attention for people that are looking for the usage of large-scale accelerators for the gravitational wave surge. Normally, if you would like to maximize the number of photons that you produce, if you are interested in the photon beams, you basically shine the light within the full bandwidth spectrum of the Doppler enlarged spectrum of the ions. And you shine the light in such a way that you overlap, you see, with the laser spot, the transverse side of your ions. The beauty of laser systems is that you can now shine the light, which is only on the fraction of the band in the transverse space, and you can shine the light on the fraction of the frequencies, you see, and then you can transmit to high-energy accelerators all that people have learned by, for example, making Bose-Einstein condensates in terms of how you basically effectively cool the bunches of particles which move in some way. So this animation that you see shows you what happens if you just take a half of the band, of the frequency band. And this is, for example, how you can form the beams which have much smaller spread, you see, in terms of z distance, you see, the length of the bunches. Below, you have the animation of how you can actually, and how quickly you can dump Betatron oscillation with our methods. And on the right side, you see that it is not only the question of Betatron oscillation, but if you actually shine the beams in the dispersive region of your machine, you can reduce transverse emittances of your beams very considerably, and this is, for example, the simulation for a lithium-like calcium, in which you see that you can reduce the emittance of the beam by factor 10 very quickly. I took this example because Paris was discussed yesterday, the measurement of MW at Fermilab. And I would just point you to the fact that there are two ways of increasing the luminosity of LHC. There is the one which is being done at the moment, and this is rebuilding of the IP geometry, but there is also a second one in which you reduce the emittance of the beam, because if you look at the luminosity formula, you see the emittances and the beta stars enter in the same way. So there is a concrete proposal. You see how you could use, for example, calcium beam, which would be accelerated to SPS, laser cooled at the SPS, then you strip the electrons, and before injecting those fishes into the LHC, and then you can collide in the LHC the bunches of calcium of similar partonic luminosity, like those of the proton-proton collisions. So this is the only way you see. In some sense, if you do it with isoscalar beams, you preserve something what was very important for Fermilab in terms of precision measurements of MW. Instead of preserving CP like in the Fermilab, you preserve isospin symmetry by having the same number of neutrons and playing with the U and D, you see, multiplied of the weak isospin. So for me, this is the only chance if LHC would ever come to the precision of Fermilab in terms of measurement of sin squared theta or MW, it will have to do with this kind of isoscalar beams. But also we would have the access to exclusive physics production in photon-photon collision, and technically we could run it with lower pileup background. And it is just one of the many applications of what you could do with laser-cooled beams in the LHC and in the SPS. I'm coming to the second part of this. All these ideas are nice, but the question how you come out of these ideas with the technical proof that such a scheme is actually feasible at CERN. The first point, and this was the subject of our dedicated runs in the SPS and LHC over 3 years, was to learn how to make atomic beams, how to accelerate them in all the LHC infrastructure, including LHC. And this effort was culminated with the fact that we were able actually to bring hydrogen-like lead through all the system and inject it to the LHC. And we have proven that we can keep the hydrogen-like lead in the LHC for at least 50 hours. That means that we are proving the fact that we can store those beams and use them, you see, in the passive way for all kinds of things that you would like to use. Of course, this didn't prove that we can accelerate, you see, the full intensity beams of the hydrogen-like lead. So we made the studies which were published in this physics review paper, in which we analyzed the way of how you could collimate those beams. And of course, collimation of such a beam is a totally different issue with respect to collimation of ion beam or proton beam. So we had to find out, you see, the way of circumventing some problems, for example, with suppression collimator. We are still planning, you see, the possibility of, collimating those beams with crystal collimation, and we are developing totally new methods of collimation of the beams of atomic beams in terms of laser collimation. Oops. Once you have the ions in the LHC and in the SPS, and you have proven that you can keep those beams, the question is how you implement the laser system. I recall that we are talking of the collision of the ions with the photons which have gigabarn cross-section. So to achieve such a jump of intensities of 7 orders of magnitude with respect to what has been done so far, we need something like 10 to the 16 photon per bunch at 40 or more likely 20 megahertz. So that means that we would like to operate 5 millijoule pulses of the laser at 40 megahertz. And this is more or less the 200 kilowatt photon beam. Of course, we do not have the laser that could provide such a power, but we can stack those photons into Fabry-Perot cavity. And this is, you see, the published plot, which tells you that for 200 kilowatt of the stacked power, we basically need the input power from the laser of the order of 20 watts. And those are commercially available lasers. We are not talking of any specific, you see, development on the laser side. So in some sense, we have in our hands the ions in the Lhc complex. We have the laser that we can use. And the only thing that we have to prove is that we can successfully incorporate such a Fabry-Perot cavity into the existing storage ring of the at CERN. And this is the subject of the gamma factory proof of principle SPS experiment, which we proposed 3 years ago. You can recognize CERN site. You see this is just the main gate, and this is the region of Atlas. And there is a place in which in the old days there was the extraction line to lab, in which there is an empty space in which we can put this Fabry-Perot cavity, which is the stacking, you see, way of getting photons, you see, on the way in the SPS to the ions. And you see, we would like to have this cavity of the length of 3.75 meters, which corresponds to 40 megahertz operation. This is the technical picture, how this would, how this implementation would look like. And this is, you see, the picture how we would like to control the photon flux. This is the technical drawing of the transfer line of the laser, you see, with the laser room, which is in this gallery, which was previously, you see, the access to the lab tunnel. So what is the purpose of this Lhc, of this proof of principle experiment? Fabry-Perot cavities of similar power have been already implemented, as I was showing on the previous picture, at KEK and HERA. So there's absolutely no problem in terms of implementing them. The only new thing, and this is really new thing that comes here for the first time, is that you would like to implement it into the environment of hadronic storage rings, which have larger radiation level. So we would like to demonstrate that an adequate laser system can be remotely operated in the high radiation field of the SPS. Once we do it, the radiation field in the LHC is, due to the better collimation, you see, of the beams at the LHC, much better with respect to those of the SPS. So we test it in the more harsh environment. We would like to demonstrate that the very high rate of photons are produced, that almost all the partially stripped ions, these atoms, are excited in single collision of the PSC bunch with the laser pulse. And you see, if we achieve this, we are talking at the SPS of lithium-like beams, for which we are using the lamp shift type of transition, which is extremely narrow. Once we go to the transitions in the LHC, in which the gamma factor is larger, we can go to hydrogen or helium-like, you see, atoms. And the cross-section is, you see, it is much easier to excite those. So in some sense, if we can prove that we can, you see, excite with 20 megahertz all the atoms on single pass of the, then we can actually be sure that we will get all the intensities of the photons that I was talking before. And of course, what is very important that we should demonstrate the stable and repeatable operation, because we would like to see, once you close the SPS, you will not have access to this laser system. So you have to be sure that you can operate the laser remotely. And we would like to demonstrate the ion beam cooling, both longitudinal and transverse cooling, and do some atomic physics measurements. The estimated cost of this proof of principle experiment is 2.5 mega Swiss franc. This is what we miss at the moment. Otherwise, everything is ready to do this experiment. I was asked by the organizers to say a little bit what we are doing at the moment. What are our preparations for this? So I should hurry up. So at the moment, you see, over the last shutdown, we were able to implement the specially designed stripper, you see, for the ions. Half of it is already equipped, and the second half will be equipped next year. You see, this is basically, by the way, our understanding, which came from our dedicated runs, how we would strip, you see, any ion to any charge state. So we know how to do it, you see, but we have to do it technically. So we'll have insertable foils that we would do it. Last week, we published the note in which we go to a spatial runs at the SPS to find out to which precision we can steer the beam. We need to have the precision of the steering of the beam in the transverse plane to something like 1 microns, and we have to tune also the frequency. So we demonstrated that we could do it with satisfactory precision. For the laser system, we have verified the industrial providers of the laser system that we can get the laser which would have sufficiently low phase noise measurement such that we can couple such a laser to the fabric cavity. And also, you see, there was a very dedicated study, you see, how we could avoid all kinds of parasitic resonant mode in such a cavity, like Laguerre modes or, for example, Hermite modes. And this was demonstrated that we can actually choose the windows, the radius of curvature of the radius that we can both follow exactly the spot size of our ion beam in the SPS, and then we can avoid all the resonant modes. So the letter of intent was submitted 3 years ago. It was the first reaction from SPS came 1 year after. And since then, we have actually prepared this experiment to be run. So I would just concentrate on this point that you see full experimental specification has been finalized. The target installation is LS3. What we only need is to find 2.5 megas Swiss franc to cover the cost of experiment and to assure what is probably more important, the requisite CERN FTE resources in terms of infrastructure that this experiment needs. When I am talking about infrastructure, this is the question of you see how we implement it into the vacuum, you see the question of impedance of the beam, cabling, you see the rooms for the lasers, and this kind of support that if we don't have from CERN, then we would better stop, you see, this activity now. Over the last, since we submitted, you see, this expression of interest, there is a lot of activity in terms of many groups trying to, you see, find out all kinds of applications of the gamma factory. So for you, I have just printed, you see, the access to the last 20 papers, you see, which look at the application of the gamma factory to various branches of science. And the strengths, but also the weakness of the gamma factory. The strength is that, you see, eventually, if constructed, many physics communities would profit from that. But the weakness is that at the approval phase, it's very difficult to somehow put this project to the stage in which people would consider it as worth doing. So I would not go into the details, you see. The application range from particle physics, nuclear physics, astrophysics, fundamental physics, atomic physics, accelerator physics, atomic physics, and applied physics. For those that would like to know, I will finalize in 2 minutes. There was a special brainstorming session, you see, 1 month ago, in which I was presenting one aspect of the gamma factor, which is how this is embedded and how it is competitive to, for example, high-energy frontier research in high-energy physics, but also in nuclear and astrophysics. So I'm just flashing this. I have 4 examples that I will probably go just very quickly. For example, for particle physics, I have chosen the example of a new method of forming high-intensity polarized muon beams of extremely low emittance, which is one of the applications that many accelerator physicists, but also high-energy physics physicists would like. This source has the property that you see, first of all, contrary to the proton-driven sources of muons, it gives the symmetricity between mu plus and mu minus, and it gives you the intensity, which is something like almost 3 orders of magnitude larger with respect to what we have at the moment. This is the plot which shows our potential in terms of finding weakly coupled particles. So this is the rejection limit of the gamma factor for axion-like particles and for the dark photons. This I will skip. We can do all the atomic physics with muonium atoms, pionic atoms, all kinds of things that you see atomic physicists would like to do, and also they would like to investigate highly charged atoms, you see, in terms of electroweak physics. This is my last example, and I was prompted to this to show this example not only because there was a recent Nature paper on this subject, but because the subject of the energy is very, very important. To me, it is highly inconceivable that in the present world, for example, if you construct FCC or, for example, CLIC, or even muon collider, we can still buy the energy of you see, of the plug power of 300 megawatts for those machines, and it is probably the high time to think how you could produce 300 megawatts, you see, in your lab. And gamma factory, actually with 10 megawatt beams, could be used, and it was used in this study of the accelerator driven system, which is based on subcritical reactor, in which you can transmute most of the nuclear waste. Conclusions. So we are at the stage that you see we did as much as we can in terms of enthusiasm of 100 people that are working on this project, and with the support of the PBC type, which provides a forum of presentation. In order to progress, we now have to have 2 things. The first is to finance 2.5 million Swiss francs to construct proof of principle experiment. The second is the support of the national funding agencies, you see, in terms of support for the groups that are participating in this project. The most important probably is the CERN, you see, involvement in this project. I am in the BE department now, and I know that CERN is busy with lots of different projects. There is a multiplicity of different projects. So at certain moments, CERN has to decide which project to support, because each project of this type requires a support from CERN. And you see, if this support is given, I can only tell you that, you see, this project has a very nice potential place in the future CERN research program, because the next high energy frontier, if ever constructed, may take a long time to be approved, built, and become operational, and it's unlikely to happen before 2050. So the present research program, as Paris was showing, you see, on his transparency, will probably by the late 30s will achieve, you see, the discovery saturation. So at that moment, a strong need which arises, you see, for a novel multidisciplinary program which could reuse or co-use the existing CERN facilities, including LHC, in ways at levels that were not necessarily thought of when the machine was designed by the broad scientific community. And the gamma factor, as I hope I was able to explain you over this 20 minutes, could do it. I just make one citation which you may find, you see. Yeah, you see. So there's the question of, you see, during the construction of a standard model that I was participating, it was most of the new projects were driven by the concept. You see, you wanted to find big works or Higgs or anything. Now we are coming to the stage in the example is almost completed. We don't know where to go. So I would like to make the citation of what Dyson said, that new directions in science are launched by new tools much more often than by new concepts. The effect of the concept-driven revolution is to explain all things in new way. The effect of tool-driven evolution is to discover new things that will have to be explained. So it is in that sense that Gamma Factory goal is predominantly to make new tools. So this is the end of my talk. Thank you. Sorry for being getting late.
Yeah, thank you for this presentation.
You can keep this transparency, you see. If
Again, we are very short of time, so at most one very urgent question to this talk.
Marek.
You take the proof of principle experiment, required, as you said, 2.5 million Swiss francs. But I guess the implementation at Lhc will be much more expensive. And the second question is it possible to run in parallel two things, Lhc, high luminosity, at that time, and also Gamma Factory, and to which extent you can really share the time?
There's only one aspect that you can share, and those are the aspects in which you cool the beams in the SPS and inject, you see, the cold beam of fully stripped electrons. You cannot run and collide those beams. So for the running of the Gamma Factory, if you have two beams counter-circulating, you have to make the bypasses such that those beams do not see each other. Why? Because the other beam colliding with the beam which carries one electron would strip this electron. So in that sense, it cannot run in parallel. So that's why I consider this project as post-high luminosity LHC project rather than, you see, the project at the time of the LHC.
Okay, thank you. For time reasons, we have to stop here. Thank you again for this presentation. Thank all the speakers of the session. I just want to make one comment that if you are more interested in these EOIs, 5 of them have been published in Nuclear Physics News, the NUPEC journal. And there is also a website. On the NUPEC website, you can find some more information. And the last thing is Maria.
I have a practical information for you. We are numerous. So there is a canteen you explored yesterday, it's just below us, but there is another canteen not far away. You have to cross the street, Serrano, come out of the campus and cross the street. So if anyone wants to explore that one, we will guide you how to reach that second one, so the queue is not so long. If you prefer to talk a bit and then unqueue in talking, while talking, then it's no problem, and you have still this canteen here. The tickets you got are, of course, valid in both canteens, so it's no problem. Okay? Thank you. The same food, I believe.
Okay. I think it's time to start the first afternoon session. This session is dedicated to knowledge transfer, and it will be in two parts. There will be first a presentation by Benjamin Frisch, and then there will be a roundtable where the intention is to have a strong interaction also with the audience, so be prepared. But first, I call Benjamin for his presentation. So Benjamin comes from the Knowledge Transfer Department of CERN, and he will talk about knowledge transfer and best practices.
Exactly. Thank you for the introduction. So I have the first 20 minutes to give you an overview of knowledge transfer. It obviously has a strong CERN perspective, but I think that many of the examples and many of the lessons that I'll try to explain are actually applicable to all our community when it comes to organizing knowledge transfer projects. And maybe as a disclaimer, I'd first like to thank everybody who contributed material for this presentation. As you can guess, time's too short to present all of it, otherwise I'd be giving a semester lecture here about knowledge transfer. And also I had to be selective in what I show. I realized that I do not talk about our work on radioisotopes for biomedical and medical research, the MEDICIS and PRISMA projects that were already mentioned. So I also apologize for not talking about that. But let us dive into knowledge transfer. And I suppose that all of you know what we're showing here. Accelerator, the experiments, and the data center. But I'd like you to look at them from the eyes of a knowledge transfer officer. Because actually, if you do that, you will realize that CERN, that particle physics, astroparticle physics, nuclear physics research organizations, they are treasure troves of know-how and technologies. When you look at that, you see know-how in superconductors, cryogenics, vacuum technologies, detector technologies, data acquisition, data storage, data analysis, obviously, and many other fields that all can find applications, that all can find societal applications, that can all find, that can all be used as solutions towards very concrete societal challenges and societal needs. And that is what explains the mission of the knowledge transfer groups in our organizations. First, there is a need to maximize the technology and knowledge return to society. And as CERN being the intergovernmental organization that we are, that obviously implies working in priority with institutions in the member states, obviously with academic partners, but also with member state industry. But beyond that, there's also the mission of promoting our community as centers of excellence for technology and innovation, as places that generate knowledge that can have a very direct, very short, very quick application, again, to solve societal needs. And then there is the broader, well, there's the broader political goal, which is that it helps demonstrating to our funding agencies, to our governments, the importance of investing into fundamental research, the importance and the impact that that can have. And that is actually recognized in the European Strategy for Particle Physics when it says, I think it's in the last chapter, when it says that particle physics research centers should promote knowledge and technology transfer and support their researchers enabling it. That is a very important point, supporting the researchers enabling knowledge transfer projects. And that the particle physics community, and I think that the same goes also for nuclear physics, for astroparticle physics, that our communities should engage with industry to facilitate knowledge transfer and technological development. Now, we've proven over the past decades that we can have an impact, that we do have an impact, and there are some areas which tend to be rather known to you. I'll show some examples. Clearly, I see that part of this slide is missing. Well, it doesn't matter. Part of the slide is missing, but anyways, which is the healthcare applications, which is aerospace applications, cultural heritage. And then there are two new areas that I'd like to highlight. One is environmental applications, and the other one is quantum technologies, which are two areas that, at least from a CERN perspective, have gained in importance over the past 1 to 2 years. The environmental aspects, they were already highlighted in previous talks yesterday afternoon and this morning. It is increasingly important to reduce our research's environmental footprint. But you could also turn it around and start thinking about what can we do to help society have a reduced environmental footprint. And that is exactly what we are going to do through the CERN Innovation Program for Environmental Applications, where we motivate our scientists, our engineers, to come forward with technologies that were developed for CERN's purposes, for particle physics purposes, and start thinking about how these could actually be applied from an environmental point of view. And the other one that I mentioned is quantum technologies. So obviously, quantum technologies, from our perspective, we are interested in understanding what quantum can actually do for us. Think about using quantum computing for data analysis. But again, you could also turn it around and start asking, what can we do for quantum technologies? What can we do for the development of quantum computers, quantum detectors, quantum communications, quantum simulations? And both of these aspects are actually summarized within the Quantum Technology Initiative at CERN and its strategy and roadmap. And as a side note, if you haven't read it, it's actually a very well-written document. It makes for a very good read to understand the importance of quantum for us, but also our importance for quantum. And again, from a knowledge transfer perspective, that's the right part of that slide. We do have very precise technologies that would make sense to cite just one. Think about superconducting coatings for radio frequency cavities. We need them for our accelerators. We want to develop them for our accelerator chain, for physics beyond collider activities. But at the same time, you need exactly the same approach to stabilize superconducting qubits in order to create more performant quantum computers. How do we do knowledge transfer? I mean, these are basically the broad tools that I think any knowledge transfer team, group, or organization are going to use. And I'll first stay with the lower part, because it really starts first with supporting our personnel. And that support is first and foremost an explanation and some help about what it is to do tech transfer. Help with legal questions, business questions, IP management, deciding what's the best way to disseminate our developments. Should we follow the open source strategy that CERN endeavors very much, or should we actually go maybe for a different IP strategy? It is providing help for entrepreneurial activities. And then it's obviously also making sure that seed funding exists and that collaborations happen. Let me say a few words about seed funding. Seed funding is paramount to make our know-how, our technologies interesting for, I'd say, the outside world, for societal applications. In many cases, our technologies, obviously, they are at the right development level that we need them for our purposes. But in some cases, you just miss a little bit, a notch higher, to make it interesting for particular industry. And in that case, all you need in many cases is to support a PhD student or a fellow for 1 or 2 years and a little bit of material money, which at CERN traditionally is provided through the KT fund, which is a clear fund for technology developments with a clear market case, a business case, the medical applications budget, which is a budget for a bit more early stage research-oriented developments with a clear healthcare application, and then a new addition to these funding mechanisms, the Impact Fund, which was set up by the Knowledge Transfer Group with the CERN and Society Foundation to develop technologies that address SDG-related challenges. The SDGs, the Societal Development Goals, such as they've been defined by the United Nations. And the idea here is to transfer technologies from the high energy physics area with external donations to solve exactly what it says, a certain number of societal challenges. Having technology and know-how ready is a good step forward, but then you need to establish the right framework. And that goes, in the best case, through collaborative R&D, setting up co-development agreements, in some cases also with industrial partners, where you develop a technology which you want to develop for your own purposes, but it is also very helpful to solve a societal need, an industrial need. In that case, you can really join forces and both help your own development, but also show that you have a really immediate impact on industry. Think about the superconducting coatings for RF cavities that I mentioned before. You can have, of course, licenses, technologies which are ready to license. You might use additional training for licensed technologies. You could also use support open source technologies. In many cases, just making a technology open source is not enough for it to be successful, because in many cases you need your original developer to actually explain how that open source technology actually works. And then we have huge research infrastructures. At CERN we have the beamlines. These beamlines can be used for prototyping, benchmarking, or testing purposes, in a sense as a service. A few more things that you could actually do that we've been doing, in some cases simple consultancy, providing a second opinion on a tech challenge. Organizing a hackathon, or what we call challenge-based innovation, where you mix CERN experts, universities, engineers from companies to solve broader issues or very specific issues. Or also facilitating knowledge exchange by having an external partner, a company, sponsoring a PhD student or a fellow that will work within our organization, that will work for us, but of course on a technology where we know that it might also be interesting for industry. That in the end brings you to these 4 standard kinds of structuring research. of structuring knowledge transfer collaborations. I'm showing them again to show in the end the 4 ways that we usually use. Now I'll jump to some very concrete examples, and I chose examples that ideally imply partners that will be part of this roundtable discussion. And I'd like to start with a detector technology, the Medipix chip. So the Medipix collaboration originally founded to produce chips used in CERN's experiments. But that chip is also licensed to many different companies, one of them being the company Advacam from where Carlos works, that uses the Medipix and Timepix families of chips to make products that can be used in the fields of material analysis, imaging, or education. And there is even one of these detectors flying on the ISS, was actually 7 of them on the ISS right now. These detectors are used by the United States NASA. They're going to be used by the European Space Agency. To give you an idea, well, now we could, when I show this to students, I always let them play the game, where's the detector? For the sake of time, you see here 3 blue handles. The rightmost handle has a blue cable going to something which looks like a very small USB stick. That's the Timepics detector that's been used. And that detector is a lot more resolving, faster, and obviously a lot smaller than any of the traditional space radiation monitoring systems that were used on the ISS up to now. Let's come back to Earth, InsightArt. That is a spin-off of the company Advacam, and they use a Medipix detector for cultural goods analysis. What you see on the right is the robot that's holding, I believe, the X-ray source, which would imply the detector is on the other side. It could be the other way around. I'm looking at Carlos. Do you remember where the detector is? On our side or behind it? Okay, so the detector is behind it and the X-ray source is on our side. It allows you to do, to analyze the composition of works of art. And what you see here on the left is a painting by Raphael that could be authenticated a few months ago, last year to be more precise, that could be authenticated thanks to the material analysis allowed by InsightArt. And to show a last example related to Medipix, there's a New Zealand-based startup, Mars Bioimaging, that uses exactly the same chip to provide color X-ray CT. So a standard X-ray CT gives you black and white information about the anatomy, and they provide on top of that information about the tissue composition, thanks to that chip. Moving away from the detectors, let me talk a little bit about accelerators. And I can't give a presentation about CERN knowledge transfer without talking about radiotherapy. I need to mention our involvement in the development of proton therapy and hadron therapy. It started back in the 90s with the proton ion medical machine study, PIMS. Then, together with the Terra Foundation, with the Italian INFN, the technologies were brought to the level that 2 hadron therapy centers in Europe could be installed, now in Italy, Mid-Austria, and Austria. But we didn't pull out of these developments. CERN is now a partner of NIMS, the New Ion Medical Machine study, where the idea is to develop key technologies for ion therapy. The reason behind that being that in the past decade, proton therapy has become a commercially available product. There are many companies offering proton therapy machines now. Ion therapy machines are still very bespoke facilities, and the idea here is to develop the technologies that will eventually make ion machines, ion radiotherapy machines also become a commercial modality. But at CERN, we don't just know how to accelerate protons and heavy ions, we also know how to accelerate electrons. So we actually teamed up with the Lausanne University Hospital, CHUV, to design a very high energy electron flash radiotherapy facility based on click electron acceleration technology developed at CERN. Talking about working with companies, based on LINAC 4 technology, we developed a very compact proton RFQ, which is licensed to a company called Adam AVO, Advanced Oncotherapy, that include that RFQ into a device called LIGHT, which would be a linear accelerator for proton therapy. What you see here is a relatively recent image of their prototype being installed in the UK. I think it's at the Harville STFC facility. I might be mistaken. So it's one of the STFC facilities. And at the same time, exactly the same technology is used in a collaboration project between INFN in Florence and CERN to develop, well, not that machine, but to develop a replacement to that machine. So again, you remember the Medipix example about InsightArt, using X-rays to do art analysis. Well, in some cases, you need higher resolution. In some cases, you need to be able to measure very light elements, such as sodium, for example, to authenticate lapis lazuli on paintings. In that case, you need proton-induced X-ray PIXE or PJ analysis. And for that, usually you have a huge proton accelerator. Well, the idea of our project of Machina is to have a transportable LINAC, something that you could put on a lorry in order to carry it from well, one museum to another museum in order to carry it into a church. Basically, if you can take the painting and bring it to the accelerator, the Louvre in Paris has a huge accelerator at Lhcb. It's easy, but in many cases you can't take a fresco from the wall and carry it around. So having such a machine would be extremely helpful again for cultural heritage. And that picture was taken last Thursday, so we have a first beam actually. We're very happy about that. And one more example related to accelerators and beams, it's simply using our knowledge in testing, well, in having to develop electronics that are radiation stable, and using that knowledge to test satellites. What you see here is a Celesta CubeSat that was tested by the European Space Agency at CERN for its radiation resistance. Well, many of the examples that I showed were still rather related to collaborations with external organizations. So how do you make sure that you create really new things? I need to hurry up, I say that. How do you create really new things? How do you make yourself interesting for industry that wouldn't think about you as a tech provider? First, you need to understand what unique value you really have and summarize that. For example, in value propositions, I took one here, data analytics. What makes our community unique? What makes your institute unique? Show some data about the great things you've already achieved, and obviously give a clear and concise overview of the competencies and technologies that you want to push. And once you have that, it's not enough to just let it float around the internet. You want to contact companies in a structured way. You need to contact many companies, approach them, cultivate your relation in order to finally close a few contracts, sign a few contracts about exciting projects. We did not really know what would happen when we contacted the German Federal Printing Agency, the Deutsche Bundesdruckerei. In the end, the Bundesdruckerei sent a team of innovation officers to CERN. We held a number of workshops, and we realized that CERN's theoretical developments in particular, think about quantum physics, could be used to develop a new generation of identity management, cryptography, and data handling. In a similar way, we didn't really know what to expect when reaching out to the Volvo Cars company, and it turns out that they forwarded us to one of their partner companies called Zenseact that develops autonomously driving cars. And it just turns out that just as we need very fast we need to make very fast decisions about data that we keep, very fast triggering using FPGAs, using machine learning on FPGAs. Well, in a similar way, a car needs to autonomously take very fast decisions about what to do if they see a pedestrian jumping into the road. But it's not only about big companies, it's also about entrepreneurship, it's about business incubation, helping either our scientists, our engineers who want to start their own company, or external entrepreneurs that realize that one of our technologies could actually help them develop a product, to take these technologies on board, which is why CERN, just like the European Space Agency, by the way, cultivates a network of business incubation centers, the Spanish one, Interstellar, being led by Eric. And it's also why I chose one example. It's actually quite an interesting example. That's a company, Orvium, incubated by the Spanish BIC, that develops a next-generation scientific publishing platform. They want to create a transparent scientific publishing platform, which is based on an open source technology developed at CERN Zenodo, itself based on another open source technology from CERN Invenio, that allows scientific data hosting. I've said that. Yeah, and that brings me to my last slide. Just a few key messages. First, serendipity pays off. Be audacious, try to bring people together, and eventually you will actually come to fun projects, to cool projects, to impactful projects. You need to have passionate experts on both sides. Of course, knowledge transfer projects are not for everybody, but you realize that in many cases, by showing the added value, you will find the right experts, you will create that passion. When defining projects, be as concrete as possible. You need to be clear about your goals. You need to be clear about your partner's goals, because that will actually allow you to achieve them in a reasonable timeline. Being too unclear, being too vague is, fortunately, a good reason for mutual problems towards the end. I'm missing a word here, apologies. But that leads to a few questions. How do we foster serendipity? How do we bring people together to start creative brainstorming and come up with great ideas? How do we make sure that what we do is connected to societal needs? I mean, we develop technologies, and many times we see that we want to push these technologies. We think that we have the solution to a problem. But how do we connect to those people in the outside world that have problems and actually look for very concrete solutions? You also realize that the timelines are very different. Objectives may be different. I mean, when you talk about high-energy physics experiments, you think in timelines of several decades. I think the FCC study, the latest date in its project plan is 2090. Compare that with companies, mobile phones that have a product life cycle of 3 to 6 months. There's somewhere a sweet spot in between that you need to find. But if you take these things into account, exactly, researcher motivation, and if you take the things into account, if you create the right conditions, motivate your researchers, provide seed funding, go out there, create serendipity, in the end the magic will happen that allows you to do knowledge transfer projects, and that allows you in the end to achieve the things that I mentioned at the beginning, and actually to comply also with the European strategy for particle physics that asks us, that requires us to do knowledge transfer, in particular with industry. That brings me to the end. I'll hand back to you.
Thank you for your talk, which is an excellent introduction for the roundtable. Unless there are any hot or urgent questions, I propose that we move to the roundtable. And Benjamin, I invite you to take a seat. And I call then Carlos Granja, who will animate the roundtable. Yeah, yes. So Carlos Granja from the Advacam company that was already mentioned. And then there will be Eric Fernandez from the InEU Star that was already mentioned in the talk, Spanish Science Industry Association. There will be also Ezio Previtali from Gran Sasso Laboratory, and Gaston Garcia from the Center for Microanalysis of Materials from Universidad Autónoma de Madrid. And did I forget? Yeah, I think. Okay, so I leave you the room.
Okay, thank you, Patricia. Thank you, the organizers, for the invitation and for this session, which is actually the first short point in this 40-minute session slot to explain and to stress the purpose or the goals that are expected from this topic. This roundtable is made by 4 experts who are here in front of you, and I will introduce them just to show the agenda, the plan. So I would like to try to keep the time with the stress to participation, to discussion with the audience. So I will ask or invite the experts to give their views on this topic and experiences in a very short manner, and also to address in their selection some selection of topics, issues that we put together. It will be, let's say, in 2 parts. I call them rounds, to give opportunity to have some feedback among ourselves and also with the public in this short time slots. As you can see in the part C and in part E, we would like the organizers of this event would like to have your feedback and your comments and questions, please. And then some short discussions. So this is the selected panel of speakers, experts, starting with Benjamin Frisch, who just gave his seminar. He's from KT CERN's group. He's an expert long-term on this topic with very broad scope of experience and activity, ranging from engineering, science, and technological developments. I'm very close with broad experience on a broad range of applications, including healthcare. Yes, and his background is in physics and in technology, and including some of his applications and experiences in, for example, in medical robotics, and so this is a very broad scope. The next one is Eric Fernandez, who is sitting second from my side. He's general manager of INEUSTAR in Spain, which is the Spanish Science Industry Association. His background is telecommunications and telecommunications engineering. He held several positions in various research institutes, supporting his broad scope and experience, creating and leading research teams in the field, applied fields such as non-destructive testing of materials. And he has held positions at the SAIDS Center in Spain, and is Associate Professor of Applied Engineering. The next one is Ezio Previtale, Director of Gran Sasso National Laboratory of INFN in Italy. He's Professor of Nuclear and Subnuclear Physics. He's been, his expertise is in particle physics experimentals, deep and broad scope, such as neutrino physics, and development instrumentation of particle physics detectors. And then he's been a spokesperson of Lhcb Experiment, and until 2020, coordinator at INFN, the National Committee on Technology Transfer. He's been responsible of KT projects such as this open at the INFN to implement base approaches and procedures, best practices to maximize KT processes from research to industry, which is the subject of this session, and such as identification of base approaches for effective, successful KT activities. Holds patents and has developed projects who have found and are licensed to industry. And the fourth expert is Gaston Garcia Lopez. He's director from the CMA, this is Center of Microanalysis of Materials at the Autonomous University in Madrid in Spain. Devoted, and is a center with an accelerator for ion beam and related nuclear application techniques. With a stress in multidisciplinary research, scoping from material science, nuclear physics, biomedical applications. Yes, he's been engaged in several also activities regarding research and infrastructures and technology applications, and he has held positions at some of these activities and collaborations. I will, and as is there, let's move on with myself. So here I include, and you will have a copy of this material, part of this of the material available for participants, also public, open. So the contacts of here of the experts and their institutions. And regarding myself, just briefly, I am a scientist, a nuclear engineer, master, and my PhD is in experimental nuclear physics. So I was doing nuclear structure and nuclear reactions, and I have been in transition gradually to applied research and industry applications. In fact, I am already working several years at Advacam, which is a spin-off startup of the Czech Technical University Research Center, which is the Medipix group in Prague, in Czech Republic. The director of the HIA is Ivan Štekl, is here attending the conference. And also, and just briefly, and from the activity of Advacam, two other startups have appeared, as briefly mentioned. And the second one, InsideR, was actually promoted as incubator from the European Space Agency. It has a very small program, so they want to see these sophisticated technologies or related technologies to space to have ground applications. And also Radalytical, which is again is just specialized on robotics, in imaging autonomous robotic systems, quite advanced, and also remote systems. And there are the web pages. I just show very briefly, will mention some of the points. I will not read them, but this is a collection of key points, challenges that we put together in this broad subject. And I will leave them here during the time that the experts will take the word for you to review. And they have a free space for giving us their expertise and recommendations, and eventually also to address some of selected points in their own selection. yes, just starting from the importance of significance of KT for researchers, for scientists, and for society. So starting with that, yes, and then the different, let's say, interactions or requirements, yes, and some of them are from Europe. So, for example, the KT appears as in the European Strategy for Particle Physics. It's officially there. It's a non-negligible element of that, and also it's a requirement of the funding agencies of Europe. Yes, and it's a channel actually, and it's an element that has in fact the importance and significance for, or should have a different level for scientists, for young researchers, for academia, for university groups, which our experts will be telling us a little bit more. So I pass the word, and my last recommendation is to create this as a forum, interactive forum, in this very broad community of different and related fields. So first, according to the agenda, I will be asking, and perhaps I will start with Eric in this order, and then Encio. So as I put in the agenda, so it will be, let's say, like a few minutes, about 3 each, which they can, and then I will be calling you in this order. Thank you.
Okay, thank you. Yes, okay, thank you very much, Carlos. Also, I want to thank for this invitation and in this really nice place. So it's my first time in this building, so I hope it will not be the last. It has been really nice to have a walk through the gardens during the last time, so really nice environment. So I think that today we will talk about a very hot topic. All of you, or the majority of you, come from public institutes, and as you know, public authorities are pushing a lot about knowledge transfer. So first thing I want to say in my intervention is that it's something that we need to do. So we have the obligation to understand each other. We have a really good research community in this field, okay, with many technologies that probably during those seminars, talking together about technologies, you could see that you have similarities in many technologies, and those technologies also can be really useful for the industry. So we have the obligation to understand each other and try to generate short-term impact from your research. So I don't want to spend too much time during this introduction, because I think that the really interesting thing is to have time for a real discussion. But I think that the main important thing that we need to do is to try to define how we are able, or how we are going to be able to establish communication channels and methodologies and procedures in order to speed up a process that nowadays already exists, but not enough. So.
Thank you. There will be a space for questions, so I will ask, please, next, Encio, please, to give us.
Okay, thank you, Carlos. So I'm here having, in some sense, two different point of view, in the sense that I'm a researcher, but in the past I coordinated technology transfer office, considering the full INFN as a potential place where we can find some technology, some application. My introduction is that technology transfer gained a lot of interest during the last few years, but we have technology transfer that started many years ago. Probably now we are able to see in a more clear way the importance of the technology transfer. I have two different approaches. One is that I believe that normally we do technology transfer making our job day by day, in the sense that the interaction of high energy physics at the frontier of the technology allow us to have the right instrument to work on particle and fundamental physics, but in parallel, we collaborate with the industry that acquire technology and learn with us new approaches concerning the strategy for new markets, new instrumentation, new evolution of the technology and the application. The second point is that in the last few years, we need, in my opinion, two different aspects to take into account. First, we have to identify the best way to communicate with the industry. It's not obvious, it's not clear. In my experience, what I see is that scientists are very bad entrepreneurs. So the problem is that we have two sides that are interested in each other to interact, but we have to find the best way to create the condition in order to obtain the maximum collaboration between the two parts. And the second point is that starting to this, we need in some sense to create a structure in which in the scientific world, we have to ask especially to our colleague, to look to their activity in two different ways. One is what we have to obtain in our scientific and fundamental research, and the other to look if what they are doing could be in some sense applied to other fields that are not directly related to high energy or astroparticle or nuclear physics. I see in my experience that many times this happens. We have probably to learn a little bit more in detail what we could do in this way.
Thank you. Please, I give the word to Gaston.
Thanks very much. So I would like to highlight the fact that it has been mentioned a few times already, for example, the European strategy for particle physics, but in this event, we have a wider view. We have high energy physics, we have astrophysics, we have nuclear physics, and when we talk about knowledge transfer, we must have a wide view, yeah? And this wide view includes also medium-sized and small-sized facilities, which at the roots are nuclear physics, accelerator physics. These are the tools, but which have extended the applications to many different areas, such as material science, biomedical areas, and so on. And some of these areas have been mentioned here as well. So when you look at this wider landscape from the side of the facilities, you realize that the interaction with industry is not so much focused on what you could call, simplifying a bit, industry as a supplier, which is a very important dimension, of course, but there is also the dimension of industry as a user, yeah? Which has been mentioned here as well, yeah? But it has a much stronger, much heavier weight in these other facilities, such as synchrotrons, free electron lasers, ion beam facilities. I'm working at one of these ion beam facilities. We have two in Spain, in Madrid and Seville, which collaborate and complement one another. And these two dimensions are very important. And I would like to highlight also that from a different point of view, we also have to adopt a wide view, and we have to see technology transfer and knowledge transfer at large as a part of an impact landscape. Yeah? So we have impact as production of knowledge, pure knowledge. We have impact as technology spillovers to industry, in some cases with direct interactions, in many cases as indirect things that arise from publications, from scientific publication at a later stage. And also we have training of people, we have science culture, we have even shaping of science policies. All these things have different dimensions that can push in this direction, and we have to have them all in view.
Mm-hmm. Thank you. Before going for questions, a couple of comments. So again, I really appreciate these concepts and this speech we are having. Quick remark, or let's say from my experience, certainly, and as I work with students, I have several at the present, it's very important, the motivation and the reason why we are sitting here, the reason for KT. In fact, I think I have been communicating, preparing this session with the experts and with Maria, Jose, and the organizers, is to have clear motivation and the reason, again, taking this example with the students. And one of them, and which happens in the company, and for me still a bit foreign concept, is the the application, the use of a product, of a technology, because I am a scientist really, but I have transitioned, and I think it's very good. And most of the teams in the company, and in my experience, they are very specialized engineers. They have these applications and this, let's say, real world, much more complete in their portfolio. But the stress, so in the company, is our case, we have many ideas and many prototypes and so, and I have myself, and I think some of us have to come to ground and make compromises and make some choices and simplify things. Another one is also to give up, some perfections or some very elaborated, let's say, products, but to make something simpler that then can reach the market quicker. And so there are many elements actually, and some of them I think are reflected here in this list. And then to open the questions and the discussion, the forum actually active, I hope, in particular, and that was my choice number one in this list, is perhaps to stress or to clarify why this topic, in fact, is important, is significant. No? And I got from the experts one quick answer, which I will translate here, is that it's actually in our interest, in my own words, yes, at different level. So in order for science and for research to exist and prosper, so most of us, we used to, and not me anymore, we used to have subsidies, the support from the public funds. And actually we are all connected, yes? So this is a closed circle. So public funds, the budget, has to have some income, yes? And very much in the form of taxes and also activities, contracts, so the economy. There are some concepts which I have learned, is that there are some parameters of return in economy and investment. So in space in particular, which is the application I am pursuing for several years at the industrial applied level of this MEDIPICS, TimePICS CERN technology, is this factor is relatively high. So these are high value added activities in the sector, which is I think one big advantage of our communities, if I can be part of it. Yes, so this is perhaps from all this big list, perhaps my priority, yes, to have clear or to take the few minutes to clarify the importance. But before passing to the second session to my expert speakers, I will ask questions or comments from several of you. So please, and I will be aided by a couple of colleagues to handle the questions. So this is the room, the opportunity to please actively contribute and discuss this subject. Please, here one.
Okay, so thank you for the opportunity. Let me, make a comment. I would say that I absolutely agree with what Gaston, was saying. Let me add something else. In my view, we should think of Europe as not only a landscape, but an ecosystem. Let us say that we have, bigger research facilities. The largest is CERN. We have, Gran Sasso. We have national facilities. So, Lord, all of us want to do technology transfer. Of course, we have different means. We do, small facilities do not have the possibility of having, a specific technology transfer. But, I would say that it is very important to have this technology transfer all over the ecosystem. That there is interaction between large and small facilities. There should be interaction indeed, and is there between companies, small and medium, and then we should really aim to have this cross-fertilization. This is easier to be done in countries with the same funding agencies and language, such as the United States. It's not so easy in Europe, because we have different things. Yes. So that's something that I think that we should try to improve as much as possible.
Thank you. Yes. If one of you want to comment.
Maybe I could comment. I think the fact that the whole landscape is formed by very large organizations, medium-sized, and many small organizations. So if you compare one-to-one, small organizations seem not to have such a big role, but there are many of them in different areas. And there is a size factor in all this. Linking to the industry is difficult. Yeah, it's not whose fault it is. That's out of the business. Yeah, it's just difficult inherently. So this requires many times dedicated resources, and this is frequently affordable at large and medium organizations, and it's barely or not at all affordable at small facilities. So a better way to interact, as Joaquin was suggesting, and gain experiences and profit from what the other does would help to boost the potentialities of smaller facilities as well, I think.
Please, Benjamin.
Maybe there's one thing that it should be mentioned, that should be reminded, is that for already a couple of years, there is an organization that exists that is called HEPTECH. It is currently headed by the STFC, by the UK STFC, that tries to coordinate the technology transfer activities of the big, the medium-sized and small-sized labs. I believe there's also some universities part of it. So I think the original idea exists. We might want to promote it. We might want to make it live. We might want to make it more active in order to provide that support that was already mentioned. Because indeed, and I want to briefly react on that also, on also what Ed just said, how to bridge the gap. I mean, doing knowledge transfer is not a little sideshow that you can do as a principal investigator. You do need the professionals who know how to interact, how to create, well, I mean, how to handle intellectual property, contracts, organize events, provide funding, manage funding. And I do understand that for a small lab, of course, it is a lot more complicated than as an organization at CERN. We are about 25 people in our group, and we already feel that we're probably not enough to do all the things that we'd actually like to do. So some sort of improved collaboration, possibly using the tools that we already have, I think would definitely make sense.
Thank you. Please.
Totally agree. I think that this is something absolutely necessary because, as Joaquin or Aston said, so the industry cannot be looking for the technologies in each laboratory in Europe, so it's something that has no sense. So having some kind of hubs or some kind of initiatives that could give support in knowledge transfer with all this specific knowledge that need to be known from the people, and that you gain knowledge with time and you cannot spend too much time in some small laboratories is really, really necessary. And I think that this is something that needs to be or will be really useful for having access to the technologies from the industry, but could be also very useful for the community, because I'm sure that you are developing similar technologies in different laboratories across Europe that could be simplified if you collaborate more. And probably you don't know that this other lab is doing this research in this specific technology, that you don't need to reinvent the wheel. So yes, for sure, I think that this will be really useful, these hubs or this, I don't know how to call it.
Okay, make just a short comment. So from one side, I believe that at the end, we collaborate with the industry normally. It's not something that doesn't happen in our activities. Probably what we have as a problem is that is not so wide as everyone for all the stakeholders, there is a possibility to assess the information. What it is important, in my opinion, is that if we try to understand, not only in large laboratories, but also in small laboratories, that we have something that could be used as a, let me say, an information for the wide public. Let me say, wide means all the possible interested people. We may help very much industry to assess our technologies, our knowledge, and so on. Let me say a point. It is not straightforward. After the information, we needed to understand clearly what will be the protocol for the knowledge transfer, because we have an approach that is different respect to the approach of the industries. So at the end, we could have an information wide as we want, but we could not be able, for example, to have the possibility to interact in a right way with the industries. There are rules. Many of our laboratories are public are supported by the government and so on. There are rules, there are other type of possible trouble that we have to solve. And so the first is we have to make, as was reported by Benjamin, we have to inform all the community that in our laboratory we have technology that could be useful for the society in general. And then we have to identify what will be the right approach in order to allow industry to collaborate with us efficiently to transfer this knowledge from the academia, from the research center to industry, to company, and so on.
Mm-hmm. Thank you. If you have questions, please, they have priority. Please, there is one behind in the middle of the room. Please, let's try to be brief as possible to handle.
Yes. It's very nice, and we have seen now very good best practice and examples which are very successful. So I have now 2 questions, and all these points are somehow ideas how to improve, how to have better communication channels, better connections. But from a point of view of a scientist, that ask me 2 questions. First, do you think that, so to say, the tools and the support are all there? Or do we need also some improvements and more people in the departments? Is on this side somehow an improvement necessary? This is, so to say, the question to these departments. And the other question is, what is somehow the parameter and how to justify if a knowledge transfer was successful? Is this, so to say, then if there is money, if there is some gain in so what defines that is a knowledge transfer is successful, and also opposite, there are probably also failures somehow, so that it doesn't work. So how is this communicated? What are the measures for making a thing successful, and where's the threshold to call it as a successful knowledge transfer?
Clear. Thank you. Please.
I will start the answer for the end. One of my old professors explained to me that research became innovation when the impact is wide on the society. So the question is, we have a technology that we develop in our laboratory. We have to trace this activity. We have to interact with the industry. If what we start as a, let me say, a technology for someone, it became technology for all, this is successful. The problem is that, in my opinion, in what we do normally, we don't have a real, let me say, history of the technology that we develop in the lab. We see before the discussion of hydrotherapy, it is clear that the accelerator was built at the beginning to make basic research. Now became an important tool for cancer therapy. So what we can say is that our community have generated something that is important for all the people. This is not necessary to have so wide, but we have to check if the technology will become something that we applied. Concerning the first point is that you say everything is there. Well, one of the main problems that was raised by Benjamin is the way to involve the scientist, the researcher, to do something that will create the step towards the market. There are many possibilities. I just remind an experience that we have in INFN. INFN, we decided 5 years ago, 6 years ago, to set a special grant only for technology transfer. There are 5-6 grants per year in which we say to the scientists, well, you have something in your mind that could be addressed to the market. You may ask us some money, some resources. We may help you in implementing the system. What we ask you is to have an interaction possibly with some industry, or if you are planning to make a spin-off. And what I would like to say is that each year we receive something around 20 requests from researchers. And many of the projects that was approved in this, let me say, 5-6 years, many of them became in some sense a success, in a sense there are licensing, there are spin-off, and so on. So probably what we have to do, this is my impression, my experience, we have to help a little bit the scientist, the researcher, to make the last step, what is called normally last mile before the application. And we may have many different approaches. I don't want to say that the approach that we apply in INFN is the right approach. It's something that works, in the sense that after a few years we could say that the approach is reasonable. We have some good results. Probably we have to find also other strategies, and probably we have to implement this as at the level not only of the single laboratory or the single institution, but as a wide capability of our community to integrate what is the need, integrate, let me say, probably is too strong, but to organize something that allow the academia to generate a final product that could go directly to the market. That is something that we have to decide, taking into account, I would like to remind what I said before, that a scientist normally is not a good entrepreneur. So what I see in my experience is that when we install in INFN a spin-off company, we have a scientist on the side, a management on the other side, and they are working in parallel in order to obtain what is the final result.
Thank you, Benjamin. I think you wanted.
I agree.
Or,
okay, sorry, Benjamin. Thank you. I agree with your point of view about the scientist, because in Spain we have a phrase which is something similar to shoemaker to your shoes. So scientists, you know how to do science, and not necessarily you know how to do business. No, that's why I think that it's really, really important the intermediate bodies like a KT department, transference office, or you can call as you want, but the main objective is to disturb the minimum to the scientist from doing science. Okay, the question need to be, okay, do you have something that is unique and could be useful for someone? Please explain me this, and I will try to translate to a clear sheet like you have in CERN, one-page sheet, because the industry will not spend more time reading a full paper. So that's, I think that we need to have this kind of bodies to help scientists to do this work. And also I think that in the beginning, this is something that the knowledge transfer is something that is still growing or is in the beginning, so needs some push from the beginning. And I think that the public authorities, here they have a role. So funding collaborations is something that helps to establish those collaborations, especially when we want to do something that is not being done before. So I think it's part of the role of the public authorities to start pushing some activities like that. So I think in order to establish a culture of collaboration, this could be also useful. And regarding the indicators, I think we could have objective and subjective indicators. Okay, so the objective for me are clear, so it's incomes and jobs. So probably there are others, but for me the most simple and sometimes the simpler is the best, are those. But also you need to have stories to tell. That's the subjective part. So it's not the same to have 2 million selling vending machines or 2 million selling equipment for medical application that is saving lives. So this is subjective.
Thank you. Benjamin, please.
Maybe jumping on that, on the subjective side, what we see is that in matters of stories that CERN communicates, the stories that tend to attract many clicks, besides the ones when there's really a big discovery to be announced, are the ones of the likes of Mars bioimaging, where you see the image of an ankle in color CT, because that is something that is more accessible to the general public. So you do create that impact, and the advantage with having stories that are accessible to the general public is that in the end it's the general public that will vote, that will give a certain mission to those people who in the end are going to decide about finance funding. So part of the impact really comes from the story. And using metrics is extremely complicated because it might lock you into doing things just for the sake of fulfilling numbers. One that tends to come up and that CERN does not care at all about is number of patents. I mean, at CERN, we don't like to take patents. There are other organizations, they love taking patents, and they just keep taking patents because they said that the more patents you have, the more successful you are in doing KT. But if none of these patents is ever used in a technology, well, then what do you have the patent for? When you start talking about revenue, you only look at revenue. In many cases, research organizations, universities, most of their revenue comes from one or two technologies that turned out to be the thing that generates money. But does that mean that you want to drop all the other projects just because they generate less money? So there is really this difficulty of defining when you're actually successful, because on the other hand, you could also say that, well, the tech transfer is successful, it has impact if it has helped to save a single life. Which then leads to a discussion of how much is a life worth, but that's more statistics and political discussion. I don't want to start here. So it is very complex, and it's something that we need to keep in mind when talking to our funding agencies, because in many cases you want to have some sort of objectivity. It's just that you also need to be careful of how you define your indicators.
Thank you. Please, Gaston, quickly.
I would like just to mention that globally, I will not give more examples. I think they were very nice, the things that were mentioned by the other panelists. But altogether, my impression, answering to the question by the audience, is that the tools, the methodologies, the practices we have for knowledge transfer in Europe have some success stories and some not so successful. But overall, I think we have to improve. So we have to put more ideas on the table. This is my conclusion.
Certainly. Thank you. The question, just a short comment. This is a key point, I think, in my opinion. These tools, which are many. This is a complex long-term activity, of course, and in particular the license and the patents, certainly, which is not straightforward. I think it depends from country to country. There is the American-USA model with different conditions. So certainly it's a complex subject. And quickly also on the concept of knowledge transfer, say for myself, and I think I'm not the only one, it's actually pretty broad at different levels. So even it turns out that it exists even within teams, within companies. And it has, and I mentioned just one hindrance, like let's say problems, issues, and that there is a natural tendency of companies, society, people, experts, students even, to hide, or not to, they don't feel or they don't see a sense in sharing or in work, in teamwork and in documentation, for example, and actually many issues, which actually in the company we are practicing or learning actually constantly. So if there are maybe one last question quickly, please, to the audience, if I can. Well, I see two questions, but if we can handle very quickly, please. So one here and one up there, please, one there. You need a microphone. Yes. And I will ask some, because we have limited time, for some short replies to my experts. Thank you. So probably we start there on the blue.
Yeah, it was maybe touched upon in the first talk, but we're also pushed very much nowadays to go open, fully open with our research and as fast as possible. And I see that there's maybe a little bit of tension between fully open publishing, very rapid open publishing, and then commercialization and protecting your IP. So do you have some comments on the procedure there or advice on how we should proceed?
Well, I'll try to be brief. But fundamentally, being open about research and publishing does not prevent commercial success. Now, of course, you could lock yourself into the thinking of a very protective industry where you do not talk at all about what you do until you have the final product ready. But that's not at all the approach that we have. I think, and CERN has been showing that, by being open, by publishing, by actually releasing quite a lot of technologies into open source, you can still do very successful knowledge transfer. And in some cases, you might realize by yourself, by discussing with industry, by discussing with your knowledge transfer team, that the best dissemination strategy might not be to immediately publish, but to defer by just the amount of time that is necessary to protect the technology. And that might be important if the gap to actually create a product which is the ultimate dissemination, the financial gap is so big that the company is going to ask for some sort of protection of the investment. In some cases, when you talk about medical devices, you realize that bringing the technology into the medical devices and investment is going to cost multiple tens of millions of francs, or euros as it is, or whatever currency you use. So the art there is to know when protection is really required, and then to be fast, of course, to not defer the publishing process, or to actually know when it is not required, and to then continue operating openly, publish, provide technologies as open source. And just because you release something into open source, for example, doesn't necessarily mean that the market will take it. Is what I said in my presentation. In many cases, you actually need to explain what your technology does, what your code does. If you just have a bit of code floating out there with an open source license, many companies are just not going to understand what it's supposed to do. Talk about collaborations, you might realize that you want to improve a software tool, an open source tool. Industry wants to also improve it, so you might just as well team up and have a real knowledge transfer project to jointly develop open source technologies for yourself and for the broader community.
Mm-hmm. Thank you.
Yes. I completely agree with Benjamin in the sense that I do not believe that each time we have to make a patent or to make a protection on the... and in general, if you need to protect something, you could do without a critical situation with respect to the open publication. Typically, we take for a patent, we take something around 1 month, so it's not an impact on that. But I completely agree on the fact that in general, I don't see it's not mandatory to have a patent for each development, and sometimes the patent became a problem in the sense that there are, in that case, some rule that doesn't help too much to transfer the information from the academia to the industry. So one of the important aspects of the let me say, of the knowledge transfer office is to identify clearly what has to be patented, what is not to be patented, and then to go ahead in that way. It's not a minor problem, but it's something that has to be taken into account.
If I may say, I think one of the key problems with this, and I empathize a lot with the colleague from the audience that raised this, is the time dimension, right? I mean, at time equals infinity, there is no problem, yeah. But the problem is that today I have something where I have a paper draft, and then I realize, oh boy, maybe this, I should consult this. And then if I don't have an agile means of checking this quickly, then I'm in trouble in practice, yeah? And this is a problem we have. You're absolutely right, and we must improve. And it's the time dimension, so it's being fast. Have a unit in your institution that can do this fast, which is challenging, of course.
Yes, thank you. And the very last question, please. Yes. Yes.
Yes, thank you very much for the nice discussion. My question was on your comments which you made where you said that the skill set of a scientist and of an entrepreneur are actually very different. And I was hoping you could elaborate on where exactly you see this difference in skill set.
So, sorry, I didn't understand well the question. Could you repeat, please?
Yes. So, as you said that scientists don't make very good entrepreneurs in your experience. And I was wondering where exactly you see the difference in the skill set.
Okay. So my experience. I will talk about my experience in the field of generating spin-offs from science or from technology. I was working in a research, in a technological institute, okay, and the strategy we had about new spin-offs was that the main researcher of the technology was the CEO of the new spin-off, and part of the team was working also in this team. And the first years of a spin-off, the main activity that needs to be developed is a commercial activity. So sometimes some scientists can do that, but not necessarily. So the policy we had in this institute was modified in, I think, close to the 2000 year, something like that, 2001, 2002. And we decided to start having professional managers for the spin-offs. So it was the main researcher that has been developing the technology had the opportunity to go to the spin-off like a technology manager or something like that, but the management work was done by an MBA or a professional in this field. And our experience was that the spin-off survival rate was really high, and the numbers of the spin-offs were really better than in the other way. So I don't know, I don't say that the scientist is not a good businessman, but don't need to be. So if he wants, and if or she wants, and has the availability, the capability, so for sure, but not necessarily. It's not regularly. It's not the case. I don't know if I have solved your question.
I had a comment that starting from the point of view of a scientist. What we see, I don't want to say that there are no scientists able to prepare and to become an entrepreneur. But the problem is that normally scientists are concentrated on the ideas. That's the main point. What we see is that when someone arrives, they say, this is a very beautiful idea. I believe that the market needs this idea. I will develop the idea. But the problem is just, was commented before, the main problem is that the market really need this new approach or not. And you need something that stay outside and look in a, let me say, in a critical way what you are proposing. One of the best success during my activity as a TT, or technology transfer in NFN, was a spin-off of theoretician. It's a spin-off that applied technology for particle physics to biology. And the main advantage is that when they start the spin-off, we have on one side the group of scientists that comes from particle physics, and there is another group that is completely different and independent that work on the management. And the spin-off was completely successful thanks to this. Because when they start, the scientists were convinced that they have the good idea to go ahead. When the management arrives, they change completely the structure of the spin-off. That was, it is not only one experience, but it's one of the most interesting experiences that I had in during the period of stay in KT.
Gaston, quickly, please.
Yeah, I also wanted to say that it's not always about people. Of course, we people are shaped by our experience, yeah, and we may be a bit different after some time. But it's also about institutions and the machinery you have around. For example, consider the example where at a facility you need to develop an instrument which is not available off the shelf, and then sometimes you have to choose in the end if you go to industry and you limit a little bit the level of ambition of what you want to have in the end, or if you go to infinite ambition and you develop a scientific collaboration with another public institution. There's a trade-off. Yeah? In some cases, you don't have any choice. You have to go for a collaboration. But you will sometimes lose something in terms of support once the thing is delivered. You will lose a little bit the control of the time scale as well. Yeah? So in the end, we must look also for options in which both worlds give the best they have. And sometimes maybe you can have the best expert in a public institution collaborating with some company that keeps it's like having the best milk, but you need the bottle to be able to drink it. Yeah, so you need both things, I think.
Thank you very much. You have the contacts here. Please feel free to contact during the coffee breaks and during this event that you are here. I will ask that, or used to ask that to the students. And also there are some, I understood, some working groups, and there are some contacts here. So please, if you want to say something or send us offline comments, please. And thank you again for the time.
Thank you again, and let's thank again all the experts of the roundtable. And now it's time for a short coffee break. We have to reconvene at 4:30.
Michael and other colleagues invited that will be invited here to have a nice discussion. Then hopefully our young colleagues will be happy. And okay, let's start. Carsten, you are logged in? Carsten?
Can you hear me?
Well, if... Hey.
Hello.
Hi, you can start when you want. I will please try to stick with the 15 minutes. I saw that you have 15 slides, which is good.
Can you hear me okay? I wasn't quite sure if you have sound from Zoom. Can you hear me okay?
Yes, you can.
Hello. Can you hear me okay?
Yes, it's fine, and we see your slides. You can start, please.
Brilliant. Okay. Good afternoon, everybody. And first of all, thanks a lot for the invitation to contribute this talk, and my sincere apologies for not being able to join you in person. We had a medical incident last week in my family, unfortunately, and that meant that I wasn't able to travel anymore. I'm very happy to have that opportunity to contribute a talk about the training of scientific and technical staff. And just a few words about my own background. I'm very keen on developing innovative ways of training researchers to their next career pathways. I've had the pleasure of coordinating no less than 5 Marie Curie innovative training networks. In fact, I was just awarded funding for number 6. And via this route, I've overseen the training of around 100 Marie Curie fellows across all of Europe. I'm also the director of 2 centers for doctoral training in data-intensive science at the moment, with each one training around 40 PhD students. I'm the head of the physics department at the University of Liverpool, and in that role, I'm responsible for the training of about 150 PhD students, but importantly also for around 100 research staff, so postdocs and more senior researchers. And finally, I'm the chair of STFC's Education, Training and Careers Committee in the UK and a member of the UKRI Skills Advisory Group. And in that role, I'm overseeing researcher development in the UK and through our international partnership programs also beyond. So really a very strong focus in my activities on developing new ways, better ways of training researchers. Now, in the first slide, you could see Madame Curie watching over our shoulders, and the Marie Curie actions clearly are one of the most outstanding ways in supporting researcher developments. There are the Marie Curie Innovative Training Networks, or doctoral networks, how they are now called. There are also the individual fellowships, and these have over the years trained more than 100,000 researchers in Europe. It's one of the most successful training schemes, and they have a pattern, a special approach in how to train researchers in collaborative actions. And that is really something which I think exemplifies in a way like no other program how we should be driving researcher trainings nowadays. Now, networks, why are they ideal for researcher training? They bring together complementary expertise. They connect research infrastructures that have quite unique capabilities that otherwise would not be disconnected. And they have international collaboration in its core. Here you can see one of our past fellows, Julian, who worked at the Helmholtz Center Dresden-Rossendorf, and he brought together the laser and the accelerator communities in his project. So interdisciplinary research built into the very doctoral program that he was enrolled in. Within the innovative training networks, we have trained around 100 Marie Curie fellows, and in fact, you can see all of them here on this slide. The plasma ball is made of the photographs of these fellows, but more indirectly, we have trained thousands of researchers from PhD students to senior experts through numerous workshops, schools, conferences, symposia that we have organized via these training programs over the years. So a really critical aspect is that not only is there the cohort approach to training via a network in itself, there's also the important element of bringing together these cohorts of students with the wider community through targeted training events and then mixing with the wider research communities.
Now, this symposium today is to build bridges between the nuclear, particle, and astrophysics communities. And ultimately, what we all have in common is that we want to drive fundamental research, but we are also all instrument builders. My own background is in accelerator science, and I'm based at the Cockcroft Institute, which is a center of excellence for accelerator research. And what we all have in common is that our research is at the very cutting edge of technology, and that it also requires expertise in different areas. And I will give you an example on just the next slide. What also we all require is we need access to large-scale research infrastructures, and these are infrastructures to which no single university would otherwise have access to. And that's very important when it comes to what makes our training, our researcher training different to other disciplines, is that we really rely on these infrastructures and the access to these infrastructures. And that also has impact on the way that we train our scientists, all the way from undergraduate projects through doctoral programs and then more senior researchers. Now, the one example I wanted to use is something that is needed for all of our research, no matter whether it's astrophysics, nuclear, or particle physics, and that is we need diagnostics in order to measure the beams, the particles that we use for our experiments. Now, what is shown here is an optical diagnostics. It is a system which relies on a digital micromirror array, so a small array of 1,000 by 2,000 mirrors that can all be individually controlled. In astrophysics, they are used to image the corona of a star. In particle accelerators, they are used to focus on specific areas of a particle beam and to analyze these areas in more detail. Fundamentally, it's something very easy. You generate light via your particle beam, you capture that light, guide it onto the mirror, and then onto a camera system, and you measure the area of the beam that you're interested in. But the point is, if you really want to do that right, you need to have expertise in a number of different areas. You need to be good at electromagnetism because you need to understand where the radiation comes from initially. You also need to understand optics because you want to guide the light to your camera system via this digital micromirror. To control the mirror, you need to be good at programming and electronics because you need to have an access to that system and you need to optimize the overall light transport. If you want to safeguard your camera, you also need to be good at nuclear physics and Monte Carlo simulations, because if you're doing all of this in an accelerator environment, you will generate radiation which could damage your camera system. And the protection that you put around your camera, the shielding, will depend on the type of beam that you're using. And you can see immediately, even something very simple like this monitor here requires a researcher to become an expert in a number of different areas. And that really makes it quite special and unique as a research discipline. And that's actually the backbone of all of the training programs that I have initiated over the years. Beam instrumentation was the very first program suggested by an international consortium back in 2007, a network called DataNet. And ever since, beam instrumentation, so the development of state-of-the-art sensors, has been a key ingredient to all the training programs that I have developed afterwards. One of the things that makes that so interesting is that it involves different disciplines in physics, but also more widely engineering. And the applications of these devices can be found in a number of different areas, from material science to security application, all the way to cancer therapy and life sciences. So a really broad area that all benefit from our technical expertise. What's also important for the training is collaboration with industry, so cross-sector collaboration to really drive innovative solutions. The photograph here was taken during one of our workshops, and you can see the director of Stahl Electronics working with our fellows on the development of a small-scale electronics in order to trigger a little detector. The fellows had to assemble this detector themselves. They had to do the soldering. And I still remember when there was one of the fellows who was very, very theoretical in their own work, who came to me and proudly showed me their burn marks on the hand from the soldering device, because it was the first time that they had assembled such a detector. And this aside, they afterwards told me that they now appreciated much more the complexity that goes into the actual assembly of the instrument. And they actually felt that this was really helping them develop their theoretical ideas for experiments, because it gave them a more realistic grounding. Now, this kind of direct interaction with industry is, I think, absolutely crucial. It gives hands-on experience to academic researchers, to PhD students, postdocs, who really learn from the best in the field, and that are the companies who are developing these products. And we have taken industry collaboration to probably new heights in the way that we work with industry in our doctoral training centers. I mentioned the 2 centers that are focusing on data-intensive science, and every single PhD student in these centers is spending 6 months in industry as part of their training, and that is 6 months outside of their core PhD to really learn additional skills that only industry can provide. This significantly broadens their expertise. It also promotes independent work, and it also boosts their employability. That's something that we have clearly seen on the number of job offers that they have received in comparison to other students after graduation. Now, what's also important for a state-of-the-art training program, in my mind, is access to international workshops and schools, which was clearly very limited over the past 2 years. But the workshop, the symposium today, is a good example that now finally we can get back together again. This brings together diverse communities. And the photograph here is from a school on laser applications at accelerators that was held in Ganil, France, back in 2012. The reason why I like that photograph so much is because it shows one group that belongs together. And I can tell you at the beginning of the school, that was absolutely not the case. The school consisted of essentially 2 communities, the accelerator experts and the laser experts. And it took a good week for them to realize that the challenges related to optical cavities are actually quite closely related to the challenges related to radio frequency cavities. And by the end of the event, and that's when this photograph was taken, it really became one group that discussed not only their own research, but also opportunities for future collaboration. So international events bring together communities that otherwise don't talk enough with each other. And the symposium, I think, this week is a fantastic example for that. And it also is a platform for joint future research and development. What also large-scale training initiatives can do, which is not possible if we are talking about single doctoral projects, is that they can organize large-scale events. This year is an event that we organized in Liverpool back in 2019 on a future circular collider. It brought almost 1,000 people into the Liverpool arena that all followed the program and the ambition of the FCC and related projects. It also gave industry a very prominent role, because we combined it with a co-innovation workshop in the afternoon, where around 100 companies joined, and we talked about the industry challenges, the product challenges that need to be addressed over the next 10-20-year period. An event of this size has nice media coverage, which means that there's also direct engagement with the general public, and that connects maybe nicely to what you will hear just in a few minutes from the other speakers about the importance of outreach as part of training and as part of engagement. What we also are building in all of our training programs is the importance of knowledge exchange. And that's something where traditionally, I would say, especially academic staff at universities are struggling with. In my department, it has been a very difficult journey to convince academics that impact generation and considering how our research influences society more widely should be part of everything that we are doing. The photograph here shows Alexandra, a past fellow who set up her own company as part of after her fellowship and following an STFC Royal Society of Edinburgh Enterprise Fellowship. So we encouraged her from the beginning to consider knowledge transfer, created awareness of the importance of IP protection. We gave her access to funding mechanisms that allowed her to set up a company. And then we also supported that company as it was growing, and it became a European success story via the Arius project. It became an SDFC success story in the UK, and it also became a technical highlight in Aztec's 2019 report. So lots of very nice results from a company that really spun out already from ideas developed in a doctoral program. Now, what large-scale initiatives also allow is to engage with our community. This year is an example of how we took doctoral training programs to international conferences, in this case, the IPAC conference, the largest conference in the world on particle accelerator science. And there we had a stand that showcased all of the outcomes from these projects, and again, provided a very good platform to discuss what is needed next. So where are we going to? What are the opportunities for joint R&D? And to just, again, build the bridge about the importance of communication and really building this into training programs, making sure that your young researchers, your postdoc, actively engage with the general public and schools. These are some of the most demanding audiences, and to become a good science communicator is important beyond the fact that you may have to defend your research at grant panels. It really fascinates the next generation of scientists and engineers, as you can see nicely here on that photograph. This was an event that was hosted at the University of Liverpool, where we had 200 school children learn about particle physics and nuclear physics applications. What's also important, and that's maybe my last recommendation when it comes to how do you create a powerful and impactful training program for researchers. Researchers are very good at doing research, but they're not necessarily the best at doing the administration part of research. So excellent researchers require excellent support. And that's why I wanted to highlight the importance of having a strong team of project managers, of communication experts, of project assistants, so people who really take the load of the researchers and give them the professional environment and support that is needed to really get the best out of research projects. At the Cockcroft Institute, I'm very happy to have the support of the fantastic project team, a 4 or at the moment 5-person team, including also a business development manager, who really are there all the time to get the best out of our research projects. And with that, I would like to summarize. What I try to show you is that, to me, a successful researcher training program today should be based on a cohort approach, and it should connect universities with research centers in industry for all the reasons that I gave. The cross-sector experience that the students and researchers will have will broaden their skills. It drives innovation, and we have seen that clearly on the number of products that came from our projects before and after, and it also improves the employability of early stage researchers. Building in interdisciplinary training, especially also industry placements, secondments to small companies where the researcher get a completely different environment, supports knowledge transfer, and it also paves the way for future projects. We have promoted this training model nationally and internationally through workshops, learning and teaching conferences. I was invited to present it at the European Commission in Brussels several times, and it has significant impact generated for our research community, but also successfully engaged the general public at large. And with that, I hope I gave you some stimulating ideas for now the next 2 talks, and then also the panel discussion afterwards. Thanks a lot.
Thank you. Carsten, you will remain connected during this session, right? Okay.
I will, yes.
I have a curiosity. Do you have a plan, a scheme, a model to have feedback and follow-up of the training?
Yes, so I mean, interestingly, I can now look back to more than a decade of researcher training, and the fellows that we trained 10 years ago, they are now the supervisors, they are the group leaders at institutions all over Europe. The vast majority of these stayed in research, which to me underlines the enormous demand that there is for highly skilled experts in our areas. Almost all the researchers that we have trained are still active in the wider field of nuclear particle and astrophysics, and that to me is a good testament for the quality of the training program as well.
Thank you, Carsten. I don't see any question. Thanks, and please stay online and participate during the discussion. So I propose to continue with the next talk. Gert? Okay.
Hello. Oops. Hello, everyone. Nice to be here. So I'm Gert Aarsendiet. I'm a theoretical particle physicist from Swansea University, and I'm also director of ECT STAR at the moment. And I'll continue Carsten's presentation on the training of postgraduate research students, focusing a bit more on the details of what we do in our doctoral training center. Now let me see if I can manage this button, yeah. So my introduction slide is that over the years, there's been quite a big change in the expectation for the training of postgraduate research students or PhD students. Whereas in the past, maybe it's attending of PhD schools and internal seminars or external seminars. Now, especially in the UK, there's a lot of reporting to be done in terms of the type of activities that students are participating in. And I put a disclaimer here, and it's interesting that the previous speaker was also from the UK. So my experience is based on the UK system, where I've been since 2004. In the UK, PhD researchers are students, and so they're not employees, which is an important distinction. And also the research councils actually play an important role in shaping the training landscape. So a lot of funding comes with a lot of stipulations on what you have to do. So it's a disclaimer, because that obviously biases my presentation. So I'll briefly describe these Centers for Doctoral Training, CDTs, that Carsten also discussed. And one of the outstanding features there is this idea of cohort training. So whereas in the past, when I did my PhD, you do an individual project with a supervisor, and you meet I'm a theoretical physicist, so you meet very few other people besides your supervisor. In these CDTs, the cohort training is really essential. And then I'll talk a little bit about my experience in terms of the support, the infrastructure, and the sustainability that's needed to keep this going. And I'll end with a takeaway message and some of the questions that we can come back to in the discussion session. So in the UK, a Centre for Doctoral Training has a very specific meaning. It's a CDT has, say, over 50 PhD positions assigned to it. Luckily, the students don't all start in the same year. They're distributed over 5 cohorts, so about 10 students per year. And importantly, these are fully funded by the Research Council, so that's where the funding comes from. And in addition to the fees, the funding for the stipends and the fees, there is also funding for the center delivery costs. And that's one of my first messages that is really important. We cannot run, or one cannot run, a big training network like this. As an academic, you really need a manager, an administrator to take care of the planning and the finances and so on. So that's very important. These doctoral training centers can sit across multiple institutions or multiple disciplines. And the example that I will discuss is the center I'm the director of, which is the UKRI, which is the Research Council in the UK, CDT in Artificial Intelligence, Machine Learning and Advanced Computing, or AIMLAC. And so what I'll say comes from my experience from AIMLAC, but I think it's more general, and so that's why I hope it's useful. As was mentioned also in the previous talk, external partners are involved, both in terms of additional funding and in terms of training, but I won't say too much about that in this talk. So very brief about AIMLAC. It's across institutions, so it's 5 institutions. 4 of them are in Wales, and 1 is in England. And then in addition, there's something called Supercomputing Wales, which provides the infrastructure, both the hardware for computing, but also the people who support in terms of the training. I'll talk about this later. And maybe what is special of our CDT is that the research themes are extremely broad. And so we have students working on the area that we're working on, so particle physics, astronomy and cosmology, but also students in biology and health sciences, and students working on, say, more hardcore mathematical and computer science approaches in machine learning. Now, the fact that all these themes are present is because the emphasis is the common emphasis that binds the students is really on the use of machine learning and computing in all these projects. So that's the connecting feature. Now, just to show you, I don't want you to read these 3 slides, but we have 3 cohorts in place. And if you just look at the richness of the projects, you can see new physics searches in B&D, meson decays, active galaxies with Euclid, but also COVID research and patient health records. So the richness of these topics is well, I'm very biased, but I'm very proud that we have such a diverse group of students working on these wide range of projects. Now, each student works on their own project. Obviously, we don't expect a student to work on projects in physics, in health, and in computer science, but the connection goes via the training. And the cohort training goes, I would say, far beyond what you usually do in a small group, a small research group, or within a department. And so we really do a lot of effort to develop this so-called cohort feeling. And in practice, it means we have about 5 events per year where the students and some of the supervisors and some of the external partners come together. They are, say, 3-day-long events, so that's not a reason why you need a manager and administrator to plan all of this. And by bringing these people together, the students together for 5 times a year, you really build this common ground and this cohort feeling. At these events, the emphasis is on the transferable skills training, computing, best practice, and so on, and not so much on the specific research domains. Although, of course, we always like to have 1 or 2 presentations that highlight the science. Now, to deliver this is non-trivial, I would say. There's a number of things to flag up here. First of all, the time it's needed. It's a number of events per year. It's not one-off. And then second of all, there's a repetition because it's 5 cohorts. It's for a number of cohorts, so you have to do this a number of times. And of course, you need to have the know-how as well in terms of who delivers the training. And so, in my mind, this is completely orthogonal to a one-off PhD school. It's very easy to get lecturers, to invite lecturers to come to a nice location somewhere in Southern Europe and talk about their field for 1 week. Here we have to do it multiple times per year and for several cohorts. So it really takes, a lot of a slightly different type of person, let me put it like this, to really implement this. Now, the way we do it in our CDT is via research software engineers. So these are people who are employed by Supercomputing Wales in our case and the university. And they actually have these skills and also the time, say, to really do these training sessions over and over again, so to say. And of course, once these training sessions are developed, they can also offer them to other students, say, in the university and in other institutions. So this is something I want to highlight, that as an academic, we often don't want to do the same thing over and over again. That's why we're in academia. We get bored very easily. Here you actually need some kind of structure to repeat your training multiple times. As an example, here is some of the training that is given. So all the students in our CDT take this training. As you can see, it's not related, it's not domain specific. It has to do with computing and machine learning and best practice and so on and so forth. And so the hope is that all the students get skilled up, so to say, in these type of areas. Now, slightly switching topic now. Of course, during COVID, we had to do all of this online, like everyone in this room here. So people learned a lot, and we're now very skilled to give online training to cohorts. And as an example, I'll give you an example from ECT STAR, and a talent school on machine learning applied to nuclear physics. And this school was run at ECT STAR twice now by Morten, 2 years in a row. And this is just an example where once you know how to deliver something, say even remotely, you can do it over and over again if the supervisor is willing to do so. And that's just an example of something that's very accessible to people to join in. Now, there are lots of initiatives everywhere in terms of online training and online materials. And the thing that was raised recently is, should we not curate all of this information and collect it together? And so there is this idea of maybe collect an online training portfolio, and Maria Paula Lombardo is very much in favor of this. It would be a shame if we lose all of this material, even though, of course, it's collected at each university or each institution. And so there's a proposal to have a LAVA as a Lattice Virtual Academy that acts as a hub of all the online resources available in our common field, which is lattice field theory. And we're currently developing this as part of Strong 2020, and this will be hosted as a virtual hub at ECT Star. And this is something that we can potentially discuss to make this kind of training more widely available and easily accessible as well. A few thoughts then about things that came to my mind when I was writing this presentation. So in my view, and also I think in the view of the students, I hope, is that the training across the different disciplines is actually very stimulating. We're very much used to being in one topic and talking only with the people who do exactly what you do, but it's actually really interesting to find out what other people are doing and what kind of problems they encounter. So I think it definitely enhances the PhD experience. The thing which I think is important is that the training is ongoing. It's not a one-off. It's not a PhD school where you go to, but the training is taking place throughout the PhD program, and that really allows this cohort to be formed and the people in the different disciplines to make connections. So one example, for instance, is that, as I said, most of the students have some element of machine learning in their PhD, and they're very happy now to share methods, say, that are popular in astronomy and share them with problems in medicine. Whereas if you meet only once, you would be maybe more reluctant to do so, but if you meet over and over again, you can share this information much easier. Because the students are talking with each other outside their own domain, they actually pick up a lot of skills without maybe realizing it. And this is important for communication and collaboration. And for instance, when you have to apply, say, for fellowships with a very broad panel, you have to be able to communicate more widely than in your own field. If you want to change disciplines, we talked about knowledge transfer and also employability. All of these skills can be, all of these applications can be trained in a way by meeting people in a very broad cohort. There is a but, of course, and that's that it actually requires quite some investment. It's not something that happens very easily. And so you need dedicated resources to deliver training, especially if it's across disciplines. That is to say, it's not owned by a specific department. It's not, say, a physics program with a little bit of medicine on the side. It's really shared across. As I tried to say a few times, you have to deliver multiple events per year for multiple cohorts. That requires a lot of stamina to keep going. And then finally, we want to, of course, all these resources that are collected, keep them available in some kind of coordinated manner, so they are available for others in the broader community as well. And then my final slide are some open questions which we may discuss later. Well, in the UK, but I'm sure everywhere, there's a lot of investment in undergraduate teaching and student experience. In fact, everything we do in the UK is driven by student experience and trying to please the students as best as we can, the undergraduate students. I'm saying it now in a slightly negative way. But and so one question is whether we should think about PGR student training in a similar way. Should we basically ask our universities and maybe our research councils to invest more funding in the training in the same way that we expect that our undergraduate students are trained or educated in the best possible way? And then some training can be done very well locally, but some aspect of the training may be done across institutions, maybe national institutions, or maybe international facilities, such as ECT Star, for instance. And then in the long run, there is a question of who is responsible for the sustainability if we want to keep going these type of activities. Okay, that's all I wanted to say. Thank you.
Thank you very much indeed. I appreciate, because it is a nice example where we learn how to, the benefits of joining effort from different universities. We heard also about the but. But it's a very interesting example. I think many of us will have a lot of things to think about after this presentation. I know that there are also other joint university efforts in other countries. I don't see Laurent here, but I know in France there are already a couple of examples. Yes, joining is efficient. So I think we have a short time for questions if you have. Yeah. Bon, maybe later during the discussion, since you will be around, right? Okay, so thanks again. We move to the last presentation and then get ready for the discussion for the roundtable.
All right. Oops. Can you hear me well? So I am Rebeca González Suárez, and I'm coming from Uppsala University. This is actually the first time I give a talk about outreach, even though I am the outreach coordinator in Atlas, and I have been doing outreach for many, many years now. And against good judgment, I have put a lot of transitions in this presentation, so I hope everything works. So let's see. Very good. Oh, it seems to work. All right, so when I was asked to prepare this presentation, I went through a few of the different documents that we have in the whole set of nuclear, astroparticle, and particle physics, and I decided to focus in the one that I am more familiar with, that is the EFCA, the 2020 update to the strategy for the European particle physics. And there, in number 7, as you have in there, oh, I think this is the problem, right? Okay, I will not do it. So when we discuss the environmental and societal impact is when outreach come to play. I have put in bold the parts that I'm gonna touch during this presentation. I'm not gonna read it out loud. So let's get to it. Good, it works. So the first stop is public engagement, education, and communication. Okay, this is very important to the scientific activity. It's highlighted as such by EFCA. And oops, yeah, very good. And it is important to highlight that indeed, public awareness and understanding of particle physics is really crucial for our field. And it doesn't matter how you spin it. It is important because fundamental research depends, at least largely, in public funding. The public pays for it, so the public should know about it, which I think is a pretty fair comment. And because they pay for it, they should probably take ownership of it. And I think this is something that we could all benefit from. Very good. This also, of course, applies to stakeholders when it's not necessarily the public that is funding. Very good. So public funding depends directly on public opinion. So we certainly need the support of the public. It's something that we cannot really live without. And public support and ownership of fundamental research means that we will have a healthier and wealthier society. That is really the case. This is going to enable us to produce more fundamental research, and it's going to also guarantee that the field can continue, not only by supporting it and giving possibilities for that, but also by getting us the next generations of physicists that are going to just take over after us. All right, so this is something, and I wanted to stress this out here, even though I took this slide from somebody else, or at least the idea, is that right now this is more important than ever, right? So we've been having a little bit of a deluge of anti-science movements all over the place, especially during the pandemic. You can see here in this latest paper that I put there, in which we have seen that it's actually quite important and that the anti-science movement is really becoming larger, more vocal, and it actually can be really problematic in general for the people and also for us, right? Very good. So focusing in collider physics, that is what I know about because this is what I work on. CERN and the LHC have been subject of conspiracy theories since always. I mean, you are all familiar with that, right? But the growth of the internet has made them all more mainstream. So we have an increasingly vocal cadre of social media users that do not trust scientists. So scientists are perceived as elitist, members of the establishment, mad that seek control of the masses, directly evil, connected to strange things like aliens and stuff, playing God, and of course the most unrealistic of them all, that is getting rich. Good. So anti-science tendencies can be motivated by many things. It can be by negative experiences, and in fact it can be a very unpleasant secondary event of just the way that we humans process information. But also, research shows directly that it can also be something related to certain political agendas. In this case, for the very first point here, outreach can help there directly. We can show the people who scientists are. Because we're all scientists, we're a lot of people, it's not really so hard for the general public to meet us. And in the last point, outreach can equip the people to be able to discern these kind of things and make proper educated decisions and understand what is the science that is out there. Very good. So common negatives for outreach that I have heard. First one, it is useless. I hear this all the time. So I insist on the point that the public pays for our research. So it doesn't matter if you think that this is not working out, it's our duty. It's a part of our scientific activity. Another one is we only attract those that were already interested in the first place. Well, so then we have to do outreach better because those didn't need it. Then the last one is that it takes time that could be used for research. And yeah, my answer is yes. But the same can be said about paper writing, and many of us, we were discussing this morning, many of us don't like to do that, and it's a part of the job, so we do it. All right, one point that the strategy document has relates to have adequate support, and I think this is really crucial. Not all the countries in Europe and in general in the world recognize outreach as part of the scientific responsibilities, and as such, they don't fund it. So often, as I said, it's not funded, but also not supported and not valued. It tends to be an activity that doesn't carry the same level of status than others. It tends to be voluntary work that comes at the expense of our free time, and it's not like we have a lot of that. And it's often done by people that already take other responsibilities, that feel like this level of commitment to the cause. So while we have obtained a scientific education, or at least I hope so, right? Many of us don't have a science communication education. This is something that is quite important. It seems like it's easy that everybody can do outreach, but it's not necessarily the case. I mean, we are not all natural-born communicators, and it's fine, but we can learn. So without training and advice, we are amateurs, and our efforts can actually be counterproductive. So it's something that we need to think about. It's like not just because we want to volunteer, we're going to do it well, we need to put an effort on this. Okay, we need to think about what we want to achieve. So it is important to establish them best practices that I think has been a common theme throughout this seminar. All right, another point is the engagement between scientific disciplines. I mean, this makes sense here, right? I mean, this is the right forum to discuss this. I think I don't need to convince you of why this is good, but of course, overlapping challenges that we all have represent opportunities for us. Specifically, when we're talking about outreach, we can avoid reinventing the wheel every time for every discipline. We can all learn from what the other people have been doing. We can adapt formats. We can learn from mistakes, because those are also made. It allows us to focus efforts and resources, organizing events in common or training in common, these kind of things that we've been discussing already this afternoon. It allows us also to give a cohesive message and a greater context, and context is really important, especially when we are doing things that are extremely specialized. It's good for the people, but it's also good for us. It's an opportunity to have common support platforms, common trainings, as I said, and centralized resources. And in particle physics, for example, IPOG is a very good example of how this can be something really good. Science is a competitive environment in which resources are scarce, but I don't have to tell you this also, but we should support each other, right? Scrutiny and skepticism in science is something that is healthy and is necessary, but the public doesn't necessarily understand this. So it's important to show a united front, and it's important to show the people that we can scrutinize each other, but it doesn't mean that some ideas are not valued or whatever. So I wanted just to put this last here, that this is not a zero-sum game. We are all in this. And when science suffers in one side, we are all suffering in all the sides. This is unavoidable. Very good. Next point is the work with educators and authorities. Again, this is a part of the topic around this afternoon. So it is important, of course, to have a basic knowledge of fundamental particles in the regular school curriculum for us, because we, of course, want to be as mainstream as possible, and it's important for the people to understand also the fundamental matter. This will increase, of course, public awareness and understanding of particle physics. And it will link back to the first slides about the engagement and why we need the public support. The pandemic, as I said before, has revealed the importance of preparing students and everybody to critically evaluate the conceptual foundations and real-world impact of science and to understand the scientific method that I think is really, really important. All right. One slide about outreach formats that we are all familiar with, just to think about the way that we do outreach around here. So, of course, there are classic public lectures. We also have like a public guiding of facilities on the style of the open days, exhibitions, science festivals, events that require a little bit more effort than that. Then we can have informal activities like Ask a Scientist or Science Cafe or the Pint of Science. We have many of these things, Science Slam. This is very nice, especially for a certain kind of audiences. Then there are the citizen science projects that include also open data exercises, like the master classes also from IPOG. Then we have schools and high school visits. That is also a very classic way of doing outreach. And most of these actually require this pre-existing interest from the participants. So it links back to one of the negatives that people have about outreach. Then we also have, of course, printed materials, posters, brochures, magazines, science magazines. There are even outreach magazines online. And of course, the press, because it's actually quite important to engage with the media. That's a way of directly connect to the public. Very good. Then we also have other things, right? So this is an example of the gingerbread village that Atlas did this end of the year to celebrate the season, right? With a new small wheel. Also, I have the Lego model of Atlas in particular that has been extremely successful. It comes in different sizes, people love it. And even things like the coffee cups during the open days at CERN are ways of doing outreach that can allow us to bridge with the people. So there are extra ways to approach outreach. All right, so then let's meet the public, okay, where they are. And the public today is online. Then the importance of websites, I think, is very clear. I think everybody has their website for the different collaborations and so on and so forth. But where people really are is in social media. Okay, so 4.48 billion people use social media today. And this means more than half of the population of the world. So this is a lot of people. And if I go to the statistics of the different channels that we have of communication in the Atlas experiment, well, the number has increased since 2020, that's important. In March of this year, the atlas.cern website got 71,000 visitors, which I think is fine. I'm happy with that number. But then if you go to Twitter, we got 242,000 impressions. So this is like an order of magnitude larger. So it is something to think about. And even if you go to Instagram, that is, let's say, less mainstream than Twitter, we still got 49,000 accounts reached, which gets very close to the mailing list, to the website. Which means that actually social media can help us, first of all, reach people that may not have a pre-existing interest in the topic, and it's going to be a lot more people. So it's something that we cannot understate. So the problem when you go into social media is that you need to tailor the content. So not all platforms are the same, and not everybody is the same. So I'm going to put a couple of things that are specifically successful for us. So we have, yes, Twitter threads that are really useful. You can give quite some information in Twitter, even though the format is limited. Then we use YouTube, especially for streaming things, long videos, to approach with the people. There is also a connection with the chat. I know that this workshop, for example, is also in YouTube. Then in Instagram, we tend to use the stories also that live for a short time but allow us for a good engagement. And then recently, we have also joined TikTok. But don't ask me about it because I don't know much about it. But it's short videos and also streaming. And this already in this point that is about social media, we have different audiences in here. So for example, Twitter, our average age for the audience is between 25 and 34. And when we move to TikTok, it's between 10 and 19, which is actually quite an important area of the year. It can really allow us to get some people into the field, right? All right. And because not everybody is the same, we have this different tailoring of the different platforms, but sometimes it looks like scientists are. We're going to discuss diversity during this workshop soon, But I just wanted to make a note because I think outreach is important for this. So this is a weak point of physics since its inception. And we all know that monocultures can create mono approaches. So if we all come from the same place and have similar experiences, we're going to solve the problems in the same way. We don't want to do that. People with different experiences and with different circumstances provide additional things, innovation and creativity. And of course, it limits our talent pool when we only fish for one area. So this has deep root causes. I mean, outreach is not going to fix this, but it can actually help. Okay, so it can be an asset that we can use to approach to groups that are not necessarily so close to science. Good. So this is the last slide that focuses a little bit more in diversity and inclusion. So there is a general push that is obvious, right, at different level, from locally to international, to bridge this science gap. So more and more often, we discuss how we can make our results more accessible, how we can make our research more accessible, and we try also to be more welcoming, right? We've been putting an effort in closed captioning of our videos. Exhibition materials, for example, for the visually impaired tend to be available more and more often. Then we have even the possibilities of remote working and remote attendance to things that have been like boosted by COVID, which is, I think, a welcome side effect for that. And we are aware of code of conducts. We actually work to set them in place, but much more can and needs to be done, and it will not come without an effort. So this was my last slide. Thank you very much for your attention, and there's a little credit there.
Thank you very much for this very well organized and very clear presentation. It helped a lot during the discussion. The only comment I have, I would kindly invite the members of the roundtable discussion, because we didn't have any talk. Your talk yet was about was entitled education, but finally it was training. But this was fine. The only thing I would like to add about education, as I was speaking with Cybrand during the coffee break, that in the strategy, as you were pushing hard 2 years ago at Van Honef, to have this particle physics basic things included in the education. So it's not a comment, it's an invitation to think about it, right? And it looks like it's not easy, huh? Okay, so I'm kindly inviting you to start, and you managed to get organized, and you have a, okay. So, Michael.
Okay, thank you very much, Kalin. I hope one can hear me, and I hope that Carsten will be back behind us. Just here, there he is, so he's on the screen. Yeah, let me first introduce the other participants here on the panel. You already had the introduction of Carsten, Gerd, and Rebecca, and there are more people, and actually we managed to cover as well all stages of the careers, all fields, all expertises. We have a large scope of the topic. There is training, there's education, which we didn't have yet in the talks, and there's outreach. And we had so far one accelerator expert, 2 particle physics experts from theory and experiment. So the next one is nuclear physicist. It's Pepe Arias. He is the coordinator of an Erasmus Mundus Master in Nuclear Physics, which happens in France, Italy, and Spain. And actually, the members, the participants, go to all these countries in this Erasmus Mundus Master. And one of the participants actually is at his side. It's Michelangelo Traina, who participated actually in this nuclear physics master, and then he went from nuclear physics to the bridge to astroparticle physics, because as you all know, the dark matter is the bridge between nuclear physics and astroparticle physics, and he does his PhD on the Lhc Experiment and is at the Sorbonne in Paris. Then next to me is back to particle physics is Lydia Brenner. He is she is the representative of the career panel of ECFA, and has been till a week ago a CERN fellow, and now moved to NICEF, but is still in particle physics experiments, and also very well concerned in training and education there in this ECFA panel. Last not least, I'm Michael Kobel. I've been in the IPOC group, which was just mentioned by Rebecca, for 20 years. I just left it last year, so it was maybe the longest term anybody had there. I was chairing them for several years, and actually it was me and Christine Sutton 17 years meanwhile ago when we kicked off the international master classes. Just we wanted to do it for 1 year, and then meanwhile it's 17 years. I'm in Germany the head of the Netzwerk Teilchenwelt, which is actually very close to this conference, because we managed to do education and outreach across all disciplines. We do particle physics, we do astroparticle physics and nuclear physics, and we are funded by our ministry, which is also a big step, so we can talk about that. And in addition to that, concerning to education, we really go into schools, we develop materials for teachers, we do teacher training, and also this is something we can talk about. And since 1 year, I'm now also on the teacher education, because I'm the vice director for academic affairs of the Technical University in Dresden, where I'm obviously responsible also for the teacher education at the university, not only in physics. Yeah, this group here and this round table is a huge opportunity, and I hope we can really take advantage of it, not only here on the panel, but also in the audience, to have exchange. As we just heard from Rebecca, it's a very important that we don't have all to invent the wheel again. So we have the opportunity today. Of course, we have to find out a bit, maybe discuss what actually are our duties, our role, but also what are the aims of these three fields. And I will try to shape the discussion in the three topics: training, education, and outreach, one after the other. Maybe a bit less on training, since we had 2 talks on that. And then it's also about you. What is your need to embark on these issues? What support structures do you need? And also there, Rebecca had quite some items on her slides. And finally, at the end of the day, or at the end of the round table, we want to try to get a take-home message, and maybe it's not one message. Maybe, as also Rebecca says, we are from different nationalities, different backgrounds, diverse. We should also take advantage of this diversity, and maybe each of you will take another different take-home message. I will just start that you learn the participants here a bit better with a very, very short statement before we go into the discussion, namely the question: what was your key experience in the fields you're in, training, education, outreach, and which statement, testimony you can then deduce from that experiments? And I just start with Carsten, because he is remote, and then there is no danger to forget him. So, what was your key experience in training which shaped your effort?
Well, I think it's mostly looking back at the training that I received and the things that worked, and also importantly the things that did not work. So what are the elements that I now know are important for the development of your own career, which simply didn't exist at the time as part of structured training programs? So for example, exposure to the industrial sector was not considered as an important element of postgraduate or postdoctoral training programs, whereas now there is clear much more mobility between sectors, all the way to very senior levels of researchers who make transfers between the academic and the industry sectors. So it's really, I think it's a reflection on what worked well in your own education and also what didn't work well, and then trying to shape that into something that works better for most students.
Okay, that's a good thing, and you're already doing that, as we heard. So I go to my left, to Lydia. What's your key experience?
Thank you. Okay, so I'm here on behalf of this early career researchers panel, and we discussed this within the panel. And one thing that became very clear is that it's not the same for everybody. So we heard today 2 talks about networks that were set up, but there's also a lot of students or other early career researchers that just don't have the access to such a network or aren't included in one. And that especially if you are not in one of those particular networks, it can be very hard to find out about training opportunities, to get funding, to get time, to actually be allowed to do these things, and to get the opportunity to do networking with other people, which is also of vital importance for any kind of training. It's not just the lesson that you learn, but also who you get to meet, and the talks in the coffee breaks where you learn a lot.
Thank you, Lydia. And then I give the word to Gerd.
I said most of what I want to say in my talk, but I think for me the key insight is actually really interesting to work with, say, PhD students in different disciplines and find this common ground that is there. And this goes back maybe to what Carsten said as well, is that when I was a student, this was not available at all. It was all very focused on your own area, even in physics. It was focused, in my case, on theoretical particle physics only. And so it probably comes with the fact that one gets older, and that it's more interesting to look in a little bit broader environment.
Thank you. And Rebecca?
So, I mean, I have an experience to share that is, in fact, a lack of experience, right? So when I was a student in the university and I was studying physics because I care about it, I was doing fundamental physics. It was the time when the internet was starting to exist, right? But still, I didn't learn about CERN until my last year in the university. So I could never really properly apply to things like summer student projects and stuff like that. So to me, nobody has ever done outreach. I had no idea about the options. I had no idea about any kind of interdisciplinary research. These things were so alien to me that I learned them much later, so I couldn't properly plan my career and see what I actually really wanted. I got lucky because I really like what I do, but it's in fact what connects to what Lydia said at the start. So it's important to see who actually knows what is available and who doesn't. Because, I mean, I was an example of somebody that doesn't. So
this could actually be already a take-home message. We have to give the options to the young people, the younger, the better in high school. They already should have a view what the options are. Pepe.
Thank you. So I will talk here about my experience as coordinator of the One Erasmus Mundus master degree in nuclear physics. So it's devoted specifically to nuclear physics. And my experience in this project that has involved 7 universities and more than 30 associate centers all around the world is that this kind of projects is very useful. So it's hard to start working with this, so many people, so many different universities and centers, but at the end, I think we have to go in this direction, not only in nuclear physics, but also in the other fields. And also my experience is that if you give a good background in whatever, in our case in nuclear physics, for the students it's very easy to go to astrophysics or dark matter or any other field in which you are involved. So one example is Michelangelo.
Thanks a lot, Pepe, and last not least, Michelangelo.
Thank you, Michael. So yeah, I mean, for me, the key experience was the joint master degree that Professor Iris coordinates, NUCFIS, relevant for education and training in this roundtable. So this was a very positive experience overall. It was a lot of work also from the student side because we were going from a country to the other in a matter of 2 years, basically. In general, I think the most important thing is that it put us in an excellent position to become researchers. So there was 2 key elements to it. The first is how much actual research work we were able to do over the master. And I know that one will take this for granted, but in my experience, that is not necessarily the case, and of course it's critical because if we are to become researchers, we must have some sort of preparation before starting our research positions. And also it can make us understand whether we actually want to pursue that career. The second key element was networking because the master has so many partner institutions, and so basically we were doing so many guided visits. We could request internships in these various institutions, and I think this is fundamental because it creates jobs and so research opportunities, but also because it lays the grounds for future synergies. So I think these are the 2 key elements that were particularly successful in the master, and I think that they can be reinforced or their support structures be adapted to make for a competitive generation of European researchers.
Thanks a lot, Michelangelo. So you have an impression of the participants. Maybe I share also one key experience which I had is also this synergy between the efforts we are doing research, education, outreach, which I realized when I talked to a master student who took part in an exhibition we had when the LHC started. And this master student was completely surprised that there is public interest for what we do. So this notion that what we are doing is a cultural issue, how does the universe work? How did it come up? How did it, what was the cosmological process? Why are we there? Where do we go to? And how does it all work? Is a matter of curiosity of the whole society. And this is maybe not clear enough to all people who start research. And that happened also here. This came up, and this will be also a question to the training people. Maybe the first question to the training people I'm having is that I saw in your course a lot of important topics of training which make you a good researcher or maybe also very good employable for industry. But is there also this component, how do I communicate soft skills or other soft skill? How do I become to be a good team leader or things like that?
Yeah, I did not list everything we do indeed, but there's also training on presenting your research, talking to a lay audience, grant proposal writing. So it's kind of staged during the 4 years of the PhD. That initially you talk about, well, initially it's more the technical training, say, and then as time goes on, it moves more to talking to the public, and then in the final year, more the leadership skills. So this is all indeed embedded in the training program. It's very important, indeed, all of it, yeah.
Good to hear that. Maybe my next question to Carsten, because you really and very convincingly told us the profit if you bring different communities together. You mentioned it might take a week, but after that they are there. And are there any communities which do not yet talk enough to one another? Should the people here in the audience or all of us start an effort where you think there is potential?
Absolutely, yes. I think there's definitely not enough communication between different disciplines. So the areas that I was directly involved with are the laser and accelerator community, then the medical accelerators community, so the oncologists working with the people developing the accelerators for beam delivery and the detectors, and also the data science community in combination with astrophysics, nuclear physics, particle physics. And you would think that there is already a very good link between all of these, but really when it comes to the details, you will find that we are sitting all on our individual islands, and we are not normally moving away from these islands a lot. A meeting like the one right now doesn't take place that often. Most of the time, it's highly specialized meetings within just one community. In addition, even within that community, my view is in order to do the best research, you need three different ingredients. First, you need universities, because you need academics who are the crazy inventors, the people who look into the future and sometimes even too far into the future, but who have to come up with crazy ideas. Secondly, within the same community, you need research facilities. So you need the large-scale infrastructures, the accelerators, the detectors that a university alone would never have. And thirdly, you need industry, because industry pulls the academics back to the ground. They make sure that we have a grounding on something that can actually be delivered within a reasonable time scale and also budget. And if you bring these three together, and that's within one community, that's not even the additional link to another community, then I think you can really drive science and innovation.
These are very important points, and I think everybody here who is organizing PhD school, postgraduate schools, maybe he or she can approach you to get the experience how to bring industry in, because this is really something which is not yet very often done. And I think for the employability and for the connection to industry, this is a very, very worthwhile effort. You mentioned just this international large-scale structure, the access to them. Maybe I can ask Pepe, who is really already the expert in international education and training programs with your Erasmus Mundus. I think Gerd also asked this question. Do we need more international training facilities hosting these trainings?
I think so. So in our master, we have, as I already mentioned, many research centers. Many of them are represented here. People, CERN, all the national centers in Italy, GANIL, CIEMAT in Spain, LIP in Portugal. So most of the European centers, as some centers of America and also in Africa, are associated centers of our master. And the compromise they acquire when they join the master is to propose topics for internships and to receive students during summertime or a couple of months, a small period of time, for doing internships, and also proposing master thesis topics to be developed in these centers. And I think this is extremely useful. So all the students are very, very, very happy about this program. And I think that also the research centers are very happy with these young people collaborating with them. So I really think that we should move in this direction. So we have to go to cooperation and internationalization in all the programs for young people.
So your recommendation would be just to approach the research centers, and they are already open for that.
Yes.
And
no, my experience is that usually the research centers are very open to these initiatives. Yeah.
That's good news. Okay, since we had a lot of on training, I propose to focus a bit more on education and outreach. And for education, I want just to stress or to try and define and maybe then also open the audience a bit with all the questions which Rebecca had. For us, I think, but it's not yet, as we also have seen here, not yet common definition. The education we should aim at already starts very early. It starts at high school. Actually, that's what we do in Germany, and it's also done in other countries. I know that astroparticle physics has high school project, HiSpark, or UCA in Italy, HiSpark in Netherlands. Particle physics has it, and particle physics, astroparticle and nuclear physics has it in my network, which I'm leading in Germany. In France, there is Science à l'école, so I guess all of us already do that. We might want to share experiences. There is not yet too much exchange on that. Maybe we need conferences and workshops on that together with educators, which was also mentioned by Rebecca. But first, let me tell you what we are trying to do. What we are trying to do is having both the broad public, the young people there, that they come into contact with science, and it's rather, it doesn't matter which kind of topic it is. So not each experiment needs its own education school material. That would be not optimal use of the resources. And that was also in the outreach talk. We are all after getting the scientific method across. We are across getting the nature of science across, and we just should pick things which we experience are successful. And successful is, on the one hand, the fascinating things, the big picture, the universe, the cosmos is already always a matter of fascination. And on the other hand, the everyday experience, which also came up here in the panel. If you have medical applications, we, for instance, have just in Germany developed a masterclass for cancer treatment, for optimizing the particle beams to meet the cancer, which is also bridging a lot between nuclear physics, accelerator physics, particle physics, and medical applications. And so this is one thing to really get the message of science across to the broad young public. But the other aim of education is really to foster talents. So in this first step we try to identify the young people who are interested to enter a stage program with additional offers, workshops, things they can really become active. They can do their baccalaureate thesis in the research groups, and the research groups actually already profit from that, and then we continue to accompany them into their studies at university. And interestingly, and this is the diversity issue in this field, and this is an extremely exception for Germany, we get 50% females. In the normal physics studies, we are hardly above 20%. So this is really a big effort which is successful if you go in with the role models into the school, with the young role models, and you bring in as well female and male role models, it seems to work. And this is maybe one message I can bring across. And then the other thing is to really get the interactive part. They should work on real data, get their chance to do research. We have astroparticle physics detectors which we build, which can be borrowed by schools to do muon measurements with different detectors. As we saw, these can be used. Yesterday there was a great talk that they can be used to analyze volcano activities. This is also already something which is connected to everyday life. And maybe at that point, of course, we have the advantage in Germany that this program, after a long discussion, is now really funded. So the outreach, education, and fostering of talents, participation of the public is regarded as integral part of the research. It's in the same funding calls than the call for research in nuclear physics and particle physics. That might be a topic for tomorrow's session with the funding agencies to see who else does it, what are the experience, and maybe by that convincing the others also to do that. And just to give you an order of magnitude, it's 1% of the funding in Germany. So it's really, you don't take away much from the research, which is often the concern, all this outreach business, but it's just 1. And you can do a great lot of good things with that. At that point, I would like to open the floor a bit to the public here, to the audience, which concerning education and outreach. Do you have enough support or exchange opportunities if you want to embark on that and take up what Rebecca said and what is in the ECFA roadmap, that it's actually a part of the duties of us? Do you have enough support, or what would you need to do that? That would be a question for the audience.
Well, somebody has the courage. Maybe we should point that IPOG has a memorandum of understanding, and member states are contributing. So if Germany, I'm jealous for the Italian budget for outreach. So other countries, they don't have. Okay, so it's important to know that.
Yeah. Yeah, there's.
Okay, so in Serbia it's half and half. We do have some support for organizing master classes and things like that. Our government also started to support some educational programs with CERN, actually allocating. It's not a large amount of money, but it can support some visits of some teachers every now and then. So there is support for that. But like general outreach, it's, as I said, it's half and half. We have something that is called Center for Science Promotion. They actually do get a lot of money. It's not just physics, of course, it's all the science. But somehow it's still on individual basis. So people that are interested in outreach, they will involve themselves into that, usually taking their own time, as Rebecca pointed, volunteering, and many people will just not. But one thing that I wanted to mention here that is not really related to that question is that we really need to work much more with science teachers, not just in high school, but also in elementary schools. Many programs for science teachers are for high school science teachers, but I have seen examples that we had elementary school teacher bringing her students to masterclass, begging if they can participate because she was the one that wanted it. But the problem is that in my country, I think that at least half of the science teachers are not really interested and they don't spread the knowledge. So I just learned from one of our science teachers that her students know about CERN, but in her school, and that's one of these schools where you get extra education in math and science, students from other physics teachers, they actually never heard of CERN in school. And first impression is done by teacher in school and not by media or something like that. And media, you still need to click somewhere to get that information. Science teacher is there because, you know, you need to go to the class.
Okay, you say we need to spread better the word to more science teachers as a multiplication factor to young people.
For school teachers, I think it's not only to spread the word, but also provide them materials they can use and educate them, because in our country, I know that in most cases, they do not know sufficient to use these kind of materials.
Mm-hmm. Yeah. There I really can report from the experiences we had in Netzwerk Teilchenwelt. It took many years. We had a lot of a series of workshops with educators, with science communicators, and also with the didactic experts. So the university didactics of physics was from the beginning on board, and this was also on Rebecca had all other transparencies. this connection to didactics may be another take-home message for all of us, at least for all of us who are at universities and have their didactic departments. Do we know these people? Could we do funding applications together? And this is what I actually did. And as to soon, if this is on the horizon, that I can say, look, we do a funding application and you might get another PhD student, they are on board. And then it was a hard way for me to learn how I really have to break down things on a level that a teacher not only can understand it, this is easier, but that the teacher can teach it at school. This is much more difficult because you have to do the didactic reduction to the level of the students, and this was a hard way, but a very successful, and maybe also here we can have an exchange over the fields. There are efforts also going on in nuclear physics there, and in astrophysics, people in DAISY and Cosmic at Web and things like that are on their way.
Yeah, we are almost at the end of, we have questions there. Let me do it.
Thank you. Just maybe two little remarks.
First, concerning the young people in the field, especially its PhD students, I think it's, as you mentioned, it's very important that they get more experience also in outreach, in maybe also contacts with industry. But on the other hand, at least at DAISY, we are bound with strict regulations to care for finishing thesis within 3 years. Mm-hmm. And this is certainly a tension is building up there, because in the end, the science results is the most important things for the further career of the young ones. And my limited personal experience with high schools is also that even on the other side of the schools, formalities become more and more strict, more administration work on the teacher, so they have less time to invite us as scientists as role models. At least this is my limited impression from Hamburg area. Mm-hmm. But my concrete question is, I think we need to communicate that PhD's thesis might not have to strictly be finished within 3 years to allow for such a broad education of the students.
Mm-hmm. Yeah.
At least at my university, we allow people 1 additional year in their PhD program if this year is spent on teaching and outreach activities. Yeah. And this is partially to alleviate teaching duties of the staff internally, but also the outreach and teaching at high schools.
If I can comment on this, it's interesting actually, because also in our doctoral training center, especially supervisors say we want to get on with the research. We think all these training activities just take away the time from doing research. And so the program I described is actually a year longer compared to the standard program to allow for this training to take place, and also the 6 months placement that Carsten mentioned. But still supervisors are saying, no, we just want to do research. So that's it needs a bit of a mind change somehow to accept, to include all these other activities.
Yeah, hello. So,
yeah, there's a question.
Yeah, so I'm 23 and I finished my bachelor's a year ago. So on a scale from general public to researcher, I'm closer to general public. And my question is that, would it be possible to create internships with people who, are in their master's or PhD, who are closer in age to people who maybe are using social media and would be then interested in going into research further down in life? Because it's where, for example, like you could, collaborate at maybe as a master's student with actual researchers to create media or create like videos or papers, more popular science papers that, could outreach to these people, because in my experience, it is a bit lacking, like creating interest in the physics field hasn't been very successful, or it's not as well done as maybe in some other disciplines like chemistry or biology, when you look in like statistics in universities and such. Yeah.
This is a very good suggestion. I have noted it down, this internship of social media. Yeah.
Carsten.
Yeah, I just wanted to add to the comment about the time requirement in order to do outreach or to help education in general, because it's not an exclusive problem to PhD students only. It's also a very real problem for senior researchers, because I think many of the things we have said in terms of the importance of working with industry, reaching out to schools, the development of teachers that was mentioned earlier, they all take very significant time. And that means there's a requirement to acknowledge this, and also by line managers to make sure that they free the time, sometimes of senior staff, to actually do that. We can't demand that we do all of these things and basically expect them to happen as a hobby. So when we have our annual professional development review meeting, and I'm speaking with all of the professors in my department, those that are doing outreach, I give them a reduction of teaching duties, or they have lower expectations in terms of the level of grant income that we are planning for the next year to really free those time. And it does take time. Just to give you one example, because today is Star Wars Day, so I guess I have to mention it. Over the winter, I wrote 3 articles for Science in School, which is a journal targeting high school teachers, explaining accelerator science and particle physics on the example of Star Wars. And to write these articles was fun, but it did take considerable time. And it is important that this is acknowledged by the administrative system. So it's really beyond PhD students. It also applies to staff.
This is a very true, and this corresponds, or this is a message to all people in the audience who are in a position high enough in the university, doing this yearly conversations, or in my university is not each year, but every other year, where we actually really do the same as you. We look at research, we look at teaching, but we also look at this third mission, and this third mission is as well education and outreach, but it could be also patents, it could be the one topic we had in the last session.
Yep, but we never addressed the her comment. But she had a comment and we never addressed it. I mean, when she discussed the internship for the young people, and I think we should.
Yeah, we should. Yeah, I was just addressing thumbs up.
Because I think this is actually a really important comment, because those opportunities already exist locally in different places. And what we need to find out in the way that we do outreach is to put together those opportunities with people that are interested on them. So this is a really important point, because they do exist and you can find them, but then you need to know how. So I think it was really, really an important point that you brought up.
Yeah.
Sorry.
Okay. Thank you. I really like the talks on education, outreach, and training, especially the one by Dr. Gonzalez on outreach, because it's something I relate to. So in my short time in science so far, I have been in situations where the public at large has a negative opinion on the research that a particular area is doing, even if the research is on at the very basic level can solve the problems of the public. So essentially the scientists are viewed as the ones who solve problems that people don't know they have in ways they don't understand. So, so in a situation where there is a lack of scientific literacy, combined with the fact that mainstream media has a negative opinion on the research that is being done in a particular area, what are the key steps that you would suggest should be taken for outreach?
Yes. It should be included in the curricula in the university. Start with Bertrand Russell first.
But I think we could have Rebecca answering.
Yep,
that.
I mean, I think we all have opinions about this, right? And I think we probably all have similar ones. So the thing is that one thing that right now we don't have is a set of how can we do this in the best possible way? How can we increase the science literacy? How can we convince the anti-vaxxer that is our cousin that we cannot really get there? So this is something that we don't have a solution for, but we all feel strongly about it. We want to work together. I'm not so sure if we will ever be able to find a global solution on how to start that, but maybe this establishment of best practices in which we can include everybody, it could be a starting point for it. But yeah, maybe some of you.
Yeah, I was saying that I spent my own money buying Bertrand Russell's book for many of my students.
I mean, you can start by that.
Lydia.
I think, I mean, I completely agree here with Rebecca that there are no best practices and we should develop them, but there's also always a lot of things you can already try out let's say, and just see how they're received. So for example, one thing that I personally noticed is that if you don't try to address all of the big issues, but you start with something small, you can change someone's mind about something small, especially if it doesn't cost them a lot of time to learn it. If you can explain a tiny thing in 1 minute, they go like, oh yeah, okay, that part is okay, but, and then step by step you go further. If you always give everybody a book right away, not necessarily that book, but a book, saying, hey, here is the solution to all your problems. You should now spend the next 8 hours reading this book. A lot of people go like, no, because that, see, here you go. You don't understand me because you want me to read a book. And if you instead give people the opportunity to just watch a TikTok video for 1 minute saying, hey, look, there is something small that you can understand, then after clicking through 60 TikTok videos, they've still listened to an hour of lectures. That's a good one.
Yeah. So one thing that I think is important is we should also be really careful about how we phrase things with the public, because, for example, right now, Rebecca, you had said very quickly, yeah, for example, how do we convince anti-vaxxers? So the first step is not calling them anti-vaxxers in the face. That's a good point. You're right. Yeah. Because otherwise you put them already as you are another group and we are fighting with each other somehow.
That's a good point. I mean, I agree with that.
Yeah. So yeah, basically those. Sorry?
Telly, you're doing so well. With
well, I don't live there since many years, so I kind of.
So you're worried about others, I suppose.
Yeah.
I was thinking about the requests of the internship. So for me, from the other side, when so I just can bring my experience, I get a lot of requests of internship from people I don't know. And since I'm very busy and overloaded all the time, often I just ignore the emails. Because when it does not come from a platform I know or a person I know, I just don't have the time really to go through. Even I scan the CV. So I was thinking, could it be possible to ask now NUPEC, APEC, and this other thing, which I cannot pronounce, maybe to support us in producing a platform, so where students who are interested can, let's say, voice their interest in doing internship. And then so that when we get, you know, kind of a pool of requests, so that if I would get it through, obviously, it needs some organization and scrutinizing, but we can ask, for example, people like me to participate and, you know, and have a look at the curriculum or contact the supervisor, so that you have a platform where people can apply somehow, and then you have, like, I don't know, a board and, where jobs, let's say, internship are advertised and are taken with a little bit of control, because I think that otherwise it's very difficult, even for people who are willing to, you know, provide internship. I would not take anybody, honestly, right? I mean, so, yeah.
You have been inspired for particle physics, which works very well. So, I don't know in nuclear physics.
May I comment on this?
Yeah,
so,
there's a comment from Michelangelo.
I think even more could be done along the same lines, like having some joint networking events from EFCA, NUPEC, and APEC, where senior researchers come together with young talents. They might come from their, you know, bachelor's or master's or even earlier, although it might be a bit more complicated. And that's how you create cross-sector connections, which can become synergies in the future, and you also create opportunities for the students.
Only a little bit. No, I was just going to make a comment for people who are skeptical about science in general. I think one of the most important things we can do is listen to them. Because honestly, you come and you just talk at them, that confirms their belief that we're arrogant, that we're elitist. I think we want to make sure that we give people an opportunity to tell us what their concerns are, and then I think you're much more likely to be able to engage them in a positive discussion, which will hopefully lead them to changing their ideas, and that scientists are actually trying to help them and help their lives and address some of the concerns that they have.
Super good point.
My comments were on two topics, but connected to this, I think what Rebecca said, very important, the social media. And we had a really short experience recently, and we just appeared on LinkedIn. I don't know, Rebecca, why LinkedIn was not in your list, but anyway.
It is. We are also in LinkedIn. Yes, we're working on it.
But we had a huge impact at the university level within 6 months. And basically, it's not that more people want to come work with us, but they know about us. And I think that's the message we want to get. And just on the training, if we want people to be interdisciplinary, we will have to give the opportunity to become interdisciplinary. And that's, I think, what the system doesn't allow at the moment. So people are very focused on finishing a PhD, specializing, first postdoc, fast results. There's no time for cross fields. And if we want to have that, we need to give people time for that, to be able to talk both languages, what the fields they are mixing, whatever they are.
Colin, I'm afraid that we used up our time, but you are the chair of the session. You can.
We can continue in front of the posters with the refreshments. Thank you for the picture. I was in that picture.
Intended to have a take-home message around, but I'm afraid we don't have time for having another take-home message round. We had a lot of good suggestions already here, and I was really baffled by this intense audience response. This was it wasn't a panel discussion; it was a plenary discussion, and that's what I aimed for to get it started. So, if we continue the discussion at the poster session, it would be great. I thank a lot all the panelists, and Colin, give you the last word.
Last word is, there are many other books written by Bertrand Russell. His name is About Education, so you can also use it. Sorry. Okay, so have a nice evening. Don't forget we have a football match this evening.
To discuss and continue these very interesting talks. Thank you.
I would have loved to discuss already, but there wasn't